Hello, KK.
Hi, Manlan. Glad you're here.
Sorry, just finished family stuff. So you're going to share slides, right?
Right, I will. Yes. Chi-Lin said that, Professor Wang will have his opening remarks, then we can speak.
Yeah, sounds good.
Good morning, everyone. A warm welcome to the 5th Asia-Pacific Workshop on Networking. Due to COVID-19, the workshop this year is streamed on Zoom online meeting with live broadcast on YouTube and Bilibili. Thank you again for participating. Our program chair, Professor KK Ramakrishnan and Professor Mingnan Yu. We also welcome our Professor Perek and Professor Stoika as the keynote speakers for the workshop. Let's now welcome Professor Wang to give an opening remark on behalf of the General Chair.
Okay. Chulin, please release your. Okay. Hello, everyone. Welcome to APNet 2021. I'm Iwan from Southern University of Science and Technology. So this is the 5th Asia Pacific workshop on networking. APNet is encouraging research and publication of new ideas in networking and systems. Following APNet 2020, a strong mix of new research and ideas from both academia and industry. This APNet 2021 will have 2 keynote speeches, 9 accepted papers, 6 industry spotlight talks, and 7 SIGCOMM NSDI sharing talks. So thanks to our supporters. Thanks very much to the sponsors, Huawei and Tencent. Thanks also to SMC, SIGCOMM SIG, Tencent Laboratory, and the Hong Kong University of Science and Technology, and the Chinese Institute of Electronics. So this is the SAM-SIGCOMM policy: open exchange of ideas, freedom of thought and expression, central to SAM's aims and goals. So please refer to the SAM-SIGCOMM SIG website for complete policy. Let us make the conference enjoyable for everyone. Please visit the workshop website for all details. With our keynote will be have the day 1 at the afternoon 2 o'clock is the first keynote speaker, and the second keynote is in the day 2 9 a.m. 9 o'clock. So please notice the keynote speaker. So last, thanks to all the members of the organizing committee, and thanks to the steering committee, especially Kaiten, Danley, and Quentin for their guidance and help. Thanks to TPC co-chairs KK and Minglan and the technical program committee. Thanks to all the others, and thanks to all the participants and each and every of you. Thanks. Welcome to APNet 2021.
Thank you, Professor Wang. And now let's welcome our program chair, Professor Ramakrishnan, and Professor Yu to give us the opening remark.
Thank you very much. Folks, welcome to the 5th APNet workshop. I've been to several of them, and they're very active. I wish we were physically there to have the workshop, but we would like to make this as close to what we could have if we were all together physically. I'm KK Ramakrishnan, and I had the honor to be a co-chair along with Minlan Yu, who always stayed a step ahead of me, and she was the TPC chair and I was just an assistant. So I'd let her take the next step.
Thank you, KK. You are really the one who does most of the work. And we would like to also thank our great TPC members, 28 of them. They put a lot of work in reviewing our papers and make the nice program. And they are also from 8 countries, so it's a diverse set of PCs. Thank you all for helping the program. Yep.
We received 20 submissions, almost exactly the same as last year. Definitely there was an impact because of the pandemic. We would have liked it to be a lot more. We nonetheless went through what we felt was a rigorous process that we would have otherwise gone through with any of the other APNet workshops. Each paper got 3 to 4 reviews. There were some violations of double-blind rules that we fixed ourselves before the reviews were taken. We did have, after all the reviews were submitted, a discussion phase for a week. We did get a few extra reviews, and we had a PC meeting online by Zoom with a majority of the PC members attending. And I must say that there were some fairly intense discussions. And in fact, some papers were selected for shepherding, and I believe that they improved as a result. We did accept, as Yi said, 9, and we think very high quality papers.
Yeah, we would like to have special thanks to Kai and his students. Kai have been making persistent effort to continue this APNet workshop, and it's having increasing impact. So thank Kai for the organization. And we would also especially thank Qing Huang from Peking University. He has been the publication chair and has done a lot of work in putting the papers together in the proceeding and publishing ACM and coordinating with authors and ACM. Thank you for your effort. Next.
Yeah, his work never seems to stop. He had to do some work even last minute.
Even today.
We would very much appreciate that you mute yourself during the presentation. If you want to have a question, please, during the Q&A, you can raise your hand before speaking, and one of the co-hosts will call on you, or the session chair will choose, and you can then speak. Of course, at any time, you can type into the chat window, and we will have the session chair or one of the co-hosts do the best to pick your question, speak, and have the speaker then answer your question. Our apologies if we can't pick all of the questions to answer. Please feel free to contact the speaker during a break or after the workshop. And certainly if you have any questions, we are always here to answer during the meeting, by email, whatever.
Yeah, and I would like to add that you can leverage the Zoom chat to communicate with authors, and authors should feel free to continue answering questions for those that session chair didn't pick. Okay, so here's our schedule in day 1 today. After the opening remark, we're gonna have the SIGCOMM and NSDI talk session, and then we will have the APNet paper session on network measurement and congestion control. And then we will have the poster session, will be on the same Zoom link. We will have 5 minutes for each poster. And then at 2 p.m., we will have the keynote from Andrea Perrick on the internet architecture. And then in the afternoon, we will have APNet papers on network programming and industry spotlight. Next.
And the industry spotlight talks are really a big feature of APNet. We encourage you to definitely listen to them. Tomorrow, we are fortunate to have Ian Stoika from UC Berkeley give a talk on RAY, their framework for distributed computing. We'll have another industrial spotlight talk session, and then the last APNet paper session. The final session of the workshop is rounded out by SIGCOMM NSDI talks.
Yep. That's the end of opening remark, and let's start the next session. Yeah, enjoy
the workshop. Yeah.
Thank you, KK and Professor Yu. So now, without further ado, let's start our first session. Let's welcome our session chair, Professor Kai Pen.
Hi, yeah. So welcome the first session. We have like over 60 audience here, and we have several hundred, like over 200. I think now we have more than 200 broadcasting like online. So the first session, we will have 3 speakers. The first one is Wu Wenfei from Tsinghua University. He will be talking about how to do in-network application for deep learning training. Okay, Wenfei is now a system professor from Tsinghua University. He got his PhD degree from University of Wisconsin-Madison, and his research interest is in network system. And recently, he has several best paper or best student paper award, for example, in SOCC, IPCCC. Most notably, he just got the NSDI 2021 Best Paper Award, and today he will be sharing that paper. Wenfei, please.
Yes. So I'm online. Okay, let me share my screen. Thanks for the introduction. So I'm going to talk about this work, ATP, in network aggregation for multi-tenant training. So this is a joint work with my colleagues from University of Wisconsin-Madison. So machine learning is applied in various applications, such as natural language processing, image classification, or even in the infrastructure management. In machine learning, the algorithm would take, with the increasing size of the data set and models, as well as in some specific scenarios, machine learning systems are distributed systems now. In machine learning, this algorithm would take epochs to compute a gradient and update the model. When this computation is distributed, especially in data parallel mode, the data set is partitioned and put on multiple workers. So each worker would compute its own gradients, and all these gradients are aggregated and used to update the model. To support this kind of gradient aggregation, there are two typical architectures. One is called drain or reduce. It takes 2 rounds to do the aggregation. In this example, there are 4 workers, each with a gradient. The gradient is chunked into 4 pieces. The first piece would would form a ring from A to D and get aggregated in worker D. In the second stage, the aggregated result would form another ring and send to all 3 other workers. Assume the gradient size is m. Each worker needs to exchange 2m data with each other. The second architecture is PS architecture. So a few parameter servers are set up. So the workers would send all their gradients to the parameter server. The gradients are aggregated and sent back to each worker. So in this architecture, each worker would exchange data of size m with the parameter server, but the parameter server would need to exchange nm data with n workers. So there are studies showing that such network communication would cause the total training to be a few times slower than the solution without the network communication. So it becomes a network bottleneck. Recently, there are programmable switches which has a memory to store durable states, and they also have computing circuit which takes the packet and the memory states as input. It can modify the in-transit network as well as the memory. This new type of device shows a potential that we can merge the information from multiple packets into one. So which can potentially can be used for gradient aggregation. So we call this chain to be in network computation. There exist some works to use in network computation for gradient aggregation. One example is called SwitchML. I would briefly introduce it. So in each worker, the gradient is organized as a sequence of packets. So different workers have different sequences. So the tensor is organized in an array of packets. And also the switch is also, switch memory is also organized as an array. In this example, there are two workers. So the first worker's packet would be sent to the switch and reserve the memory in the switch. So the packet is consumed and dropped. The second packet would be accumulated on the switch memory. When this accumulation is done, the result is sent back to each worker using multicast. So this solution is the first prototype to use in network computation to accelerate machine learning. It targets the scenario of a single job and a single rack. In practical deployments, there is usually an infrastructure shared by multiple tenants. When there are multiple tenants, there would be multiple distributed training jobs. And recently, the large size of the model make the training cannot be handled by the machines in a single rack. So, for example, in BERT, in the training of BERT, they use tens of machines to do this training. So, thus, in ATP, we set up 3 goals. The first goal is we want to leverage the programmable switches to accelerate distributed training. Then, targeting the deployment scenario, we want this solution to support multiple simultaneous jobs and complex topology with multiple racks. So after design this ATP, we also find that it makes other contributions. For example, it can improve the floating point computation, and it can also has throughput optimization. I would describe how do we support multiple jobs and multiple racks. In supporting multiple jobs, we find that the end host reliability needs to be redesigned, and also we redesign the congestion control as well as the floating point calculation. So how do we support multiple jobs? A straightforward way is to partition. Since we have architecture to support a single job acceleration, if we want to support multiple jobs, a straightforward way is to partition the switch memory into several regions. So each job reserves its own region and do in network aggregation. We call this solution to be static allocation. Another alternative solution is what we propose in ATP. We call it a dynamic allocation. Compared with static allocation, dynamic allocation has its own advantage. First, in machine learning algorithms, the algorithm iteratively do computation and communication. So if we statically allocate switch memory, when a job is in the computation phase, the switch resource cannot be used by other jobs, so the resource is not fully utilized. Another reason is if we do static allocation, we need to handle the complexity of integrating the switch memory management with the job placement. That is extra complexity. So if we do dynamic allocation,
recording in progress.
If we do dynamic allocation, we can take this advantage and avoid the complexity. To do dynamic allocation, the switch memory is still organized as a basic computing unit. We call it aggregators. But each job's packet would be randomly hashed to one of the aggregators. Here we use the hash function to hash the field or job ID and the sequence number in the packet. So the different packets from the same job with the same sequence number, but from different workers would be hashed to the same location and get aggregated there. Let me show the example. So in each worker, the tensor is organized in a sequence of packets. Switch memory is another array of aggregators. in each packet, there are fields to describe the job ID and the sequence number. So this shaded aggregator means it's reserved by a job, otherwise it's empty. In the ideal case, the packet from different workers would be hashed to the same location. If this location is empty, so the packet would be aggregated there and sent to the PS. The PS send the result back to the switch memory. It would deallocate the memory and multicast to the worker. So here we keep the design of the PS different, which is different from switch ML. There is a reason, because switch memory is not always available. There may be hash clearance. So we keep the PS as a fallback. So in this example, the packets are hashed to an aggregator, which is reserved by another job. In this case, the packet would not be aggregated, but sent to the fallback PS. The PS would do the aggregation, and the result is sent back. It does not deallocate the switch memory, but it would be still multicast back to each worker. Okay, so until now, we have the best effort service in the switch, and the end host needed to customize the networking stack to provide a fallback. But there is a corner case. The aggregation may be incomplete. That drives us to redesign the reliability. In this example, when the first packet arrives at the switch, the switch memory is not available. But after a while, this job-wise aggregation is done, and the switch is deallocated. Then the second packet arrives, and it would reserve switch memory. So the two packets are in different places, and they are waiting for each other. That forms a deadlock. What's worse is that there is no no result replied. So this memory would never be released. It would cause memory leak in the switch. So to handle this, we inherit the design from TCP. We retransmit the packet. So if a packet does not, the result does not arrive at the sender, the worker would always retransmit the packet. We use the duplicate ACK and timeout to trigger this retransmission. Here we need to use the retransmission for in-network computation and packet loss. It's not trivial because in this scenario, the reliability, the semantic of reliability is not the same as TCP to recover lost packet. It need not only to recover packet loss, it also must guarantee the computation is correct. All the aggregation must be done once and exactly once. And if possible, it needed to proceed the in-network aggregation, avoid memory leak and deadlock. To do this, we let the end host to always retransmit on arrival packet, and we add in the switch in each aggregator, we add a bitmap to record whether each worker's gradient is aggregated. So with the bitmap, we can dedupe the duplicated data. We can add the dropped packet to guarantee the correctness. So details are in the paper, and I'm also happy to discuss at the end of this talk. Then we also redesigned the congestion control, because in this case, there are multiple jobs. They share the switch resources. In ATP, the scenario is a bit unique because here is a many-to-one communication. We need to design congestion control for this. And the end host content not only for link bandwidth, but also for switch memory. There are new switch resources to contend for. So to design a congestion control mechanism, we need to make two decisions. One is what should be the congestion signal. Second, what is the congestion control algorithm? Here, there are multiple choices to choose the congestion signal, like RPT, ECN, and packet loss. Packet loss is definitely a signal of congestion, but among RTT and ECN, we choose ECN because in network aggregation, most packets are consumed in the switch. They do not have round trip, so they do not have RTT. So the switch would have aggregator would have a bit in the aggregator, which accumulate the ECN bit from multiple workers. So this design makes the total progress to be keep the same with the slowest worker. But this is reasonable because in synchronized training, so the workers need to be synchronized between epochs. In the congestion control algorithm, we use window-based adjustment using additive increase and multiplicative decrease scheme. Okay, so next, we need to extend this design to multiple racks to adapt to a complicated data center topology. So in this example, the aggregation would form it's a hierarchical aggregation. There are two levels. There are three switches. The switch 2 would do a second level aggregation. So there is the design above need to make some customization. So and the host doesn't need to change anything, but for switch there is a complication. Because in the previous design, we use a bitmap to record whether each worker would participate the aggregation and the switch. But in the higher level, one bit here, one bit for example, one bit in switch 2 for switch 0 cannot represent all the 4 aggregation cases from worker 0 and worker 1. So the switch cannot be naively applied. So for higher level aggregation, there should be a customization. So the bitmap in higher level customization would only would use 1 to denote the case that all the descendants are aggregated. In all other scenarios, if, for example, if it get a switch 2 get a partial result from switch 0, it would not do any aggregation in switch 2, but only send fallback and send the result to the PS. PS would handle all the exceptional cases. So this design can be extended to many levels. In our current design, we support a 2-level aggregation due to a header space, and also in data center, there is non-deterministic routing like ECMP. So all the switches in the aggregation switch and the core switches use ECMP. So there are multiple paths. So it's hard to check whether 2 flows would be merged at a specific point in the higher level. But the Tor switches are deterministic points that all the flows would definitely go through. So it's easy to build the aggregation hierarchy on Tor switches. Currently, we can support more than 1,000 servers now. Okay. So the floating point design can also so this architecture can also improve the state-of-the-art floating point value calculation. Because in current switch, it does not support floating point arithmetics. So we need to extend existing in-network computation cannot handle, cannot do this, cannot natively support floating point calculation. So in current solutions, usually people scale the floating point to integers, aggregate the integer and scale it back. So there is a problem of choosing the scaling factor. If the scaling factor is too small, it would and we scale a floating point value with a small factor, then we abandon the floating decimal parts and only aggregate the integer parts. In this case, we would lose the precision. But if we choose a very large scaling factor, large numbers aggregated in the switch may cause switch overflow. But in ATP, we can simplify this design. We just use a large scaling factor because in any case we have the PS as the fallback. So for 32-bit floating point value with 7 decimal digits, we multiply the value with 10 to 8 and use the integer parts to do the aggregation. The switch would detect the integer overflow. In that case, the switch would not do anything, but all the values are sent to the PS. PS would handle the exceptional case. Okay, so to summarize, ATP in the ATP architecture, it contains the aggregation service in the switch and the networking stack at the end host. The switch is a simple service. It's a best effort service. It can support multiple rack and floating point, but still it's best effort. It doesn't provide any correctness guarantee. The end host would provide a fallback, reliability, and congestion control, floating point calculation. Okay. So this this design complies with the end-to-end principle. We keep the switch to be simple and the host to be complicated. So in the current implementation, we also make the current implementation combines 4 techniques. One is the programmable switch, DMA, NIC IO for acceleration, kernel bypass, the user level protocol stack, and we connect it with machine learning frameworks using BytePS. So there is an engineering optimization that is in programmable switch. Current programmable switch can only support 184 byte of packet header parsing. So our packet size is limited by this constraint. So we make some switch specific optimization and increase the packet size to be 300. And with this optimization, as well as some offload features on the NIC, we improve the throughput to be 60 gigabit per second. Currently, we use DPDK. We can improve it to 100 now. And we conduct some experiments to show its feasibility. In the test bed, we use 8 workers, and we have 9 servers, 8 for workers and 1 for PS. We use NVIDIA NIC, NVIDIA GPU, and Mellanox NIC. The switch is a barefoot switch with 32 ports. So we compare ATP with other architectures, including PS architecture with 1 PS or several PSs. We also compare, improve the existing PS architecture with RDMA acceleration. We also compare ATP with switch ML and ring or reduce architecture, also with RDMA acceleration. We run workload of different famous models from ImageNet, AlexNet, VGG, and ResNet. So first, let me show the single job acceleration. We use the training throughput, it's the average image per second on each worker as the metric. In each group shows the result of one machine learning model. We get the following observations. First, in some cases, for example, in the parameter server with many to one. In this case, network is the bottleneck, and the ATP solves the bottleneck. So we get the performance acceleration. In some workload are computation intensive. So while ATP cannot improve them significantly, but it's still the best. The improvement is not acceleration is not that significant. So if the network is not the bottleneck, ATP is slightly better than hardwired, but it compare ATP with ring or reduce architecture. ATP is slightly better, but it only consumes half of the bandwidth. We use another metric, time to accuracy, to measure the to show the training quality. So the result is the observation is that the time to TTA complies with the throughput. So if the network is the bottleneck for VGG, we improve the network throughput. We can accelerate, we can improve the training time. But if network is not the bottleneck, ATP has the same performance with other architectures. So here we show the result of multiple jobs. In this experiment, we also compare the design choice of dynamic and static allocation. So we run 3 VGG 16 jobs, and we first tune the switch memory to achieve the peak throughput. Because if we give the jobs very little switch memory, the throughput would be low. But if we give them, we increase the switch memory until we find the throughput arrive at its peak. It's the peak throughput. We call it, this is a 100% PTA. Then we decrease the switch memory. And in the dynamic allocation is the ATP's design. Static means we statically partition the switch memory and assign the switch memory to 3 jobs. So this figure shows the result. With less switch memory, the throughput would decrease. But comparing the dynamic and static allocation, dynamic allocation decreases more gracefully. So to summarize, we have other results in the paper and also in the backup slides. To summarize ATP, in ATP we design a network protocol which contains the aggregation service in the switch. The switch do best effort service, and the unhost networking stack has complicated mechanisms to provide fallback to provide correctness guarantee. It handles the hash collision, packet loss, floating point overflow, multi-rack deployment. It also has reliability and congestion control. For machine learning jobs, this design can support our target scenario, multiple jobs, and multiple racks. It provides a performance gain, and it has a correctness guarantee. So to conclude, now switch can compute, and its computing circuit is orders is a few terabit per second, which is more than 10 times of the PCIe on server. So if we use switch to compute, usually we can get a very significant performance gain. And we show the case to use ATP to accelerate machine learning. But in this case, correctness guarantee is hard because the in-network computation introduces some other semantics in packet processing, like a packet may be consumed, which should be distinguished from the case packets are lost. Packet transformation is not a packet corruption. So correctness guarantee is difficult. So usually we need a switch and then host co-design. So we can get both performance gain and correctness guarantee. So this is a very large research space. And here are some other some directions that worth thinking and worth discussion for the next step. One is switch resource management. Here we use sharing in switch ML. If we can handle the complexity of switch memory management, to provide isolated memory for jobs, we can provide a SLE guarantee. And for ATP specific job, how do we design the control plan policy given multiple jobs and the infrastructure? How do we make the infrastructure carry more jobs? Here, if we introduce in-network computation in the protocol design, so there are new properties to verify, like correctness and consistency. I'm also thinking, how can we, in the current ATP design, we open source it, but it usually we need to set up a cluster. I'm thinking whether we can, any of us are interested in to build tools for researchers without a cluster to do this research. And in-network aggregation can be used for other applications. For example, in big data, in the MapReduce. Reduce is a very typical scenario that can use in-network aggregation, and also in file systems. There are other opportunities. And ATP is open sourced on the GitHub, and we are maintaining the compatible hardware and software versions. Audience, if you are interested, you can contact us and get the deployment menu. So that's all about my talk. I'm happy for questions.
Okay, thank you, Wenfei. Questions? Maybe first one from KK. You want to ask a question?
Thank you. Wenfei, very nice talk.
Yeah,
I have this question on the congestion control component.
Yeah.
Naturally. You've got two dimensions of what constitutes congestion, right? One is that you are occupying space in the switch in terms of spatially how much memory is being occupied.
Yes.
There is also a certain amount of computation that the switch has to do.
Yeah.
So what aspect constitutes congestion? And the second component of my question is, if I have multiple jobs, how do I deal with fairness across these multiple dimensions for using your ECN and AIMD to achieve some notion of fairness across multiple competing entities, competing learning tasks progressing concurrently?
Yeah, thanks for the question. Let me explain. The first question, in ATP, there are two resources for contention. One is the link bandwidth. Another is the switch memory. We analyzed the second case especially. So once in both cases, actually the final SIGCOMM is the queue, switch queue build up. ECN is a good choice. In the first case, if link are congestion, the queue would build up. In the second case, if switch memory is not sufficient, there would be more packets. More packets would not be aggregated, so queue would be still be built up. So we use ECN. So yeah, the second.
I get that, I get that, but some jobs might sit around for longer than others in the queue, right?
Yes. Yeah.
So even if you have a small occupancy, you might be holding on to it for a long time. Is that a concern or not?
It's not. So the switch memory is allocated in a first come first serve without preemption. So yes, if a job reserve the aggregator first, it would get more advantage. The later job would experience longer waiting time. But statistically, I think it's related with your second question, is the fairness. If two jobs, they are sending packets, they are supposed to have the same the same opportunity. Two same job would have the same opportunity to reserve the switch memory. But also for your second question, if jobs are the same, also in our experiment, they have the same chance to reserve switch memory. So they would get a fair allocation of the switch memory as well as the bandwidth. But for different jobs, we don't have a mathematical model right now, but we are doing experiments. There are slightly difference. They do not get equal share of the switch memory. Yeah, that was the study about. That was the study of the fairness.
Yeah. Okay. Thank you very much.
Yeah.
So, as the audience, if you have questions, raise your hand.
I'll try to.
Anyone? Okay, so yeah, actually, I'm the shepherd of your paper, Wenfei. I have all my questions have been asked during shepherding, but I'm going to ask maybe on behalf of the audience, some audience who are shy. So for like parameter synchronization, right, we have primary server or ring, right? I know your solution ATP will be effective when in primary server, well, those parameters can meet each other in the network, right?
Yeah.
But for a large portion of their aggregation or synchronization, they're happening in ring or hierarchical ring, okay?
No.
So any chance like in-network application approach can take effect in such scenario, or no chance?
Yeah, I think actually, if we think about the ring or reduce, for or reduce part, if we know some part would be, if we don't think about this ring, we think about ring or reduce. In this case, in the ring, they form a pipeline. So data are sent in. They do not send simultaneously. They do not meet in the switch. So there is no chance. So if you with ring, but if we rethink the send and receive pattern, actually all these 4 pieces of data just need to meet in the switch. They can get aggregated. For reduce part or reduce, we can do in network aggregation. But for ring, I don't think so. Actually, by the PS N2N PS architecture is also or reduce or reduce architecture that can be applied. So my point is if the data can be sent simultaneously into the network and meet in the network, then there would be chance for in-network aggregation. If they form a pipeline, there is no chance.
Right. Okay, so I think that this is going to be a hot topic followed by many audience here in the Zoom or online. We have over like nearly 2,000 people watching online. So I'm thinking, for example, parallel work, which is switch ML, right? Also NSDI.
Yeah.
So how do you compare your work ATP with switch ML?
Yeah. Actually, that work start early than ours, and they are released on archive first. So we also will definitely refer to some design of them. One is, for example, the quantization part, and so our project actually started later than that. So we we observe that switch ML in that design, it targeting to accelerate a single job, and by its default topology is a star topology with the switch in the middle. Workers connected with the switch, so it's a single rack topology. So our design would be so in the deployment we consider the deployment scenario. We need to support multiple jobs. So that drives us to redesign the switch memory allocation mechanism and also multiple racks. Well, multiple racks is a natural extent, but yeah, we do that work.
Okay. So last question. Okay. Also asked on behalf of the audience. So you at the end you suggest several like possible opportunities, but on the other hand, do you have any suggestion on the traps, like so for the new research in there, they give a warning or just caveat to them?
Yeah,
something that definitely not possible if you want to do this.
Yeah. So my feeling is there are a lot of new things to study, but yeah, here I list some like switch memory management, and especially here, this protocol can be used in other applications. But to do that, I think I need to refer to these slides. Usually, switch acceleration performance gain is easier, but CoNEXT guarantee is difficult. And to do that, I think the first suggestion is in network computation need to be accompanied with user with the customized network stack. Yeah, because of the CoNEXT guarantee. To do that, I think we need to learn. Researchers need to learn both the switch and the how to build a user level stack to do this prototype. And the second is yeah, that's the first suggestion. The second suggestion is even in the switch programming switch that the programming switch is not very easy to use. Usually we need to find good vendors that to deliver a totally workable switch with the SDK and also the deployed. So you can save the development time. And yeah, that's my two suggestions to do this kind of research, especially if you want to build a system. You need to do both the and host programming, the user level stack, network stack, and the switch co-design.
Okay. Okay. Great. Thank you, Wang Fei.
Thanks.
Yes. Thank you.
Okay.
Okay. Maybe you can finish sharing. The next speaker can share the screen. Okay, so our next second speaker is Professor Junchen Jiang. Junchen Jiang, Professor Jiang is an assistant professor at the University of Chicago, Computer Science. He got his PhD from CMU 2017 and a bachelor from Tsinghua University. His research interest include network systems and their intersections with machine learning, especially Junchen has done a lot of great work in video streaming. Okay, and he is also a recipient of a Google Faculty Research Award in 2019, Best Paper Award at Symposium of Edge Computing 2020, and the CMU Computer Science Doctoral Dissertation Award 2017. And today, Professor Jiang will share his research work on perception-driven optimization, a new frontier for scaling internet applications. And for the audience, I would encourage you to raise, to ask questions or type your questions in the chat if you have. And Professor Jiang has a very rich experience, especially in internet, those video streaming, this internet applications. So, you know, don't waste this chance to ask your questions. Okay, so Junchen, please.
Okay, thanks. You can hear me, right?
Yeah.
Cool. Right. It's a bit strange talking about video streaming while everyone is on Zoom. So thanks for the introduction, deeply flattered. In the next talk, let's now switch gear a little bit up the stack, the network stack, and talk about internet applications that people use every day, like video streaming. And let's see how to improve users' experience of internet applications by a deeper understanding of users' perception of internet service quality. And as we'll see, the key insight in this talk is to align network resource allocation with user attention. Okay, so let's get started. First of all, as you all know, content providers always seek to increase users' engagement by ensuring higher and higher quality of experience, or in short, QoE. Okay. And the key here is how to balance QoE, improving QoE, and using network resource efficiently. And this is the challenge behind every content providers, and it becoming increasingly challenging for a multitude of reasons. First of all, there are simply more and more users and more devices, of course. And moreover, there are more videos in higher resolution played on bigger and bigger screens. The applications are also becoming more and more interactive. And finally, and probably more importantly, users are just becoming more and more impatient to low quality services. So if you put these trends together, okay, this is what we got today, right? So a rapid growth of internet traffic, which would soon overwhelm ISPs. And this is not just distant future. With more people staying at home, working or watching YouTube, or just doing Zoom calls these days, the video streaming services are forced to uniformly lower their quality sometimes to prevent the ISPs from the internet from collapsing. So this is the reality. Now, what I want to do is step back and ask the question: does it really have to grow so fast? Okay, and the answer our answer is not really necessarily. The basic insight behind this is every user only has a limited span of attention. And now let's look at what do we mean by attention first. Okay, now attention is a widely used term in the user experience literature, user experience design literature. For instance, we all have this experience driving on the road while holding the GPS or cell phone on your hand and reading something. This is obviously not a good design, not a very safe design. And obviously better design is what's on the right-hand side, right? We blend the GPS screen or the cell phone screen on the windshield, okay? This is because when you are driving, you will naturally pay more attention to the road. You will basically looking at the windshield. Right? And if the important information is displayed on the windshield, this will be directly under the spotlight of your attention. Now, this is just something about user experience design, which is not going to be the focus of this talk. But there's analogy. Okay, this analogy in user experience design, the most efficient way to display information is to put it where user attention naturally is. And this has been one of the basic design tenets behind all user experience designs. Okay, now what we're trying to argue is that as narrow system designers or narrow application designers, we should similarly put network or compute resources where user attention is, when and where user attention is. Okay, for example, when you allocate network bandwidth, CPU cycles, cache space, put more resource to the content or the time window when or where user will pay more attention. Okay, so this is a high-level idea. Now, what's the offshoot? Well, if we allocate resource proportional to user attention, and because each user has limited span of attention, the total amount of resources needed is simply linear to the number of users. Okay, it grows linear with the number of users. And this has a huge implication actually, because basically no matter how large the screens become, or how high the quality of, how high resolution the quality is, or how impatient users are. Each user is always going to perceive only a limited amount of information, or so-called a limited number of quality, if you want. Okay, so the total amount of resource demanded by these applications are going to be bounded by number of users. It's not going to grow so fast. Now, as good as that sounds, this paradigm may sound, I don't claim I have a generic solution or a architecture to apply this idea to all applications. Now, instead, in this talk, I will show you some preliminary studies, pick some case studies from our recent work, including internet video streaming, web services, and video analytics, some emerging ML-based applications, and show you how users' attention is unevenly distributed spatially and temporally, okay, and how it could be harnessed, okay? So let's start by with video streaming, internet video streaming, as a first case study of perception-driven optimization. This is a joint work with Microsoft Research. Now, let's first see how what's the conventional wisdom of internet video streaming? Okay, now traditionally, video streaming systems, what they want to do is try to optimize quality everywhere, okay, during a video. So basically, rebuffering stores, low quality, low visual quality, or quality switches, bitrate switches must be avoided at any cost anywhere during a video. Okay, there's no important region, non-important regions. Everywhere must be no rebuffering, should be minimizing the rebuffering ratio or low quality, low resolution quality. Okay, so as you can imagine, this is pretty restrictive, right? So especially for long videos. Okay, and this is actually one of the reasons pushing the bandwidth demand of internet videos to be so high these days. Okay, now, however, we want to step back and ask the question like, does the quality really have to be optimized uniformly everywhere? Okay, and to answer this question, we did some user studies. And here, I'm gonna, in the next couple of slides, I will try to, let you do a simplified version of this study. Okay, so what I'm gonna do is, what I'm gonna do is show you two short videos, very short videos, and they are of the same content, exact same content. Okay, and after that, I will ask you which one has better video quality. Okay, so here's the first video. And in both videos, by the way, in both videos, there will be a short rebuffering stall. Okay, now here's the first video. It's a basketball video. And this guy is doing a free throw. Okay. Okay, and there was the rebuffering stall. Okay, so this is the first video. And let's look at the second video, same content and with a rebuffering stall. Here's a free throw again. And there was the rebuffering. Okay, same content. Now, it may be a bit hard to watch videos on Zoom. I did this before. Some people complained it was rebuffering everywhere. But in case some of you didn't see the video clearly, what happened in video A was there was a rebuffering stall right after the free throw. And in video B, however, there was a rebuffering right in the middle of the free throw. Okay, so which video has worse quality? Now, I don't have the time to do a show of hand here, unfortunately. But if you're like most people in our the user study, video B will seem to have worse quality to you. Okay. Now, does that mean video B, the second video, have a longer rebuffering stall? Well, not really. Actually, both videos have exactly 1 second rebuffering. Only when the rebuffering happened are different. Okay, so why video B seem to have worse quality than video A? Well, to find out, to actually review the whole thing behind this, we run a similar test on a crowdsourcing platform called Amazon Mechanic Turk, and the result was curious enough. So for people who are not familiar with Amazon Mechanic Turk, it's a public crowdsourcing platform. You can publish human tasks, like in this case, watching videos and rating their quality of experience on a scale of 1 to 5. And the platform will just automatically find cross-source workers or participants for you. Now, what we did was we showed them the video, the same video with the same video as we saw before or other videos, same content with the same rebuffering event inserted at different points of the video. Okay, and ask them to rate the quality of each resulting video with a score between 1 to 5, higher the better. Now, the hypothesis here is that if the traditional wisdom is correct, which means that users are equally sensitive to low quality everywhere during a video, their ratings, their scores will be quite the same regardless when the rebuffering happens. Okay. But this is obviously not what happened. The scores are systematically different. In the video you just saw, this is actually the scores from the videos you just saw. We have other videos. The score varied by almost 50% depending on when the rebuffering store occurred. Okay, and this shows that users have very dynamic sensitivity to video quality. Here, each bar represents the level of sensitivity of a user to a rebuffering store at different moments of the video. If a bar is high, then the rebuffering store that occurs during that moment can cause a greater drop in the scores of users' experience. And effectively, that shows users are more sensitive during that time. And that's actually why video B has worse quality, because the rebuffering really happens when the users are very sensitive. So in short, users don't evenly care about video quality everywhere in a video, and that inspired our design of the system called Sensei. Now, Sensei is a video streaming protocol that basically try to pre-profile the temporal distribution, the temporal variation of user attention during, using the crowdsourcing platform. Okay, and in the runtime, it will avoid low quality incidents such as rebuffering when attention or user sensitivity is high. Now, intuitively, why will this work? Well, because we did a systematic study across many videos, and we found that the sensitivity to video quality varies significantly over time for a lot of videos. And here, I'm gonna just show you one of the empirical studies we did. We used 16 short videos covering various content genres. And in each video, we create multiple versions by inserting still a 1 second rebuffering store at different time t, and show these videos to crowdsource participants in a random order, okay, and then collect their feedback and average the score of each video. And then we calculate how much the score would drop between showing them no buffering video, videos with no rebuffering, and having a rebuffering store at some time t. Okay. By the way, it's very important when you show people these participant videos, you show them with randomized orders, because otherwise score difference may just be a result of some specific showing orders. Okay. Now the curve here, the CDF here, shows how much different the QE drop caused by the same rebuffering store can be within each video. And we can see that for 50% of video, half of the videos in the set, QE drop vary by over 100% depending on when the rebuffering store really occurs. So this shows the opportunity to leverage this large variability of quality sensitivity within each video and try to trade off insensitive chunks for sensitive ones. Okay, so this is, again, just trying to do some resource allocation depending on user sensitivity within each video. Okay, and how to apply this in a real video streaming system? Now, the idea is quite simple. What we want to do is to align the video quality with quality sensitivity, okay, which means avoiding bad quality when sensitivity is high. Let's see an example here. Let's consider this session where the y-axis shows the buffer length, and when the buffer length becomes 0, of course, you're going to have a rebuffering store. This is actually what today's players are going to normally do. This is like pretty standard video player behavior if it is not aware of dynamic quality sensitivity, okay, the dynamic sensitivity of video quality. However, this would not be an ideal outcome if the rebuffering store here occurs during when the quality sensitivity is high, such as, for example, the free throw example from the basketball video, if you remember. Now, how to avoid the rebuffering when users have high quality sensitivity? Well, this is quite straightforward. What you can do in our system is we try to predict the trajectory of buffer length, okay, and then schedule the rebuffering stop earlier. Okay, you just move it ahead such that users have a higher quality when they are actually sensitive to quality. Okay, so this is, of course, a vastly simplified view of the algorithm in the paper, and more details can be found in the paper, of course. This is NSDI paper this year, but the key idea is basically the same. We want to align video quality adaptation with the dynamics of user quality sensitivity. Okay, so let's just see some quick evaluation. The paper has a lot of results, but let's just to save you time, let's see just one example. Here, the census, we show the census QoE versus bandwidth trade-off, okay? And we compare that with some recent solutions that use pretty involving bandwidth adaptation algorithms, but these bandwidth adaptation algorithms all assume quality matters everywhere during a video. So there's no like sensitivity dynamics behind them. And it allows us to make claims like Sensei improves QoE by 70 to 50% on different videos without actually using more bandwidth. It's the same amount of bandwidth, but because you allocate the quality, schedule quality events more smartly, you can improve user experience or users rating in this case. Okay, and basically Sensei doesn't invent any new video streaming algorithm. What it does is to make traditional algorithms, in this case pensive, to be aware of the sensitivity dynamism. Okay. So now, natural question here is how to automatically build such a QoE model, right? So how do you actually know when users have more sensitivity? In the project, in the Sensei system, what we did was we simply rely on processing platform like Amazon Mechanic Turks. Okay, of course, naively, if we do this naively, we would have to show participants all the videos in all possible quality levels in order to get their ratings to profile the quality of each, the quality dynamics, the sensitivity dynamics over each video. And the cost obviously would be prohibitive. Now, after some cost optimization in this paper, you can find more details, but the cost can actually be much cheaper and the process can be streamlined to be much faster. What we showed was we can do this for a 1 minute video with only $30, a bit over $30 for each 1 minute worth of video, okay? And this is not in real time, of course, but this is actually, we did some math, and this is actually doable with large content providers these days, like Netflix, or not really YouTube, but Netflix or Hulu, or these kind of large scale content providers. And it does not work, of course, for live videos. You cannot show videos to people, to crowdsource workers before broadcasting them. So they still need a better solution. And it seems a good fit for computer vision, okay? Since the only reason for quality sensitivity to vary is basically the video content, right? And we did try to do this, but unfortunately, we tried many off-the-shelf vision models. They don't really work as expected. They sort of reflect the typical love-hate relationship networking people have with ML techniques. We don't really trust them, but here we compare the real quality sensitivity obtained by user study at each time window with 3 vision-based methods, and none of them seem to correlate very well with users' quality sensitivity. However, there are reasons to be hopeful since some of these models, as you can see, do produce a similar trend at some point of time. So this is a direction we're actually looking into in a new project, right? Now, next, let's briefly discuss how this idea could be used in web services. I'm not going to talk too much about details, but this is just applying similar idea to web services as the extension. Let's first look at prior work. Of course, what's the conventional wisdom, right? The web services have been optimized for user experience for decades. So what's the conventional wisdom? To improve web QoE, the conventional wisdom is to try to cut the server-side processing delay, for example, like minimizing the mean or 99th percentile of delay for every user, okay? These techniques, there are many different techniques, but they all share the common property. They try to reduce the server-side delay for all requests with the same content, with the same criteria. Okay. And at first glance, this seems pretty reasonable, right? So there's no obvious reason to treat different web requests differently. But is it really the case, right? Let's think about a scenario. Okay, so let's say you have two users, Bob and Alice. Okay, and they request the same web page at the same time. Okay, everything is the same except the Alice request spent only 2 seconds before arriving at the web service, but Bob's request spent 10 seconds. Maybe Bob has a bad wallet service. Okay, now if you are the web service designer, you have to choose between two options. Okay, option one is you can reduce Alice's request by 1 second. Okay, option two is you can reduce Bob's request by 1 second. Okay, you cut the delay by 1 second. Okay, but you can only cut one of them. So which one would you choose? Okay, in conventional wisdom, of course, these two options just identical. They contribute the same to the same extent to the server-side average delay or 99 percentiles. But obviously, option one is better because intuitively, Alice can be improved more by this latency cut than Bob does. Okay, so why is that? Well, to understand it, let's just plot the page load time versus QoE relationship. So here the y-axis is QoE measured in time on site, basically how much time user engaged on the website. And from the perspective of human cognition, okay, this is basic human intuition. People are sensitive to page load time only in a short period of time. This is the yellow part, okay? This is so-called the sensitive region. And in this region, even a small extra delay can negatively impact QoE. Or in other words, an even small reduction of delay can greatly improve QoE. Okay, well, that's actually why you feel like cutting 1 second makes more difference to Alice than to Bob, because Alice is in this sensitive region, but Bob is not. Okay, now the delay is too long for Bob basically to care about anyway. Now, to leverage this idea, we designed a server-side scheduling system called E2E. The idea behind E2E is that the resource allocation should be made in such a way that more resources would be allocated to users to requests who are in the sensitive region, meaning that they are paying more attention to the page loading event. Okay, so we have a lot of analysis in the paper, but let's just show one simple analysis here. Okay, from Microsoft, we got a trace of 1.6 million web requests. Each request has a total page load time and a server-side delay processing, server-side processing delay. And for each request, we can estimate its QoE by just looking at the total page load time on the QoE page load time graph on the last page, right? So basically, here we have the server-side delay of each request, which is in the blue bar and the blue bars, and the page load time of each request, which is the total length of the blue bar and the gray bar, okay, and the QoE of each request by looking up this value in the curve we just saw before. Okay, so now let's imagine we can reshuffle the server-side delay among these requests arriving at the server side at the same time. Okay, so these requests who are in the sensitive region will now get less server-side delay. Okay, it's just reshuffling their server-side delay. Okay, this is obviously a similar simplifying assumption. You can't do this exactly on a large-scale web service, but this is not completely unrealistic because we didn't change the server-side delay distribution. We simply reshuffle it. Okay, so what did we find? We did this analysis on 1.6 million page loading requests, and the yellow curve here shows the improvement of QoE by doing such reshuffling. Now, if x-axis is over 0, okay, is positive, that means a request has a better QoE under this after this kind of reshuffling. And we can see that over 20% of web requests gets at least 20% better QoE. Okay, and 10% even get 50% better. And to put this gain into perspective, this seems a bit marginal, but it's actually pretty sizable because they're very similar to if the server-side delay is all 0. The blue line shows when server-side delay is all 0, which is kind of the best thing you can do with web service providers. Okay, so they're quite similar to the case where you're almost like 0 server-side delay. Okay, so this is pretty optimal. Okay, so let's switch gear from user-facing applications to a bit more ML-centric applications and see whether the attention-driven designs could improve bandwidth efficiency for these ML applications as well. So in some sense, this is going back to the video streaming problem, and this is a project with joint with Google Brain. Now, a major premise of ML these days practices automate process large volumes of video streams in various settings. This actually creates a new type of video streaming problem, as you can imagine. So basically, with more cheap cameras deployed everywhere, large volumes of video streams need to be sent continuously to a logically centralized service and to be analyzed with deep learning models or DNNs. Okay, and these DNNs are just too complex to be running on the camera, so the videos have to be streamed back. Okay, and the goal here is that the requirement is that each camera needs to send minimum data to the server to achieve good inference accuracy. You don't want to send too much data, okay, but you still want the server to get a very accurate inference. And to put this video streaming problem in perspective, let's just compare that against traditional video streaming to human viewers. Okay. On one hand, traditional video streaming optimizes user perception, user-perceived QoE with minimum bandwidth. What does human user care about, right? They care about smooth playback with everything in high quality. In contrast, the new video streaming for analytics, for vision analytics, optimizes DNN inference accuracy. Okay? And these videos won't be directly viewed or analyzed by human, but DNN models. And what do DNN models care about? Well, it doesn't really care about frame rate, right? So it doesn't care about even frame having everything inside it. All it cares about is really whether the regions that do get sent to the server have good quality for it to detect the objects. Okay? You can even skip frames that don't have real information. Okay? So there's a lot of potential here to save bandwidth. And here we plot the number of pixels that are around objects in different frames of three data sets. They are pretty typical to video analytics workload. And we can see that here in 50 to 80% of frames. Okay, the fraction of pixels that need to be successfully needed to really successfully detect and classify objects is less than 20%. Okay, in other words, object detection models, at least this is just one of the applications, but across many applications, we found that these models are somehow like human. Okay, but it's just more aggressive. They have very narrow span of attention. They have extremely narrow span of attention in terms of what pixels they really care about. And this is the idea behind our recent project called DDS. Okay? DDS is a video streaming protocol that extracts feedback from server-side DNN to identify ambiguous regions where video quality greatly influence greatly influence the DNN inference accuracy. And our measurement shows that the vision algorithms only have small ambiguous regions. Okay, these regions are really the thing that you need to send in high quality. Okay, so that's why intuitively DDS can save a lot of bandwidth without hurting inference accuracy. Okay, so just to give a sense like what how DDS at a high level how DDS achieves this, it's quite simple. For each video segment, DDS first downsize the video to a low quality version and then send the low quality version to the server for DNN inference. This is just sending low quality, so it doesn't take a lot of bandwidth and it's pretty real time. And then based on the inference, then the DNN on the server side will do some inference on a low quality video. And based on the inference output, DDS protocol would then find the regions that needs higher quality. These are the regions called feedback regions. Or so-called ambiguous regions. Okay, and then the client then re-encodes the request regions and send them in higher quality to the server for further analysis. And finally, the server-side DNN can find all the objects, correctly identify all the objects. Okay. Now, DDS also includes many optimizations, and this is kind of, you can see this iterative process. It's not very friendly to delays. There are optimizations in the paper, but let me give you a sense of one of the key technique here, which is how to get the feedback region. Okay, this is so here is an example, and let's just assume the vision task is object detection. The paper has technique to optimize to identify feedback regions for other vision tasks, but here we just look at object detection. So when the server side gets the low quality image, okay, the DNN will first return the regions, okay, the so-called region proposals here. So they're shown in orange boxes. These are the regions that might contain objects, okay, and it will also return some actual detection results, but these results, as you can see, are not very accurate. You can see some they miss some objects here in the back here, okay. Now, the idea of feedback region is to find the regions that might have objects but needs more investigations with high quality images. Okay, so one interesting case, again, you can see here is this box is not in the final detection results in low quality, but it's not in the feedback region as well. We don't want to investigate it because that region is actually big, okay, pretty big, and it's if it's a real detection, it should have been already detected. So that's why DDS protocol would discard this region in the feedback region. Again, the paper has more detail, but the main takeaway is this. Okay? Basically, the low quality video is not accurate enough. I mean, it's not enough for a model to be accurate, but it does offer useful feedback for the streaming protocol to improve its result. Okay, and these are details of how we evaluate DDS. Basically, we tried it on 3 different vision applications over 70 videos spanning several video content genres. We let DDS adapt 2 video knobs, resolution and quantization parameters. It could do frame rate as well, but we just didn't try it here. So what's the result? This graph shows the trade-off between inference accuracy on the y-axis and the bandwidth usage of x-axis, and we tried different video analytics systems. Okay, and here's video traffic camera video data set, and object detection is the task. Now we compare DDS with 2 kinds of baselines here. AW Stream and CloudSig are prior work that don't use region selection. They don't do spatially differentiable, spatially differentiated pixel encoding. And Glimpse, on the other hand, Glimpse and Visual, they rely on cheap but very inaccurate models on the camera to filter, to identify which regions are important. So basically, none of them will identify important regions based on the server-side DNN. Okay, this is the key of DDS. Okay? We can see that DDS achieves better trade-off in terms of between accuracy and bandwidth usage. In particular, DDS achieves same or higher, even higher accuracy than baselines while using 20 to 60% less bandwidth. Okay, so okay, to wrap up, okay, a fundamental issue underlying many networking challenge is the dramatically increased resource demand of applications. This is not just a problem of video streaming or web services or video analytics workload. This is kind of a cross-board challenge. Okay? This is a fundamental issue. You have more resource demanding applications. And the key idea of all these projects is to cut the resource demand by the insight that users have a short span of attention. Okay, just like right now, probably many of you are paying more attention to this cute squirrel on the right-hand side than what I'm talking about. This is typical attention at work. Now, while we managed to the prior projects can squeeze QoE improvement by basically leveraging uneven distribution of user attention, there has been a missing piece. Probably a lot of you have already realized. The missing piece is how do we actually identify user attention distribution, both spatially and temporally? This is pretty subjective, okay? And it's a challenging case how to identify that. So we believe this is the real roadblock towards systematic architecture to align network resource allocation. And instead of providing solutions, actually we don't have it right now. We posit that this is actually the next frontier of ML in networking. And this is the last slide, so we're going to just pose the challenge here. Okay, so you see, in general, ML is effective when the problem is immensely complex. Okay, now traditionally, this being it has been extensively and successfully used to model and optimize network as a complex software system, okay, like scheduling or end-to-end adaptation. Okay. Now, our argument is that ML can also be used to understand and optimize internet user perception. Okay, as we have seen, this can dramatically improve QoE with less resource demand. On the other hand, there's a ton of ML tools out there to model human cognition and vision, which might help model user perception of internet service quality. So, in short, there are just many untapped opportunities and challenges to combine ML and networking to optimize QoE of the internet. Okay, so very lastly, I would like to shout out for my students, Xu Zhang and Kuntai Du, who led these projects. They are really the masterminds behind these projects. And I will try my best to answer questions, but please do feel free to reach out to these students if you have more technical questions. Thanks.
Thank you, Junchen.
How are you doing?
Yeah, very nice talk. Summarize your great work in recent years in this direction. Okay. So I have first question. The first question from audience. Let me just read it. Okay. And for other audience, I encourage you, if you have questions, maybe speak out. Okay. Make this online conference more interactive. So the first question from audience is from Vic. His question is for Project Sensei. Can Sensei apply to live video streaming or some scenarios that have strict delay requirements?
Yeah, so that's a good question. I probably haven't said something right after this question because I did say the Sensei system doesn't apply to live video streaming right now. But the idea actually can be applied there too. So we had a recent paper submission, so I can't talk about too much about details. But basically, if you are a large live streaming provider, I mean live video streaming content provider, okay, and you have actually a lot of content, a lot of viewers of the same content, and if you know a little bit about today's internet live video streaming, the live video streaming are not really real time and simultaneous or synchronous across all users. They are users who watch the videos tens of seconds ahead of other users. So there is a chance for the Sensei idea to be applied to live video. So basically, you can online get some feedback from just monitor the action of users from earlier viewers of each video chunk, and then try to profile the sensitivity of users and apply that to later arrivals. So it's not completely the same solution, but the idea can be carried there. Okay, thanks.
Okay.
Does that answer the question? Yeah, I guess I can talk to them directly. Yeah. Thanks.
Thank you for the answer. Okay. Second one from Chen. You have a question? Yeah, you can speak out.
Okay, thank you. Can you hear me?
Yeah.
Okay, Junchen, very inspiring talk. Yeah, I can see your wisdom, to combine not only the technical, but also the wisdom from, the economics. Right. So in fact, you are choosing, in the situation you have restricted resource where you should put your resource. Right. So my question is, okay, when you allocate your resource to different places, are you at the same time choosing the user? For example, okay, in your second scenario, you will choose some users who has already got very bad experience. You will just ignore them and choose to improve someone, in fact, has much better performance, right? And also for the first case, I think that is also, we have diversity of the users. You are choosing, who you seems like the majority, but just to give the minority even worse experience? Right, that's my question. Thank you.
Oh, so that's a great question. I think there's, I mean, first of all, at a very high level, there is always this tension when the system research, I mean, very high level, if the system research start to tap into user cognition or perception, there's always a question, how do you really know what they want, right? And how to account for the differences across users. And least is this is a monster question of network neutrality when you allocate resources across users, how do you make sure this is also fair and efficient? So to answer the first question, the second project here does in theory have a possibility of deliberately delaying users who don't really care about the delay anymore a little bit in order to improve the user experience of users who do care about the system optimization. So our argument is not that we say this is actually fair, but this is not I mean, from a resource allocation perspective, this is less fair if you really care about the delay itself, the delay per se. Okay? But what we do find was if you do this optimization, okay, the fairness across users' experience, right? So the y-axis, which is a non-linear function of delay, will actually become fairer. Okay. The idea behind this is you're actually making everyone to the left, okay, in a way that you optimizes the y-axis values. There's a pretty complex math proof behind it, but the idea is if you really talk about the QoE fairness, right, the user experience fairness, it's actually become fairer and fairer because you're not really, I mean, we don't really care about the delay fairness. We care about the y-axis, the fairness in terms of the perception of these users. Okay. So again, it's not a perfect answer. Like I said, it's always a bit tricky to tap into this, and it depends on how you define the problem.
Okay, thank you very much.
Okay, next, Yongchang, you want to ask a question?
Yeah, thank you very much, Juncheng. Can you hear me?
Yeah.
Okay. I like the idea of Sensei, and yeah, very impressive. And I'm just curious, what kind of generality can this approach provide? For example, for different type of the video spots or music or some entertainment or the soccer, and for different type of audience, for example, elderly, minority, that is actually related to what Cheng just asked. So I'm just wondering whether your scheme can work out one fits all solution, or which finally result in some customized one to adapt for different needs and different type of content.
It's a good question. So of course, if you're trying to do per content optimization, there's always a question whether this is applicable to other videos. How do you apply to other videos that are not covered here yet? So in fact, the argument of the Sensei paper is that first of all, there are traditional video streaming protocols are trying to be more generalizable. They try to apply the same heuristic across all the video genres. Right? And so the idea of the argument of Sensei is against it actually. It's trying to say, well, you can't really apply these simple heuristic to all videos. Okay, and because these videos actually have very content-dependent sensitivity, variability within them. Okay, so the starting position of Sensei is that it's kind of against being very too general purpose across the board. Now, at the end of my talk, that part of the talk, I did mention there is a potential to make it more generalizable, which is if you look at the vision community, right? So if you think about more complex vision-based models, these models are actually trying to do similar things that the Sensei tried to do, but with a much general purpose solution, generic solution, which is they feed the video into a model and try to understand which part of the video is so-called a highlight, or so-called, I mean, they use this to, for example, generate some GIF, so summarizing video of a long video. So they do have techniques to try to identify where are the key moments. So potentially those techniques could be a approach to a better generalizable solution that has the benefit of Sensei.
Yeah, thank you very much.
Thank you.
Okay, great. Thank you, Juncheng. Actually, Juncheng is one of the, I would say, one of the cleverest research I know. Okay, so for those students who online, if you want to find a clever and energetic advisor, Junchen may be a good option. You send an email to. Okay, thank you, Junchen.
Thanks. All right, stop sharing.
Yeah. Let's move on to the next one. Next one. Okay. Our next speaker is Bojie Li. Bojie is now a senior engineer with computer network and protocol labs in Huawei 2012 labs. He is currently working on the next generation data center interconnects. Dr. Li received his PhD degree in 2019 from the Jordan program from USTC and Microsoft Research Asia. And during his PhD time and after his graduation, he has published many papers on like top tier conference like SIGCOMM, NSDI, SOSP, PLDI. And he also received the 2019 ACM China doctorate dissertation award. Okay, today Bojie will be talking about when in-network processing meet distributed systems. Okay, let's welcome Bojie, please.
Hello, can you hear me?
Yeah, we can hear you, but I cannot see you.
Really? Cannot see me?
Yeah, I can see you now. Yeah.
Okay. Thank you. Thank you, Dr. Kai Chen, for the introduction. Good morning, ladies and gentlemen. And my talk today is when in-network processing meets distributed systems. Actually, distributed systems and network co-design is is a popular topic in recent years. This talk will consist of 3 parts. First, we will briefly review several related works in the network and system co-design. And second, we will introduce our SIGCOMM work in this year. And finally, we will propose several open questions in this area. So let's begin with the first part. Distributed systems are actually traditionally designed. Sorry. Let me see what happens. Okay, sorry. Distributed systems are actually traditionally designed independently from the underlying network. So it makes the worst case assumptions about its behavior. Such an approach is well suited for the internet, which is basically unreliable, has high packet loss rate, has high delay, and lower bandwidth, and also the network switches are not controllable. However, in the data center network, our data center network is mostly reliable and has low packet loss rate and low delay and very high bandwidth. So it's much different. We argue that in this data center network environments, it is possible to co-design the distributed systems with their network layer. And doing so, we can offer substantial benefits. So the largest difference between data center networking and traditional distributed systems is the latency. The data center networking has microsecond scale I/O latency. A natural question to ask is why we need microsecond scale latency. Some people may say that humans can only perceive tens of milliseconds of latency. So why do we bother with microsecond scale? So this is because many data center applications are actually consumed by other computing systems. For example, some high-frequency trading programs are actually competing speed with other high-frequency trading programs. And for microservices and high-performance computing, AI and big data applications, there are actually many iterations of communication and computation in a distributed system. So the latency inside the data center is actually very important. To minimize the latency of the data center networking applications, there have been very extensive research in network and system co-design. We know that the mainly two network devices in the data center are the SmartNIC and the programmable switch. A SmartNIC is actually similar to a switch because it interconnects many components inside the host including many devices, many virtual machines, and many applications. And the programmable switch is actually on the top of rack, and it connects multiple hosts or other switches. So many of the workloads can be either done on the CPU or offloaded to the smart NIC or offloaded to a programmable switch. Each of these means has pros and cons. So for example, here is a lot of workloads, and congestion control and the load balancer are the traditional workloads and networking workloads. And for the distributed applications, this is the topic of our task of our talk, such as key value stores, aggregation, log, coordination, and replication. This kind of thing can both be offloaded on smart NIC or programmable switch. So the fundamental problem to achieve fault tolerance of the distributed applications is actually the state machine replication problem. So if our application, we want to achieve fault tolerance, we want to say this is a state machine. And actually, the replicated state machines are typically implemented using a replicated log. And each log contains the same commands in the same order, so that each state machine can process the same sequence of commands. So they are executing the same program. Because each state machine, actually the application, we require them to be deterministic. So each computes the same state and the same sequence of outputs. However, this is this simple approach, and a classical approach has its performance problem, because any single read operation needs to perform an RPC to the remote machine, to the multiple servers, and wait for a quorum of responses, wait for a large portion of responses to come back. So this is a very costly remote operation. So in the next, we will outline several works which uses either standard RDMA or host smart NIC offloading or network switches to achieve faster coordination. So the first work we want to introduce is Directro. It is published on Transaction of the Computer Systems 2019. It actually uses the standard RDMA NICs to achieve faster state machine replication. So different from the traditional Paxos way, in the Directro, the leader only coordinates membership changes and the system restarts. The Directro applications are stored data in replicated version vectors. The versions are actually passed through a series of stages. This is different from the traditional Paxos way. First, they are created, which is marked as red, and then it is logged locally. When it's logged on the local durable storage, it is marked as orange, and then it becomes stable. The stable state are actually distinguished between basic Paxos durability, which is all the green versions, and there is some temporal stability, which is called darker green. So this is temporary, and this is global stable, which is lighter green. So this is the basic idea of the Directro. And it has an additional guarantee that no update with an earlier real-time timestamp would occur. So this is how it tracks the state of the system through the all-to-all information exchanges. And this is quite a theoretical paper. So if you are interested in the details, you can consult with the paper. And here is another optimization in Directro's RDMA multicast protocol. It breaks the large messages into chunks, and they focus them. They forward them trunk by trunk over a network overlay of reliable FIFO channels. The left diagrams illustrate a binomial copying protocol, which processes represented by circles, and the data transfer steps are represented by the numbered arrows. The middle and right diagrams illustrate the idea of running three binomial protocols simultaneously on a three-dimensional hypercube. So the hypercube is created as an overlay within the RDMA network. When the pipeline is fully active, every node has one block to send and one block to receive at each logical timestamp. And the second paper we survey is much different from the first paper. The Directro proposed a new algorithm that runs in software and utilizes standard RDMA. But consensus in a box, this is an NSDI paper. is a hardware implementation of Zookeeper protocol. This is also a traditional replication protocol in an FPGA-based SmartNICs. We can see that the latency of FPGA is 2 orders of magnitude lower than the TCP/IP counterpart. Both the retro and consensus in a box, both two solutions have microsecond scale latency. But we will need to, when we look at the performance of research papers, for example, comparing the performance of the SmartNIC approach with the standard software-based approaches, we need to take care that we do not want to compare against this standard software. Because they are not well optimized. For example, if we just simply replace the kernel-based TCP/IP stack by RDMA of the Zookeeper or etcd, maybe their performance will be improved very greatly, but no paper has been evaluating these effects. So there has been a very interesting paper in Hot OS called Scalability, but at what cost? This paper actually compares several state-of-the-art scalable graph processing systems with a single-threaded implementation. And it finds that a system with hundreds of cores simply underperform one thread. So this is this cost paper actually indicates that when we compare performance, the baseline should not be very low. So we should be cautious on the performance comparisons. Okay, let's go back to the programmable switches. We know that a programmable switch has a programmable parser, which can parse custom key-value fields in the packets. And it also has a programmable match action engine to read and update key-value data as line rate. So the programmable switch has a higher processing capability, but it has a relatively low memory capacity and relatively low programmability. So this has pros and cons with servers. There has been a lot of work doing this. For example, NetChain saves the coordination states inside the network switches. A problem is if the switch fails, then the coordination switch also disappears. So we need multiple replicas to save the states. In NetChain, the storage nodes are organized in a chain structure. The read operations are directly handled from the tail of the chain, and the write applications are first handled by the head of chain, then replicated from the head to the tail. So this is a normal case behavior that processes read and write operations line rate. When some switch fails or we need to add a new switch, the network controller needs to handle the reconfigurations. So this separation of normal case and abnormal case is a common principle in network and system co-design. And we will see this principle repeatedly later in this talk. The next work we want to introduce is NoPaxos, which implements the Paxos consensus algorithm in the programmable switches. The programmable switch actually acts as a sequencer to determine the order of messages and multicast the messages to all the receivers. So during the normal operation, the receivers do not need any coordination, and the operation is completed within one RTT. It's very simple. But when a message is dropped, the receiver can detect the dropped message according to the gap in the sequence numbers. So when a message drop is detected, the replicas will run a traditional Paxos agreement algorithm. And then last related work we want to discuss is ARIS. It is published in SOSP. It proposes a new way to divide the responsibilities for different guarantees. In the ARIS work, an independent transaction actually involves multiple shards, and each shard has multiple replicas. So each packet in a transaction would be multicast to different sets of replicas. So it just multicast the message from the client to all the replicas of all the related shards. This is how it works. So how does it ensure the ordering of the shards? This is because using the programmable switch as a sequencer. Different from the NoPaxos paper, because each transaction in the ARIS paper only involves a portion of shards. So broadcasting each message to all the shards will be very wasteful. To this end, ARIS paper specifies a set of destination replica groups. So each replica group represents a shard, and the programmable switch is the sequencer it keeps the counter for each replica group. We can see A2, B3, and C2 here. And when the replica detect the gap in the sequence number, we can also find it on the figure that the replica knows that B1 and B3 has a gap in the sequence number, so there is a lost message. And the failure coordinator will use a traditional consensus algorithm to achieve consensus among the replicas. And now let's move to our paper. We know that ARIS is a very great work. It achieves total order communication with a centralized sequencer, but it is not scalable because all traffic must pass through the centralized sequencer. So we think about this problem and design one pipe, a scalable total order communication abstraction in data center networks. The first thing we want to define is what kind of ordering we want to provide in the distributed system. There are two kinds of ordering anomalies or ordering hazards in a distributed system. The first kind of ordering anomaly violates the causal ordering. For example, host A writes something to the O, and then A sends a message to notify B. Then after B receives the notification, it reads from O, but it may not get the data due to the delay of A's write operation. And the second kind of problem violates total ordering on atomicity. So the first A first writes both data and the metadata to two objects, and then simultaneously B reads metadata and data from the two objects. And it is possible that B reads metadata from A, but the data is not updated yet. So this is called isolation among concurrent transactions. It is also possible that only one of the two operations succeed and the other fail. So the metadata and data will be inconsistent. This is called failure atomicity. So to avoid these two kinds of ordering anomalies, we propose a one big pipe abstraction in which messages are sent in groups called scatterings. This is called scattering, and this is scattering. We can see that this is from one sender to two receivers, and this is from one sender to two receivers. And each scattering is serialized in a virtual pipe. Different receivers actually deliver messages in a consistent order, as if the scatterings are pulled out from the pipe and delivered to the sequencers atomically and sequentially. So this is the basic abstraction of us. Informally, the one pipe abstraction is causally and totally ordered communication support called CATCOX. So it involves total order and causal order and atomicity. This is similar to the introduction we have seen, motivation we have seen before. And we must make it clear that one pipe, it already says that full failure atomicity is impossible. So let's take this figure as an example. If receiver 1 can fail permanently at any time, how can receiver 2 knows whether or not it has delivered the message M or not? So this is very hard to know. Actually, it's impossible. Traditional approach of existing fault-tolerant systems actually use replication. And one possible way is actually to use, for example, like NetChain to replicate every message. But we are different from NetChain because it only focuses on important states that it needs to be replicated. But we are offering a basic communication primitive. If every message is replicated, then the overhead will be very high. So we apply the design principle of optimizing for the normal case because the data center is mostly reliable. And we will have a mechanism to invoke the application to handle the failures. Now we consider the core design of one pipe, how to achieve the total ordering. We introduce our first strawman. The first strawman is the approach of ARIS. We have talked about this approach before. This is exactly the same. The major problem is that the switch becomes a centralized bottleneck. And the second strawman is a classical algorithm called vector timestamp. So each sender has an increasing logical timestamp, And each message is broadcasted to all the receivers, regardless of the actual destination of the message. So it is all-to-all communication. And each receiver will maintain a vector of received timestamps from the senders. So this is why this algorithm is called a vector timestamp. Then the critical step is that the receivers exchange the vector timestamps among each other. When one receiver knows that all receivers has received some message, this is computed by computing the minimum of received timestamp. It can safely deliver the message. So there are two drawbacks of this approach. First, the receivers must use one all-to-all communication among the receivers. And second, each message is broadcast to all the receivers. So we want to improve, and we come to the third drawback, which is much closer to our final design. We will synchronize the physical time on the senders, and the messages are attached with physical timestamps. We can see the physical times. When the receiver receives the message, it will first put the message into a receive buffer. Here is a receive buffer. And similar to a vector timestamp, the receiver will maintain a timestamp for each sender, and it computes the minimum timestamp of all the senders. For example, the minimum timestamp of these three are the 9 o'clock. So the minimum timestamp, if it's greater or equal to the timestamp of some message, then the message is delivered. So the two messages with timestamp 9 o'clock will be delivered. But here, because we do not know any message from this, so we cannot deliver any message. So sorry, we have an error in this figure. It should be 0 o'clock in the black one. And this approach also has several drawbacks. First, each message needs to broadcast to all the receivers, including those not needed. And the second drawback is that there needs periodic beacons for an idle pair of receivers. Otherwise, if it does not send to the receiver, it cannot know the sender's time, and it will block all the receivers forever. And furthermore, it cannot detect the packet loss and failures. So let's come to our design. Before introducing our design, we will first introduce the data center topology. A data center typically has a multi-rooted tree topology, and we expand the tree topology to a directed acyclic graph. The routing graph between a sender and receiver is a DAG. In this DAG, each switch and the host actually has two rows, and the dashed arrows actually indicate a loopback on the network switch. The dashed arrows are here. These are the two identical switches, actually one for the uplink and one for the downlink. In this deck, we will consider how to aggregate timestamp barriers. The key design of one pipe is similar to the last drawback. We first consider the case with one switch and then extended to multiple switches. It synchronizes the physical clock on the senders and aggregates the minimum timestamp on the receivers. And in the last drawback, each sender needs to send beacon to each receiver. And to solve this scalability problem, we use the programmable switch to aggregate the minimum timestamp of senders and broadcast the minimum timestamp to all the receivers. So each packet has two timestamps, one message timestamp and a barrier timestamp. These are two timestamps. The message timestamp does not change during the forwarding, and the barrier timestamp is changed during the forwarding. When a switch or host receives the packet with some barrier timestamp from a network link, it indicates that the message timestamp and barrier timestamp will, of all the future arrived packets from this link, will be larger than the barrier timestamp. So this is the barrier property. And let's consider a DAG of distributed network switches. We can hierarchically aggregate the barrier timestamps through layers of switches, hop by hop. For example, the switch 1A computes the minimum barrier of sender 1 and sender 2, and broadcasts the minimum barrier to switch 1B and switch 2B. And switch 1B and 2B also receives the minimum barrier from sender 3 and 4. So it gets the barrier from all the 4 senders. In this way, each receiver will get the barrier of all the reachable hosts and links in the network. And we recall the barrier property, and the receiver will deliver the message in the receive buffer when it receives the barrier stamp higher or equal to the barrier message timestamp. Finally, if some network links are idle, so beacons are sent periodically on each idle link to prevent it from storing the entire network. Okay, this is how basic one pipe works. And now let's consider packet losses. For example, the packet from sender 2 to receiver A with timestamp 8 o'clock is lost. Receiver A should deliver 10 o'clock after delivering this packet, but because the packet is lost, the switch and the receiver A does not know that timestamp 8 o'clock has lost. So this violates the out of order packet. Unlike a centralized sequencer, the receivers do not know whether or not the packet message is lost. A straightforward solution is to add hop-to-hop sequence number to detect packet loss. However, it is not capable for many kind of switches. So we will introduce a more complicated solution. And this complicated solution will actually introduce an extra RTT. So we will provide two kinds of services. One kind of service provides the best effort service that provides at most once delivery. And we will provide a reliable service that provides exactly once delivery that recovers lost packets and handles failures. So the reason why we need the best effort service is that because some use cases of one pipe only need ordering but do not need reliability. For example, a read-only transaction can only be safely retried if someone's messages are lost. So to achieve this reliability, one pipe has one round trip of prepare phase. The sender first sends a message to the receiver, and the prepare message contains a message timestamp, which is the wall clock time of the sender. And the receiver puts the message into the receive buffer, and then the receiver responds with an egg. And when the sender collects all eggs equal or below to some timestamp, it will send a commit timestamp message to the neighbor switch. And the commit message means to deliver all messages below or equal to the commit timestamp. And the commit timestamp will be aggregated by the switches, similar to in the best effort approach. And now let's see how reliable one pipe handles packet losses. In the first example, we assume that the egg packet is lost. And after the sender will detect the lost packet through end-to-end mechanism, either via timeout or duplicate ACK. And after retransmitting the prepare message, the sender can finally send out the commit message. And in the second example, we assume that the commit message is lost. Actually, it is easier to handle because the commit message is monotonic. Committing the timestamp 10 o'clock is equivalent to committing the message at 9 o'clock. So even if there are no other messages to commit, we will have periodic beacons on each network link, and it will be automatically retransmitting the commit timestamp. And now let's go to the packet loss. After handling the packet loss, now we come to the failure recovery of hosts and switches. Actually, this is a actually very complicated part, and I will go through it very briefly. The first, the failures will be detected via beacon timeout and reported to the controller. And then the controller will determine the failure process and which time the process fails. And then it broadcasts the failure notification. And then each of the process will discard the messages sent to from the message in the send or receive buffer. And if the discarded message is within the scattering, it needs to recall other messages in the scattering to achieve atomicity. And finally, each process will execute a user-defined callback function. For example, a traditional consensus function to synchronize the replicas. And finally, the controller will resume the commit timestamp propagation, and the failure recovery is ended. And if there are multiple simultaneous failures, the recovery is more complicated. The key idea is that the controller needs to determine which components have failed and when each component fails. The former question is easy to answer, but the latter question, when each component fails, is hard to answer, because the failure timestamp of a component determines which messages should be delivered for the scattering sent to or from the failed component. So it needs to be carefully determined. And we have a principle that the failure timestamp of a process is a commit timestamp actually sent by some process, but it has not propagated to any receiver. This is to ensure that no messages after this timestamp has been delivered, and all the messages have been buffered in their receivers accordingly. So this, I will skip the details of the protocol. And we must notice that the failure recovery has its limitations. If the receiver A crashes at some unknown time, so we do not know the last timestamp A has delivered. So the other receiver B at the same time scattering does not know whether A has delivered this timestamp 9 o'clock. So the controller, we can only ensure atomicity in the failure recovery model. That is, when receiver A recovers from the failure, it communicates with the controller to determine which messages the receive buffer should be delivered. But if it never recovers, that is, fails permanently, we cannot ensure the atomicity. Now we come to the implementation on the host. On hosts, one pipe is implemented using RDMA unreliable datagram. Actually, this is because if we use RDMA RC, each QP will buffer several messages, and we cannot ensure the ordering among these messages on the network link. Ideally, we would like to use a smart NIC, but we do not have access to such a smart NIC, so we use a software-based approach. One pipe also has a pooling thread per host to synchronize the time and generate periodic beacons. And now we come to the implementation on network switches. We consider 3 types of network switches with a different programmability. Using a programmable switch, the switch data plane can aggregate the barrier timestamps. And using a commodity switch without a programmable switching chip, for example, a Broadcom switching chips, we can actually implement the in-network processing on the switch CPU. It is also possible. And even if the switch vendor does not impose access interfaces to the switch CPUs, we can also offload the beacon processing to the end hosts. We will skip this. And the evaluation part, we will use 32 servers and 10 switches and to form a 3-layer fat tree topology. And we compare one pipe with other total order broadcast algorithms. So one pipe scales linearly with 500 processes, achieving 5 million messages per second per process, which is 80 million messages per second per host. And the throughput of one pipe is limited by CPU processing and RDMA messaging rate. And reliable one pipe has 1/4 lower throughput than best efforts because of this 2-phase commit overhead. In contrast, if we use the switch or host as a sequencer, the sequencer will be a centralized bottleneck. And the CPU overhead of one pipe has 2 parts: ordering at the receivers and beacon processing at the switches. We can see that the processing overhead is quite low. We can see more details in the final paper. And now we come to the case study. The first case study is a transactional value store. For the read-only transactions, we can use best effort one pipe because it does not have any side effect. If any of the read requests fails, the client can simply retry the request. This is why we designed the best effort one pipe. And the transactions, including at least the write operation, needs to use reliable one pipe to ensure atomicity. In normal cases, the transaction will be completed in 1 round trip. And the second case is log replication. Traditionally, we have 2 ways for log replication. It's a leader-follower approach and the sequencer-based approach. Both methods will need 2 RTTs. And using one pipe, log replication can be achieved with only 1 RTT. This is because one pipe removes the need of sequencer in the traditional approach. We use best effort one pipe to achieve the minimum latency and let the sender to detect the packet loss. Here is how we do. Each replica maintains a checksum, which is the sum of all timestamps the replica has received. If the checksum matches, then all replicas have received the log entry in a consistent order. If the checksum do not match, then at least one log entry is lost, and we rely on the log generator to recover it. The last case study is independent transactions. This is similar to the areas we have just discussed before. And we will benchmark the new order and payment transactions in the TPCC benchmark. And we can see that the two-phase logging and the OCC do not scale, but our scheme can scale with the number of processes. And also we can see on the right figure that the performance on the packet loss is good. Finally, we will discuss some limitations of one pipe. Actually, CoNEXT is a very age-old controversial topic. There has been a very famous paper understanding the limitation of CoNEXT. It says it cannot say for sure, cannot say together, and cannot say efficiently. And actually, for the first thing, one pipe is not a panacea. And for the second thing, we provide some scattering primitive and restricted failure atomicity. And for the third thing, one pipe has low latency, high throughput, and low overhead. And there are some limitations of one pipe. It cannot achieve atomicity and require hosts to synchronize clocks, and a straggler host will slow down the entire network, and is also not very secure. So this is the conclusion of one pipe. And finally, we will propose two open questions. We have heterogeneous data access methods. For example, we have load store, read-write, switch offloading, semantic offloading, and RPC on the CPU. Traditionally, the only way to access remote data is by executing the RPC on the remote CPU. Then we have RDMA technology. And then if the data structure is complicated, we may need multiple network round trips to RDMA the data. But because it removes the cost to invoke an RPC on the remote CPU, it is mainly the TCP/IP and RPC protocol stack. The overall performance may be still higher. Then we have semantic offloading and in-network computation. And in summary, we have a wide spectrum of data access methods, and we will need some way to choose among them. This is an open question. And the second is traditionally OS and hardware mechanisms are designed for the millisecond scale I/O mechanism. For example, networking and storage. But RDMA and flash devices now we have now are in the microsecond scale range. So RPC protocol contributes a large portion of latency, and it's very hard to offload. Serialization and deserialization is language dependent. And many RDMA applications use polling mode because the interrupt mode has too much latency overhead. So can we dynamically switch between polling and interrupt mode? This is a question. And finally, we have distributed applications in the big memory era because we have tiered storage such as DDR storage, class memory, flash, and remote memory, which may be faster than flash. And distributed applications need a big memory abstraction consisting of tiered storage. The hot and cold data needs placement and migration. If the data is migratable among the hosts, how to address the memory object, and how to replicate the memory objects or make them durable. This is a question. And also how to migrate the data between the DDR and the flash, and to avoid the memory pinning of RDMA is also a kind of a problem. Actually, we should consider, should the swap in or swap out be fully controlled by the OS software, or we use a software and hardware co-design? These are some open questions in our distributed applications. Okay, thank you. Finally, the simple ad. Welcome to the Computer Network and Protocol Lab in Huawei. Thank you.
Thank you, Bojie. Yeah, so now we have questions from the audience. Yeah, go ahead.
Okay, is it me?
Yeah.
Can I ask a question? Okay, so Bojie, very good talk. So every time we can get quite a lot of insights from your talk. Okay, so my question is, okay, now the idea is to combine the networking and the computing, right? So my question is, so far we have quite a lot of discussion on how to abstract the switch as well as SmartNIC to provide programmability. But most of them now are mainly based on the networking idea, or not too much or not sufficient support for adding more computation capacity in the networking device. So what is your suggestion, or what do you see in the future how we would involve the programmability abstraction, especially for your talk, right, to add this function into the switch? Did you meet any difficulties to enable your idea? Yeah.
Yeah, thank you. This is a very good question. Actually, when we were designing the one pipe in the switch, we actually meet some difficulties because the number of pipeline stages is a quite limited resource. And for example, we have 32 ports, and we need a binary tree to combine them, and we need several multiple stages. This is only one problem. And actually, when we are doing research on some congestion control mechanisms, we want to evaluate some function and then put the result back into the register, and we will find that the combinational logic cannot be very efficiently expressed inside the programmable switch using the P4 Tofino and logic. So there have been a lot of things that we need to the programmable switch can improve. And actually, I think that the programmable switch and the SmartNIC needs to have a very good split of work because the switch has a high throughput, but it has low programmability. Relatively low programmability, and it has relatively low buffer size compared to the high bandwidth it has had to handle. And the SmartNIC also has low buffer size, but the buffer size is a bit larger than the switch. And many SmartNICs are now equipped with DRAMs, so it can buffer more packets. And it has higher parallelism because it has multiple cores inside it. And but the SmartNIC, there is another benefit of SmartNIC is because it has a tight integration with the CPU, because it can access the CPU memory directly via PCIe, or in the future, maybe it via more tightly integrated CXL or Gen Z kind of interconnects. And the programmable switch, actually, I expected it to evolve to have more powerful CPU on that, because whenever we want to do some switch processing, it also needs some control plane processing. And the control plane on the commodity switches only have very weak CPUs. So if we have a strong CPU to connect them together, for example, using the Microsoft Sonic approach, that would be very, very interesting.
Okay, a follow-up question. So yeah, I think it would be relatively easy to upgrade the CPU in switch. Right? You don't need to change fundamentally for the switch architecture. But do you see any needs to change totally the architecture, for example, to add like programmable processors like GPU, FPGA, or other kind of heterogeneous processors there?
Yeah, thank you for this question. Actually, in my point of view, I think maybe in a programmable switch inside the data centers, we want to actually reduce some functionality inside the programmable switch. That's my point of view, because the switch needs to forward the packets as fast as possible. And in the future, in the data center, we will have a memory fabric. By memory fabric, we means that tens of thousands of hosts are interconnected, and we will have memory semantics. For example, load and store or read and write this memory through the memory mapped interfaces, and the latency should be as low as possible. For example, 1 microsecond for 3 hops of network switches. So in order to achieve this, the switch must be very simple, and the forwarding tables must be compressed. I think we do not need to sacrifice the programmability, but we can have some means to, for example, compress the tables or have more tightly integrated programming pipeline to make the forwarding latency of the switches as low as possible. For example, reducing from 500 nanoseconds to 100 or 200 nanoseconds. That would be very interesting for future distributed systems.
Okay. Yeah, I have to cut off. So we're running out of time. So yeah, very nice talk. Thank you, Boje. Okay.
Thank you, Dr. Chai.
Yeah, if you audience have questions, you can talk to Boje online later. Okay, so that's the end for this session. And because we're running out of time, maybe we have a short 3-minute break before we enter the next session. Okay, thank you.
Thank you. So we now have a break, and please come back at 11:28 or 11:29. Thank you.
Hi, Dong-Soo.
Hi, KK.
I'm glad you're here. Do you have any information about the
speakers?
Yeah.
Yeah, I do have all the bios from all the speakers.
Great, thank you.
Okay, welcome back. So I will now hand the microphone to Professor Han for the next session.
Okay, thank you. So welcome to the first regular paper session of APNet 2021. So we'll have 3 papers in network measurement and congestion control. The first paper is titled A Sketch Algorithm to Monitor High Packet Delay in Network Traffic. And this will be presented by Jiaqi Zhu. He's an undergrad student majoring in computer science at Peking University. He's also advised by Professor Kun Huang, and his research interests include computer networks and network measurement. Okay, so let's welcome Jiaqi.
Okay, so could you hear me?
Yes, please go ahead.
Okay, thanks for the introduction. And today is my pleasure here to present our work about a sketch algorithm to monitor high packet delay in network traffic. So as we all know, network measurement provides critical information for network management. And there are many network traffic such as heavy hitter, heavy changer, super spreader, and packet delay. So in this paper, we aim at the measurement of packet delay, and we think that which is an important indicator of the network health. And typically, we focus on intraflow packet delay, which is called IFPD for short. And it is the time span between the two adjacent packets of one flow. And we think that the measurement of IFPD is helpful to monitor network health. So although there are some related works in the measurement of packet delay, however, these works are based on sampling or injecting probe packets, and they cannot give the measurement of every IFPD in detail. So in our work, we proposed a sketch-based approach to detect high IFPD packets, and our algorithm has high accuracy with low space usage. The experiments on the real-world trace show that our algorithm has high performance. And next, let's move on to the formulas of our problem. The first thing we want to know is that what is IFPD? So we can assume a situation that all packets arrive at the network device in a chronological order, and each packet has a flow key and a timestamp to indicate its arrival time. And since that all the packets which has the same flow key consist of a flow, therefore we can represent a flow X with k packets as Fx equals xt1, xt2 to xtk, where the x is the flow key of a packet and the t is the timestamp of its arrival time. And therefore, for a flow x, the intraflow packet delay of the S packet is dix equals ti minus ti minus 1, and it is the time span between two adjacent packets of one flow. And here we can take an example of IFPD. So now we can see here that there are some packets, and each packet has a timestamp and a flow key. And those packets consist of three flows, fx1, fx2, and fx3. So therefore, for the packets in each flow, we can compute its IFPD. And for example, the d2x1 equals 4, which is 7 minus 3. And the d3x1 equals 13, which is 12, which is 20 minus 7. So since we have already formulated IFPD, and our goal is detecting high IFPD in network, it means that given a threshold seed, our primary goal is to report all packets whose IFPD exceeds seed. However, since that the accurate algorithm consumes too much resources and it is hard to be applied in the hardware such as switch, therefore, we will use approximation algorithms to detect high IFPD. And therefore, we want our algorithm to have high accuracy and low resource usage. And in order to solve our problem, we follow that line of the sketch-based algorithms. So sketch is a family of data structures which comprising of multiple buckets. The sketch can make a trade-off between accuracy and measurement by allowing each bucket to accommodate multiple flows. And they use independent hash functions to mitigate the errors. Sketch algorithms are widely used in network measurement, such as flow size estimation and heavy hitter detection. So here we can introduce count-mean sketch as an example. The count-mean sketch can be considered as a two-dimensional D times W array of buckets with D independent hash functions. And the CM sketch is traditionally used in flow size estimation. So here is an example of the CM sketch used in the flow size estimation. And in this situation, each bucket of the count-mean sketch, which is CM sketch, stores a counter, and this counter is initially zero. The count-mean sketch has two operations, update and query. For example, if each packet comes, then the CM sketch will do its update operation. And this example is a packet of flow X with size S comes. So for the CM sketch, the update operation is that the sketch will hash the flow key X into one of the W buckets each row, and then it will increase the counter of those buckets by the packet size S. And after all the update operation, if we want to query the size of a flow X, then we just hash the flow key X into one of the W buckets each row, as we mentioned above. And to query the size of flow X, we use the minimum counter value of those buckets as an estimation of the flow size. So we can apply count-mean sketch to detect high IFPD packets. And in this situation, each bucket stores a time step instead of a counter. The time step is different from counter because the time step is non-adaptive. And if the packet X T current comes, we will hash it into one of the W buckets each row. So to estimate the IFPD, we first choose the minimum time step from all the hash buckets, and we take it as the estimation of the time when the previous packet of flow X arrived. Then we can estimate the IFPD as T current minus T previous. And after we compute the IFPD, we will update those buckets with the time step T current. However, we found that this algorithm has some limitations in high IFPD detection, and it cannot observe good results. First, we find that it cannot accurately distinguish whether a packet is the initial packet of a flow. So although we set all the packets initially zero, it can be easily flashed due to hash conflicts. And in this figure, we can find that more than 40% of the first packets are missed. And another limitation is that high IFPD packets are hardly detected. That is because during the interval from T previous to T current, the T previous stored in the buckets can be replaced due to hash conflicts. And in this figure, we can find that the recall of the reported high IFPD packets gradually decrease as the threshold increase. So that can show us that this algorithm cannot detect high IFPD packets. Therefore, our key issue is to deal with the hash conflicts for time step. And since the time step is non-adaptive, detecting high IFPD is more difficult than the traditional network measurement problem. So in this paper, we use 3 methods to address this issue. And the first method is that we use a fingerprint-based approach to detect high conflicts. That means that we assume a fingerprint to each row. And our sketch is different from the same sketch is that our the bucket of our sketch has 2 fields. And the one field is for a fingerprint, and the other field is stores a time step. And our second method is a conservative update method that we only update one of the D hash buckets each time. And this idea can help to keep the time step of potential high IFPD flows. We can look at the following figure. And the yellow block represents a time step of another flow, which is different from the common packet. So if we update all the hash buckets, then the yellow block will be replaced by the blue block, which means the timestamp of the yellow block is lost. However, if we use conservative update method and we use a naive method that we randomly update one bucket, then maybe the yellow bucket will not be replaced by the blue block. That means that the timestamp stored in the yellow block will be kept. And our third idea is a replacement strategy. Its idea is trying to maintain the timestamp of potential high IFTD flows, and we will introduce it in detail later. So now let's look into our algorithm in detail. And for each commune packet, we will first compute a fingerprint of it based on its flow key X. Then, just like the counting sketch, we hash the flow key into one of the W buckets each row. And our update method has 3 cases based on the fingerprint of the buckets. The first case is that if a bucket stores the same fingerprint as FPX. And in this situation, we consider that this bucket stores the timestamp of the flow X because they are hashed into the same buckets and they have the same fingerprints. So we just compute IFTD as T current minus the timestamp stored in that bucket. And then we update the timestamp in bucket by T current. So here is an example. The packet X25 is coming and its fingerprint is 2. Then we can find that the fingerprint is equal to the bucket in row sign column 1. So we compute the IFTD as 25 minus 12 as 13 and update that bucket with 25. And the second case is that if we find an empty bucket, in this time, we consider this packet as the first packet of flow X. And so we compute its IFTD as 0, since it is the first packet of a flow. And after computing the IFTD, we will insert it into the empty bucket. And the third case, which is a little complex, is that if all of the D-hash buckets has stored fingerprints, while none of them stores FPX, then in this situation, we will find the bucket which stores the largest timestamp among those D-hash buckets. And that is because we want to keep the buckets which stores potential high IFTD flows. And high IFTD flow will update slowly. So we think that its timestamp is small in high probability. Therefore, we choose the largest timestamp among those D buckets in order to keep those potential high IFTD packets. And then after we choose a bucket, we can compute its IFTD as T current minus the timestamp of those buckets in that bucket. And we update that bucket with the flow key X and the fingerprint FPX and the timestamp T current. Here is an example. Here is an example that the commune packet is X25 and its fingerprint is 6. We can find that none of the hash buckets match the incoming packet by fingerprint, and all those buckets are occupied. So we choose the bucket in row 1, column 2, because it has the largest timestamp among those 3 hash buckets. So we compute IFTD as 25 minus 20 equals 5, and we update that bucket. And that's all for our algorithm. Next comes to the experiment part, and we test our method based on the public network traffic from CADA, and we divide each trace into segments of 2 seconds, and each segment has 1 million packets. Then we use 2 baselines, and the first is the CM sketch, which we mentioned above, and the second is a CMI sketch with a Bloom filter. A Bloom filter is a space-efficient data structure to test whether an element is a member of site. Therefore, by using a Bloom filter, we can detect whether a packet is the first packet of a flow, and that can partially resolve the limitations of a counting sketch. So we use 4 metrics to evaluate the accuracy of high IFTD detection, and the precision indicates the ability of an algorithm to detect high FPD accurately, and the recall indicates the ability of an algorithm to catch the most high FPD packets, and FE soccer is the harmonic mean of the precision and recall. So we first compare the accuracy for high FPD detection with different thresholds. And we can find that the precision of CM is low because it cannot determine whether a packet is the first initial packet. And the precision of CMBF is nearly 100%. That is because the algorithm assures that the estimated FPD of all the packets except the first one are smaller than its accurate value. So that will lead to a nearly 100% precision. However, we find that the recall rate of both CM and CMBF decrease rapidly as the threshold increase. And it implies that those two methods cannot detect high FPD efficiently. And look at our method. Our method has a stable recall rate and precision as the thresholds increase. Besides, our algorithm has lower relative error. And then we set the threshold to 700 milliseconds and compare the accuracy of high FPD detection with different memory use. The precision and recall rate increase as the memory use increase, and because when the memory increase, the hash conflict is decreased, and we can mitigate it by increase the memory use. And the experiment shows that our method has higher FE score and lower relative error. And with 600 kilobits memory use, our methods can achieve precision and recall rate of nearly 99%. In fact, if we use a hash map to calculate FPD accurately, it will cost at least 2 megabits. So it shows that our method can achieve good performance with low resource usage. And in conclusion, we aim at detecting high FPD packets, and we follow the line of sketch algorithms to solve this problem. However, we find that traditional sketch algorithms has limitations in high FPD detection. So we propose a new sketch algorithm based on 3 ideas. The first is using fingerprints to detect hash conflicts. And the second is a conservative method that updates only 1 bucket each time. And the third is a replacement strategy to keep potential high FPD flows. The evaluation shows that our method has high accuracy with low resource usage. And that's all for my talk. So any questions?
Okay, thank you. We have time for questions. So let me start with my own. So here you focused on measuring the absolute time difference between 2 packets. Have you thought about changing this to measure the relative difference? Maybe you want to identify like top 10%, top 5%, just like heavy hitters is relative.
Yes, and our first work is focused on, and we'll focus on this, and our first work will focus on the mathematical analysis, and we will supply different sets, different thresholds to different flows, or even set the thresholds dynamically. So we will consider of this, but there is one limit of the implement in the hardware is that the program for switch cannot support the device operation. So we are thinking about that.
I see. So does the current code run in a programmable switch?
No, this code run is implied in C++ and it's a software. So we will imply it in the hardware in further work.
Okay. So from this IFPD, how do you detect an anomaly? Like even if you have a very high PD, it could be just that the packet is not generated by the application.
This work is considered in delay sensitive networks, and so that the FPD of each packet should be low under normal circumstances. However, if a network anomaly occurs and a packet arriving at the update switch may be blocked or lost, so that will cause a high FPD. And we consider it in such as a data center network, which is delay sensitive network. And it's your question is it's good, and if maybe some applications they will send some hard ping maybe packets, and that will cause a high FPD. But in our situation, we assume that in normal circumstance the delay is low and it is a delay sensitive network.
Okay, thank you. KK, you can go ahead.
So I don't mean to put this off. I mean, it's a different context for the question I'm asking, which is, there's this whole area of doing in-network telemetry, and especially in data centers where you are so concerned about delay sensitivity. How much better would I be able to do with using INT versus what you're doing? I mean, what you're doing is basically saying, look, I don't need much network support. The question is, what compromise am I making compared to using INT?
I'm sorry that could you explain your question, and I didn't understand it well. So I'm sorry that I didn't understand.
It's okay. Maybe we can take that offline.
Okay.
With you and Chun. Okay.
Okay. Any other questions? Okay, then thank you, Jiaqi, for your presentation. So let's now move on to the second paper of this session. Here we'll talk about hierarchical RDMA congestion control. And the presenter is Zirui Wan. He's a first-year PhD student at Beijing University of Posts and Telecommunications. He's advised by Associate Professor Zhao Zhang. And his research interests include data center networking and transport control protocols. Okay, so please go ahead.
Oh, okay. Can you hear me?
Yes, very good.
Okay, thanks for the introduction. And good morning, everyone. I'm Zirui Wan from the Beijing University of Posts and Telecommunications. And today is my great honor to present our paper, the HICC, the Hierarchical RDMA Congestion Control. And this is a joint work of BUPT and Huawei. And today, the high-performance networking is designed in the data center network, and many new applications such as the cluster-wide storage system, the machine learning system, and the resource disaggregation architectures are being deployed using this network. And correspondingly, all of these new applications need the ultra-low latencies to avoid the performance degradations, such like the cluster-wide storage system need 45 microseconds latency, and the machine learning system need about 30 microseconds to achieve a better performance and transmit the parameters between the servers and the workers. And besides, the resource disaggregations architectures need about 5 microseconds to transmit between the compute transmit between the compute resource and the memory. And thus, the ultra-low latency communication is needed to achieve a better performance. And the data center network is become a bottleneck. When we strive to provide ultra-low latency access, we face some challenges, as we find the throughput-sensitive applications may want the senders to send as many packets as possible, such like the senders may usually send packets using the line rate, and make full use of the switch buffer to achieve the highest throughput. However, this choice may cause a lot of damage to other flows go through this switch. In contrast, the latency-sensitive applications may expect that the senders to send as next min rate, so it will use as fewer buffer as possible. The latency-sensitive packets can experience the minimal queuing delays to achieve the ultra-low latency. However, this choice may sometimes not fully use the network bandwidth, and it may cause the link bandwidth underutilization. So in short, we face a dilemma in balancing the requirements between the throughput-sensitive applications and the ultra-low latency-sensitive applications. And how to effectively use the link bandwidth becomes the challenges in the data center network. In recent years, many solutions have been proposed to solve this dilemma, and there are three main options. First, some reaction congestion control proposals like DCQCN, Timely, and HPCC leverage the congestion signals to detect the congestion happens, but these schemes always react after the congestion happens. And second, in order to make control before the congestion happens, some proactive congestion control mechanisms like the express path, NDP, and HOMA use the credits to schedule packets in the network, but these schemes may meet the first RTT problem. And besides, some centralized control proposals like the FastPass or the FlowTune use the central arbiter to globally schedule packets, and they need one extra RTT to request the credit, so they may also waste the first RTT time. These schemes can reconcile the latency and the throughput to some extent, but however, during our usage, we find them face a dilemma in handling with the traffic uncertainty. And next, we will illustrate the point by conducting two common cases with the uncertainty traffic and find the main problem behind that. In the case one, we conduct a short burst flow scenarios. As the figure shows, we connect the senders and the receivers by two switches, and we maintain two long-lived flows as the background flows. And we add 16 short burst flows to the network after the long-lived flows converge to the ideal rate. And we use the HPCC as the CC solutions. The reactive mechanisms has many drawbacks, such like it usually makes congestion after the congestion happens. And it also needs multiple rounds to converge to the ideal rate. So it can't effectively handle the short burst flows. The following two pictures show the switch queue peaks and the total throughput respectively. We can note that the queue length of the bottleneck link grows up to 350 kilobytes. And the HPCC needs 5 RTT to converge to the ideal rate. When we dive into the throughput changes versus the time, we can divide the whole conversion process into 3 parts during the traffic pattern changes. And first, most existing reactive congestion control mechanisms use the line rate at the initial rate, so they can fully utilize the link bandwidth and achieve high throughput when flows start. Second, when short burst flows start, the existing flows that have already converged to the ideal rate may have to converge to the desired rate again. So if the number of the concurrent flows becomes large, the ideal rate would be much lower compared to the line rate. And third, when the short burst flows finish, the remaining flows need multiple rounds to occupy the bandwidth released by the completed flows. And in HPCC, you can find that they need the max stage rounds RTT for the converging process, and the converging time will be longer for DCQCN or other reactive solutions. And overall, we can find that the first problem caused dilemma is that existing reactive CC solutions perform well in the stable state, but the instantaneous performance is poor with the bursty traffic. We then proceed to the case 2, and we conduct the in-cast scenarios. We use the same topology and the congestion control scheme like the case 1, but we changes the number of the senders. We consider that the reactive congestion control can't effectively limit the queue length when massive flows burst. And this is because that most flows start at line rate. And when a great deal of concurrent flow bursts, all of the packets will be accumulated at the switch buffer before the congestion signal works. And this figure shows how the queue length peak grows versus the number of flows. And we can see that to make the control after the congestion happened can't effectively limit the packets accumulations. And this can easily lead to the packets lost when concurrent number grows higher. We then make these two scenarios together and increase the RTTs from 6 microseconds to 12 microseconds. And when the RTT grows, the conversion times may change from 30 microseconds to 60 microseconds, and the queue length peak changes from 6 megabytes to 9 megabytes. So we can note that the second problem caused dilemma is that the performance becomes worse when RTT grows. And we think that this is because the congestion often happens at the last hop, and the longer control loop extends the time to send feedback back to the sender. And nevertheless, some people may argue that if the above issues only happen when we use in the reactive solutions, and if we use the proactive solutions, which use the credit to schedule packets sending, the proactive solutions may solve the queuing problem and maintain fully bandwidth utilizations. However, the proactive solutions also meet the first RTT problems, which is mentioned in the ALS. Let me show the first RTT problems. And on the one hand, if we use the first RTT time to schedule packets, just like in the feature, we first send the credit request from the sender to the receiver, and then we send back the credit from receiver back to the senders. This may waste the first RTT time and cause the link bandwidth underutilizations. And on the other hand, if we simply burst packets in the first RTT to avoid waste time, to avoid the first RTT wasting, and the unscheduled packets from the new flows may grab the bandwidth delivered to the scheduled packets, and this may cause buffer overflow at the switches, and the packets loss may happen. So put it simply, we conclude that the third problem caused the dilemma is that it is hard to accurately allocate credit in the first RTT. And all in all, we can conclude that existing solutions face a dilemma in handling with the traffic uncertainty. But however, with the link speed grows from 1 gigabytes per second to 100 gigabytes per second, most flows will finish in few RTTs, and the traffic churn will happen more frequently in today's data center network, and the traffic uncertainty problem may become more severe. So how can we deal with this dilemma? Based on the preceding analysis, there are three main problems behind the dilemma, and we come up with some ideas to solve them. The first problem is that existing solutions perform poorly when dealing with the burst traffic. And according to the Facebook data, the aggregate flows by destination hosts are tightly distributed around 1 megabyte. So we try to aggregate flows to make long-lived flows to mitigate the impact of the bursty traffic. The second problem is that the performance may become worse when RTT grows. So we try to directly send feedback from the sender side TOR to shorten the control loop. So the feedback delay will be reduced within only one RTT. And third, it is hard to accurately allocate credit in the first RTT. So we try to use a pre-credit scheme that we set as initial credit for the aggregate flows. So the packets can be directly sent in the first RTT. Based on the basic ideas, we propose our solution, HiCC, which combines aggregate flows, the credit-based mechanism, and the short control loop. Let me introduce it. And at the layer 2, the packet, the interact layer, packets with the same destination may go into the same view queue, just like the figure shows that the yellow packet and the blue packet with the same destination 7 will go into the same view queue 1.7. And next, the receiver side TOR will use the credits to proactive schedule packets between the TOR switches. And it is based on the weight round robin mechanisms. And in this way, we want to achieve no congestion occur between the TOR switches. As for the first RTT problem mentioned in the previous slides, we use a pre-credit scheme to alleviate it. And we set a few initial credits so that the packets firstly go into the view queue and can directly forward to the next hop. Above all, we aggregate flows and use a pre-credit mechanism to alleviate the first RTT problem and ensure the high bandwidth utilization between TORs. As for the layer 1, we directly distribute rate to the individual flows, and the bandwidth obtained by the aggregate flows can be allocated to the corresponding individual flows. We calculate the rate based on both the view queue arrival rate and the view queue length in order to limit the view queue usage. We will pause the sender when view queue length exceeds the view queue threshold. This would help us to reduce the buffer usage when large-scale concurrent flows burst. We then talk about two challenges in the implementations. And the first problem is about the rate allocation packets. And in higher CC, we mark one reserved bit at the senders periodically, and the sender side TOR do not need to maintain a flow table to store the information of the active senders. And the second problem is about the view queue. And we can find that currently some switch strips like Arista Jericho and the Cisco SilicOne 1 support up to 100 kilo view queue queues. And so the higher CC scheme can work fine for the data centers with the number of the physical servers below this specification that the 100 kilos. But there may be some deployment issues in larger data centers. And moreover, we make a series of System C simulations and S3 simulations. We built a factory topology with 25 gigabytes per second link rate. And there are 16 core switches in S3 and 2 core switches in the System C. We test 3 different scenarios, and including the short burst flow scenarios, the limited scale web search scenario, and all-to-all cache traffic scenario. We first show the result that the throughput and the queue length with the burst flow scenarios. From the figure, we can conclude that the higher CC can limit the view queue length, and it keeps high link bandwidth utilization at the same time. We then show the result of the web search scenarios, and these two figures shows that the FCT slowdown and the queue length while using the different solutions in different traffic patterns. We can observe that high CC reduce the FCT of both the long and the short flows, while also significantly reduce the queuing length. And at last, we show the result of the cache scenarios. And these two figures indicate that in different workflow, the higher CC can reduce the overall average FCT and the 99th percentile FCT compared to other solutions. And high CC can reduce up to 40 percentile FCT slowdown compared to the DCQCN. And to sum up, we conclude that the main problem in today's congestion control solutions is that they face a dilemma in handling the traffic uncertainty. And we come up with a new schemes, high CC, which make long-lived flows against the traffic uncertainty and address the first RTT problems using a pre-credit schemes. And we shorten the control loop by directly distribute rate to the host. And thank you for your attention, and looking forward to your questions.
thank you for the presentation. Are there any questions from the audience? So let me start with my own question. So I know that there are some follow-up work for proactive congestion control, and some of that actually tries to solve the first RTT problem. So can you compare your work with Elias from Kai Chan's group?
Okay. The alias schemes that limit the first RTT problems by the single flows, but we aggregate flows in the sender side TORs, just like that. And we only set the initial credits to the VOQs, and we set the initial credits to the all of the aggregate flows. So I think this may limit the queue length better than ALS, because ALS only control the packet sendings of only the single flows. We can illustrate that if there are many flows from host 1 and host 2 within the same TOR, and we set the initial credit to both of these flows. So I think it can reduce the buffer usage.
I see. So the first RTT data packets are controlled at the virtual output queue, do it by flow control, basically, right? You do something like
yes.
proactive flow control. Okay. So there's a question from audience. Hu Jinbin is asking, is PFC deployed?
Yes, we deployed the PFC.
Okay. So, and I assume this has to be implemented in the switch ASIC, right? So have you given thoughts on how you can further develop this paper into maybe a full conference paper?
I can't get your.
So I assume that the solution has to be implemented in the switch ASIC, right? In the hardware.
Yes.
Okay, so do you have any further plans to develop this paper into a full conference paper?
Yes, we have some future works that maybe we can reduce the scale of the VOQs and some other choice to deploy it in the switch ASIC.
So is that going to be done in simulation, or are you going to actually build emulate switch ASIC using FPGA? What are some options?
Maybe we may build it because of the sanctions of the switch chips. We now only use the simulations, but we will deployment it in the switch chips in the future. Maybe using the maybe use some programmable switch choice or FPGA.
Okay, thank you. Any other questions from the audience? Okay, then let's conclude this presentation. Thank you very much, Siri. Okay, we're going to move on to the final paper of this session, Conjecture, which talks about Nash equilibria in modern internet congestion control. So this is kind of an interesting paper. The talk will be given by Ayush Misra. He's a third-year PhD student at National University of Singapore. His research include systems and networking, more specifically congestion control. So he's been working on internet congestion control with his advisor, Ben Long. Okay, Ayush?
Prof, can you hear me?
Yes, very well.
Okay, so I'll just go ahead and share my screen. Okay, so good afternoon, everyone. I'm Ayush, and I'll be talking about a recent book where we study about the existence of a Nash equilibria in the modern internet congestion control landscape. This work was done along with my colleagues Jingzi, Melodies, Sean, Raj, and my advisor Ben Leong. So first up, I'd just like to talk a little about the internet congestion control landscape. So for as long as the internet has existed, most of the time, the internet congestion control landscape has been largely homogeneous. And we have been able to verify this via periodic measurement studies. So the first one of these came in 2001, where Pade et al. Were inferring TCP behavior of various web servers. And they were able to conclude that a large majority of them were either running Reno or New Reno. Then a few years later, or actually 10 years later in 2011, Yang et al. Were able to perform another measurement study. And this was actually after the introduction of Cubic in 2007. So the 2011 measurement study actually found out that most of the internet had now moved on from predominantly running Reno and New Reno to actually running TCP Cubic. Now, in 2016, Google proposed and deployed on GCP and YouTube their new congestion control algorithm called BBR. And the purpose of introducing BBR was primarily to combat buffer bloat, which was a problem associated with loss-based congestion control algorithms whenever they interacted with debuffers. And because BBR did not use packet losses as a congestion inference mechanism, and instead they used your bottleneck bandwidth and RTT estimates to perform congestion control, they were able to perform a lot better in lossy networks and get better throughput overall on the internet, as was verified by a lot of deployment results by the likes of Google, Dropbox, and Spotify. Now, naturally, when you have the big guns of the internet, running this cool new algorithm, a lot of other people will also want to try it out and try to get the most of these throughput benefits. So in another measurement study that we did a year ago, we actually set about to gather the scope of this exact problem. Like, we have this new congestion control algorithm. How many actual people on the internet have actually switched to this algorithm? So what we found was that even though Cubic was still the most dominant force on the internet, and 36% of the top 20,000 websites on the internet deployed Cubic, BBR was fast approaching, and it was quickly becoming a dominant force in the internet congestion control landscape. We found that 22% of the top 20,000 websites were actually deploying BBR in 2019. And if you couple this with the fact that most of these websites actually stream video, like YouTube and a lot of other video streaming websites, throughput-wise, BBR actually has the potential to contribute to more than 40% of the downstream traffic. So obviously, in the short period of time between BBR being introduced in 2016 and this measurement study being conducted in 2019, BBR has gained a lot of traction because of its throughput benefits. And because of this, a lot of people are adopting it. And it's not hard to see why BBR is doing so well on the internet, because there have been measurement studies that have looked at how BBR performs, especially when it's interacting with loss-based flows like Cubic. And what they've found is that a small number of BBR flows can be very competitive against Cubic. In fact, a recent paper found that single BBR flow can actually get a disproportionately large amount of the bottleneck bandwidth when competing with cubic, which explains a lot of the throughput benefits that a lot of the early adopters of BBR are seeing. So given this paradigm shift in congestion control and how things are changing on the internet in general, the question we want to answer is, given this throughput benefit, is this throughput benefit really going to sustain as more and more people catch on and more people actually switch to BBR? So as more and more servers start running BBR, can we expect the throughput gains to proportionally rise, therefore making BBR a clear, better choice for everyone? And of course, the end product of studying this evolution would likely predict what the future of the internet congestion control landscape would look like. So given the interactions that we already know, can we expect the entire internet to switch from cubic to BBR, as we have seen from Reno to cubic in the past? Or are we missing something, and are things going to be slightly different? Now, fortunately for us, there's a very elegant way to study this problem, because we can model this entire problem of different servers deciding between cubic or BBR as a normal form game. In game theory, a normal form game is basically just a standard representation of a game where the players have a preference of outcome. So in this case, my players would be the individual web servers that are trying to send something on the internet, and the preference of outcome would be throughput. So they'll maybe run cubic and BBR, and they'll choose whichever algorithm gives them better throughput. So in this case, we would call running cubic or BBR as the strategies that these players choose to adopt. Now, given that we can actually model this game as a normal form, we can model this interaction as a normal form game, what we can do is we can look at the already observed interactions between cubic and BBR and try to incorporate these observations into our normal form game and actually predict how this normal form game is going to work. So in the next part of my presentation, I'll quickly go through some observations about how cubic and BBR have been interacting in bottleneck buffers and different network conditions. And then later we'll use these observations and interactions as a basis to understand how we can predict the outcome of this normal form game. So the first interaction I'm going to comment about is throughput in relation to buffer size. Now, because we know cubic is a loss-based algorithm, we can expect it to do really well in deep buffers, right? Because it'll fill the entire buffer, and it's only going to back off when it sees a packet loss, which is likely to be less frequent in deep buffers. And because of this, it's not surprising that people have found that in deep buffers, cubic is able to beat BBR really easily. On the flip side, if you have a bottleneck buffer with a really shallow buffer, you're going to have very frequent packet losses, which is not a good thing for cubic, because this means cubic will be backing off very frequently. But it's not so much of a consequence for BBR, because for a small percentage of packet losses, it's largely loss agnostic. So because of this interaction, given the buffer size, we can make our first observation, which is that when competing at the bottleneck, a cubic flow tends to get a higher throughput than BBR when it's in a deep buffer, and the converse is true when the buffer is shallow. So we can actually take this observation and extend it a little more to really understand how this interaction works. So in the graph that I have on the slide over here, what we've done is we've taken cubic and BBR flows, and we have assigned them different RTTs, and we have progressively increased the size of the bottleneck buffer. And we've tried to understand what BBR's throughput is going to be when this network configuration is applied. And this throughput obviously is normalized by what the throughput of the competing cubic flow is going to be. So unsurprisingly, following our earlier observation, what we see is that in shallow buffers, BBR is able to get most of the throughput, which is why its normalized throughput is above 1. And in deeper buffers, BBR starts losing out. And therefore, its normalized throughput is less than 1, which means it's getting lesser throughput than cubic. But what's interesting is that because we get this smooth trend here, it actually means that there will be a buffer size where for any given network configuration, the BBR flow is going to get the same throughput as the cubic flow. And obviously, this threshold buffer size is not static. It's going to depend on what your network conditions look like. So for example, over here, because we assign different RTTs to different flows, we get different thresholds where the two throughputs are equal. So we kind of formalize this in our second observation, where we say that there must exist a buffer size called T fair, where if the buffer size is less than T fair, BBR is going to win in terms of throughput. If the buffer size is greater than T fair, then BBR is going to lose in terms of throughput. But when the buffer size is exactly T fair, the two algorithms are going to get similar throughput. Next, we can also make an observation about the throughput that BBR gets in relation to the number or the percentage of BBR flows at the bottleneck. And this is especially important because of the problem that we are trying to solve. So what we're trying to solve is we're trying to see how the throughput is going to change as more and more flows start running BBR at the bottleneck. And what we found is that as more and more flows at the bottleneck start running BBR, BBR actually starts getting diminishing returns in terms of throughput. And in fact, depending on your buffer size, there's also going to be this threshold share of BBR flows at the bottleneck buffer, where BBR actually starts performing worse than the computing cubic flows. So in terms of the real world, you can think of it as a point of time in the world where so many people in the world are running BBR that actually now the other congestion control algorithm, which is cubic, starts becoming a better alternative, and BBR stops having its throughput gains. So we summarize this observation as our observation number 3, which is that as the percentage of BBR flows at the bottleneck increase, the per flow average throughput of BBR flows at that bottleneck will decrease. And this is a purely empirical observation that we have made. The last observation I'd like to go through before we actually get into the normal form game and start analyzing it is the throughput of cubic and BBR in relation to the RTT. So we make a very simple observation here, which is based on other measurement studies that have studied how cubic and BBR interact when they have different RTTs. So the observation we make here is that having a smaller RTT is actually beneficial for cubic flows because cubic is able to get more frequent updates about the amount of congestion or amount of available bandwidth at the bottleneck and is therefore able to probe much more aggressively. On the other hand, because BBR places 1 BDP worth of packets at the bottleneck buffer when competing with cubic flows, the BDP becomes a direct correlating factor between the flow and how much bandwidth it gets at the bottleneck. So a direct consequence of this is that a BBR flow with a larger RTT can be expected to get more bandwidth than a BBR flow with a shorter RTT. And this is based on the fact that a larger RTT flow will have a larger BDP and therefore plays more packets in the bottleneck buffer. So in the paper, what we do is that we use these observations, and we use these observations to model a two-flow game. So in the interest of time, I'm not going to go through how we use each of these observations to model each of the different network configurations, but basically the high-level important thing here is that based on our previous observations, we can actually partition all the possible network configurations into 3 regimes, which are based on the different buffer sizes. And inside each of these regimes, we can figure out which congestion control algorithm is going to get the better throughput. So for example, in the first regime, where the buffer size is less than some threshold T2, when both flows are running cubic, the flow with the shorter RTT is going to get the higher throughput, which is notified in this table as S2 being the winner and S1 being the loser. And we can say the exact opposite thing for BBR flows. So when both flows run BBR, the flow with the higher throughput is higher RTT is actually going to get the higher throughput, which is why BBR gets better throughput. And progressively, we can use these observations to actually fill out this entire table and figure out who the winner is going to be in each scenario. Now, given that we have tabulated all the possible combinations of two flows running either cubic or BBR, and we know who wins in each combination, we can actually exhaustively compute what's called the Nash equilibrium for each of these network configurations. A Nash equilibrium in game theory is basically strategy distribution among the players, where none of the players have the incentive to switch to another strategy because they will do strictly worse. So, for example, over here, it would mean that in this configuration where the first flow is running BBR and the second flow is running cubic, if this was the Nash equilibrium, this basically means that the first flow gets worse throughput when running cubic, and the second flow gets worse throughput when running BBR. So in each of these strategies, given that we know who the winner is, we can actually compute this Nash equilibrium. So in the first strategy, for example, if we just look at flow 1, we can see that flow 1 is guaranteed to get most of the bandwidth whenever it's running BBR. And because it's guaranteed success, this is what we call in game theory as a purely dominant strategy, which means that whatever your network condition, whatever the other guy is doing, your first flow is always going to select BBR as its congestion control algorithm. So because the first flow is always going to select BBR, the second flow is simply free to choose whatever gives it better throughput. And we can say that the Nash equilibrium in the first network configuration actually lies when the first flow runs BBR and the second flow is free to run whatever it wants. In the second configuration, again, BBR becomes a purely dominant strategy for your first flow because, again, it's guaranteed to win whenever BBR is running. And following the same logic as our first regime, in the second regime as well, B star becomes the Nash equilibrium. In the last network configuration, where the buffer size is greater than some threshold T3, things actually flip around. And this time, cubic becomes a strictly dominant strategy for flow number 2. So over here, things flip around, and now your Nash equilibrium actually exists whenever your second flow is running cubic, and your first flow is free to run whatever it wants. So it's important to see here that we were able to construct this table purely based on the observations that we made earlier. And this is a purely theoretical result. But actually, if you run this experiment in the real world, and we actually ran this exact experiment for 2 flows, we actually got the exact same Nash equilibrium predicted by this theoretical analysis. So what we found is that for buffer sizes up to twice the BDP of the smallest flow, the Nash equilibrium always existed when both the flows ran BBR. And for all other buffer sizes, the Nash equilibrium existed when the smaller RTT flow ran cubic and the larger RTT flow ran BBR. So minimally, we were able to verify the claims of this analysis and basically make sense of the observations that we saw earlier. Now, obviously, exhaustive proof like we did in the 2-flow game is not good enough for the internet because you have a lot of flows on the internet, and what you need for the internet is a general n-flow proof. And you can't do an n-flow proof exhaustively. So the actual formal proof for an n-flow game is beyond the scope of our short paper here, but we still go ahead and make the conjecture that even in an n-flow game, a Nash equilibrium will exist. And we make this conjecture based on the observation that we saw earlier, which is that BBR flows actually get diminishing returns in terms of throughput as the percentage of BBR flows at the bottleneck increases. So, and this these diminishing returns are actually easy to understand if we take note of an observation that we made earlier, which is that a small number of BBR flows are able to get a disproportionately large share of the bottleneck bandwidth. So if we use this observation, we can plot this small graph here, where on the y-axis, I plot the aggregate bandwidth of all the BBR flows at the bottleneck. And in the x-axis, I just have the percentage of BBR flows at the bottleneck. So this dashed line here on top is the link speed. And this basically defines the bounds of our graph, because even if all your flows are running BBR, you can't get more than the link speed at the bottleneck. So given that BBR flows get a disproportionately large amount of bottleneck bandwidth at when there are a small number of flows, that can actually help us plot this point here, blue point here, which we can see is clearly above the linear function red line that we have here. So basically, if you follow the linear line, that means that as the number of flows increase, your throughput also increases proportionally. But anything above this line would be a sublinear graph, which would basically say that your throughput must come in diminishing returns. So given that our earlier result already makes us plot this blue point here, and our final point can't be higher than the link speed itself, we are actually always stuck with having a sublinear graph over here, which means that BBR is always going to get diminishing returns. So given that we are not actually getting into the formal proof for an n-flow game in this paper, what we actually did was we tried to verify the claims of this conjecture in a limited state space. So what we did here was we ran various number of flows through a bottleneck, and we changed the RTTs of these flows and the network configuration of the bottleneck on its own. And for any given number of flows, what we did was we ran all the possible configurations of different flows running different congestion control algorithms. So for n flows and 2 strategies, that would mean 2 to the power n combinations. And given these combinations, once we had recorded the throughput of each flow in each of these combinations, we were able to calculate the Nash equilibrium. And the Nash equilibrium, as discussed earlier, can be computed very easily. So for example, if I have a toy configuration CBC here, which means that the first flow runs cubic, the second flow runs PBR, and the third flow runs cubic again, then we can consider CBC to be the Nash equilibrium if the first flow switching gives the first flow a worse throughput, the second flow switching gives the second flow a worse throughput, and the third flow switching gives the third flow a worse throughput, thereby proving that none of these flows actually have the incentive to change their congestion control algorithm. So the experiments themselves were conducted with 6, 9, and 12 flows. And in each of these configurations, we gave each third of these flows RTTs of 20, 50, and 80 ms. And then these flows were basically launched through bottlenecks of different link speeds and with different buffer sizes. So before I get into the actual results themselves, I would actually like to go over the properties of the Nash equilibria that we observed in all of our experiments. So in all of our experiments, we were able to observe exactly one Nash equilibrium. And in this exactly one Nash equilibrium, we were able to, we found out that when you actually sort all the flows by RTT, we were always able to write the Nash equilibrium in the following format, which is that the first n flows chose to run cubic, and the last few n minus m flows chose to run DBR. So take note here that because we are sorting our flows by RTT, the first few flows are actually the flows that have the smaller RTT, and the last few flows are actually the flows that have a larger RTT. So because of this, of the unique nature of the Nash equilibrium that we saw, and because we were able to always write it in this configuration, this actually gave us a very succinct way of representing these Nash equilibria. So in the following graphs, where I will go over the effects of different network parameters on this Nash equilibria itself, I will be representing each Nash equilibrium by a single number. And that single number would be M, or basically the percentage of flows that in any configuration are running the cubic algorithm. So first, I'd like to go over the effect of buffer size and link speed on the observed Nash equilibrium. So what we did was, for each of our 6, 9, and 12 flow experiments, we started with a buffer size of 0.5 BDP, and we progressively increased this to a buffer size of 10 BDP. And for each network configuration, we ran the 2πn experiments and tried to calculate what the Nash equilibrium was. What we figured, what we were able to observe, and this wasn't very surprising, is that the buffer size had the biggest effect on where the Nash equilibrium was. So at small buffer sizes, the Nash equilibrium basically existed where none of the flows were running cubic. And this makes sense because in cubic, because in small buffer sizes, cubic is largely handicapped because of frequent packet losses. However, as we increase the packet size, and even for very large buffer sizes, the Nash equilibrium seemed to stagnate at a 50-50 split between the cubic and BBR flows. And this behavior was, of course, consistent across 20, 50, and 100 Mbps bottlenecks. Next, we also tried to change the RTTs that we were assigning to our flows to see if this was having some effect on where the Nash equilibrium lie. And so what we did was, instead of assigning each third of our flows 20, 50, and 80 ms RTTs, we assigned them 40, 80, and 20 ms RTTs and reran our experiments and tried to figure out how the Nash equilibrium changed. So as we can see from the graph here, there's no large change in the trend. The Nash equilibrium still exists where hardly any flows are running cubic when the buffer is shallow, and at a 50-50 split when the buffers are very large. But there is a slight change in the curve itself that connects these 2 points. So when you have larger RTTs, it seems like the flows are slower in adopting cubic at the Nash equilibrium as compared to a network configuration where they had smaller RTTs. So our main motivation behind performing these experiments was to verify the claim that a Nash equilibrium will exist for an arbitrary number of flows. And I think we were able to accomplish that for a limited state space. But this by no means is the end of the road. And of course, there's a lot of future work that we need to do to actually make a bold prediction about end-flow systems and the internet itself in general. But minimally, given our observations in a limited state space, we still think we can draw some interesting conclusions about the future of the internet landscape in general. The first conclusion we like to draw is that despite BBR's current throughput benefits, its benefits are likely going to disappear as more and more people adopt BBR. And a direct consequence of this is that because these benefits are going to reduce, cubic is unlikely to completely disappear from the internet anytime soon. We also think that the internet is likely to remain a heterogeneous mix of congestion control algorithms simply because even in deep buffers and consistently across all realistic network configurations, we have seen a mixed Nash equilibrium where you always have few flows running the other congestion control algorithm. And I guess another big lesson in terms of congestion control design itself is that TCP performance is highly contextual, which means that even though BBR is performing well right now, it does not necessarily mean it's a superior algorithm. It's going to be a superior algorithm in the future as well. It's highly related to how the current algorithm is interacting with what everyone else is doing on the internet. In terms of future work, as discussed before, we need to come up with a formal proof for the Enflow game in general. And in this direction, things do look promising because there have been game theoretic analysis that analyze games very similar to our setting over here, and they have been able to prove the existence of pure strategy Nash equilibrium in those games. So what remains to be seen is if we are successfully able to reduce our setting into those other game theoretic studies so that we can reuse their results. I guess another thing I would like to say is that even though we were able to calculate the Nash equilibrium, we need to bear in mind that the internet does not follow economic game theory. The prime example of this is that Cubic is always more aggressive than Reno, and which we would have considered as a clearly dominant strategy, but there still exist Reno flows on the internet today, and Cubic has not displaced all of them. So whatever our results might be, it's never going to be an accurate description of what is going on the internet. And the last thing I think we need to look at is the effect on the Nash equilibrium in the presence of multi-hop paths, a much larger number of flows that's closer to the number of flows on the internet, and bottleneck links deploying AQMs that can dramatically change the interactions on which we based our entire analysis in this paper. So that's all I have for you today. Thank you for your attention. And now I'd be pleased to take any questions.
Okay, thank you. Then KK has a few questions.
So Ayush, I have a couple, and one is, you're focusing your analysis based on buffer size. And I was wondering what would happen if you were to have an environment that is reacting to occupancy of the buffer rather than buffer size. You alluded to it in the very last word in your future work about AQMs. And, my favorite thing is to look at how I would control buffer occupancy with some kind of notification based on an AQM.
Yes.
And so would your analysis fundamentally change if you had that kind of behavior? And I look at BBR, and that has evolved. It started with the kind of mechanism that you analyzed. It looked to do some notion of being occupancy aware. And it appears to be that the next revision seems to be going back to the old version again. So I wonder if there is something that you can shed light if you focused on occupancy rather than the buffer size itself.
Right. So I think both of those are really great questions. And these are questions that we are working really hard to answer as well. So I'll answer the first question first, which is what happens when you don't have a very simple first in, first out queue at the bottleneck? Obviously, the middle boxes have evolved at this point. More and more people are deploying AQMs. How are things going to change? So I think the biggest thing that we need to study in the presence of these AQMs is the existence of, is basically the validity of this graph that I've drawn here. So in a first in, first out system where most analysis, in which most other measurement studies are done, because they were able to see that a small number of BBR flows get a disproportionately large amount of bandwidth, we are able to plot out a sublinear graph, therefore say that BBR is going to get diminishing returns. Now, obviously, this might not hold in the presence of AQM or any ECN-based scheme, because that fundamentally changes where I'm plotting this blue point here. So if this blue point is somewhere here, you're going to get a superlinear graph. So I think fundamentally when trying to answer the question about how things are going to change in the face of AQMs, we really need to see how the observations that we made based on other measurement studies in this paper are going to change because those are going to predict the interactions. That said, I think I still think a Nash equilibrium is still going to exist, but the nature of this Nash equilibrium might change depending on how these interactions change in the face of AQM. As for your second question, where we can see BBR evolving into BBR v2. So from what I understand about BBR v2 is that the modifications that they're making are, they're trying to be less aggressive when probing bandwidth in the presence of other loss-based schemes. So they try to react to packet losses. And basically, because BBR is unfair to cubic in certain buffer sizes, they're trying to bring this blue point as close as they can to the red point.
Well,
So,
actually, they're also looking at how to get some network feedback.
Right. So I believe that network feedback is based on ECN response and packet losses, in addition to already looking at the RTT and bandwidth. So yes, I agree BBR is evolving, and basically the strategies that we played around with in this analysis are going to change. But I would actually say this is not limited to BBR itself, because in HTTP 3, most of your transport stack is actually going to move to the user space with QUIC, which is going to lower the barrier to deploying your own congestion control algorithm. And in fact, even in the measurement study that we did a year ago, there are lots of interesting new congestion control algorithms that have not been published. So a prime example of this is Fastly deploying this new congestion control algorithm that seems to be following the BDP really closely. And when we got in touch with them, they even have an algorithm that can, switch its modes of operation depending on how the network is reacting to it. So in terms of this problem itself, I think what we have done here is we have taken a very, very simplistic view of the problem in an effort to see if this is a promising direction to work in. So we have taken the two most dominant algorithms, put them through the most standard bottleneck, and see how things change. But obviously, in our future work and when we do a more real-world analysis, definitely considering more complex strategies and a wider array of network configurations and larger number of flows is going to be on the top of our priority list.
Dong-Su, that was a long answer, so I don't know if I can ask one more, hopefully a short question, short answer. On your previous slide to this one on 19, you talked about BBR favoring the long RTT to get better throughput. To me, that seems like a blatantly unfair thing to do. And, we speak a lot about proportional fairness. And then when you say, hey, look, you have a longer RTT, you get better throughput, seems quite the opposite of what you would want.
Yes.
Do you have an insight as to what piece of the mechanism makes that happen? And if, there's at some point you can look at this game theoretic framework and also consider some aspect of fairness.
Okay, so the RTT unfairness in BBR is actually a problem that's been studied by other measurement studies as well. And what they have found is that when BBR is competing with cubic, or even when BBR is competing with a lot of other BBR flows, what happens is that BBR, even though it's a rate-based algorithm, starts becoming C-band limited. And in BBR, the C-band is set to twice the bandwidth delay product, which is your bandwidth multiplied by your RTT. So as soon as your BBR flows become C-band limited, they start placing 1 BDP worth of packets in the bottleneck buffer. And the larger BDP you have, the more packets you're going to place, which is why the RTT unfairness happens in BBR. So I think the root cause for this RTT unfairness is the fact that the C-vent is a multiple of the BDP, and this BDP is different for different RTT flows.
So all these corner case fixes that people have major impact, it looks like.
Yes, they definitely have major impact, but I mean, I still feel like because they are corner case fixes, we might come across other corner cases in the future where things don't work out so well. So really, I think the best thing about BBR is that, obviously it has performance benefits, but it seems to have reignited, this interest in congestion control, and a lot of people are asking the right questions. So really what we need to do is, learn from the issues in BBR's deployment, the unfairness, and all the other studies that people have done, take these questions into consideration and really have a clean slate approach to solving these problems rather than, coming up with small fixes to solve the problems that we see today, but which might not solve the problems that we see tomorrow.
Okay, it's now time to conclude the session. Thank you very much, Ayush, for the insightful presentation and Q&A. I actually have my own set of questions, and since I don't have the online time, I just typed the question on the Zoom chat. Okay, so feel free to answer the questions on Zoom. So this concludes the session. Thank you. Thank you all three speakers.
So Kai, will we have the poster session right away? Or Jillian?
Yes. So now we can have a 5-minute break and come back to the poster session starting at 1 o'clock.
Thank you.
So there will be a presentation at the poster session. Do we stay on Zoom?
Yes, the poster session will still on Zoom.
Okay.
It's short presentations for each poster.
Yeah, it's 10 minutes for each poster.
Got it. Thank you.
Okay, so now we'll start our poster session. Today we will have 6 posters. And now I'll hand the microphone to our first presenter, Qin. Professor Qin Liang, could you please start your session?
Okay. Can you hear me? Can you see this poster?
Yes, we can see it.
Okay. Good afternoon, everyone. And my name is Qin Liang. I'm from Xidian University. And now I want to make a brief introduction to my work. We all know that the end-to-end network traffic protection plays an important role in many network areas, such as security, path planning, and congestion control. And most traditional traffic protection methods only consider temporal correlation and ignore spectral correlation, resulting in low accuracy. To this end, we propose effective traffic protection method based on the graph multi-hand attention convolution neural network method, termed as flow diviner, which combines graph convolutional network and multi-hand attention in its encoder and decoder architecture. Specifically, the graph convolutional network is used to extract spectral correlation from complex network topology and multi-hand attention machines is used to capture dynamic temporal correlation from traffic. Meanwhile, a middle attention module is added between encoder and decoder to model the relationship between historical and future timestamps of traffic. Thus, it can elevate the error accumulation and improve accuracy of flow diviner. The preliminary experts show that our method can effectively obtain temporal and spectral correlation from network historical traffic data, and the test results of all metrics are significantly better than baseline schemes in real traffic distance.
So feel free to ask any questions.
Okay, I see the problem. Li Shuo, can you hear me? Yes. Your question sounds great. We all know that the graph convolutional network is a very effective tool to extract the spatial correlation of traffic data. If the number is too small, it cannot extract the characteristics effectively. If there are too many layers, it will cause the problem of oversmoothing, which is also not conducive to the traffic prediction task. Therefore, and we need to consider it in combination with the network topology. In our preliminary experiment, we set the number of the graph convolution network layer to 3 so that it can effectively aggregate node information and achieve a balance between effectiveness and oversmoothing. Thank you.
Thanks, Qinliang, for the presentation. And
Okay.
now we'll go to the second poster from Dr. Zhen Ling.
Hello everyone, can you hear me?
Yes.
Okay. Good day, dear colleagues. My name is Lin Zheng, and I'm from Xi'an University of Post and Telecommunications. It's a pleasure for me to attend the conference, and I'm glad here to present our recent work as a poster session. So here is my poster presentation, and the title of my presentation is Combined Shared Memory and Buffered Crossbar Architecture for High Bandwidth Onboard Switching Fabric. So let's begin. Let's begin in the introduction section. So nowadays, the space, air, ground integrated network is a very hot research topic. It aims to provide seamless network services all over the globe, satisfying the various future network requirements. And to support the applications on the ground, the satellite network needs to be compatible with the terrestrial IP-based technologies. The satellite onboard switching is the key part of the satellite communication network. But unlike the IP network on the ground, the hardware resources are greatly limited in the space. Therefore, how to design high bandwidth onboard switching in the resource-limited space environment is a problem. So in this paper, we propose a novel switch architecture called Combined Shared Memory and Cross-Point Queuing, and CSCQ for short, for onboard switching fabric. The proposed architecture aims at reducing the memory while maintaining high bandwidth in resource-limited satellite onboard environment. Now let's move to the architecture design. As shown in figure 1, the CSCQ architecture consists of 3 parts, which is the shared memory module, the buffered crossbar element, and the output arbitration modules. In the input side, a fixed number of input ports are multiplexed into one internal bus, and multiple internal buses are interconnected by a cross-point queued crossbar switching element. And in the output side, the output arbitration module demultiplexes the data from one internal bus and split the data into multiple output ports. Through the technique of flow converging, the memory size at the input side and the cross-point buffer can be reduced with no performance degradation. To buffer input packets, each shared memory module maintains a set of dedicated virtual output queues to avoid the head of line blocking and for the QoS support. And a set of schedulers, such as an input bus scheduler and output bus scheduler, are used to control the data transmission in the switching fabric. And the details of the scheduler design can be referred to in our paper. And after that, the simulation results are presented. We verify the performance of the proposal using software simulations. First of all, the packet delay as a function of switch side is shown in figure 2. As we can see, compared with traditional CICQ switching architecture, that is combined input and cross-point queuing, the queuing delay is reduced by about 46% to 69% for different switch size. The reason is that the CSCQ architecture merges multiple ports into one internal bus, reducing the complexity of the switching fabric. The internal speed up also helps to improve the switching performance. And moreover, the proposed architecture is implemented in Xilinx UltraScale Plus FPGA platform According to our experiment, the hardware resources such as lookup tables, registers, and block RAMs are significantly reduced, as shown in Figure 3. The LUT resources are saved about 47% to 68%, and the block RAM is saved about 79% to 85% respectively. And using the state-of-the-art UltraScale Plus FPGA product, the peak throughput can reach 480 gigabits per second, making it a very promising solution for high bandwidth satellite onboard switching. That's all of my poster presentation. This is a joint work with the State Key Laboratory of ISN Xidian University. So if you have any questions, please feel free to contact me at the mailbox. Thanks for all of your attentions.
Thank you, Lin, for the poster. And now we'll start our third poster from Rongji Liao.
Okay, thank you. Can you hear me?
Yeah.
I am Rongji Liao, a student of Communication University of China. And now I will start my presentation. The title of my poster is Learning-Based Deadline-Aware Congestion Control. Congestion control, and with the emergency of a large variety of applications such as VR, video conference, and online gaming, the requirement of deadline awareness is more and more urgent. That is, multimedia data must arrive at the receiving and before a given deadline. In this paper, we proposed a congestion control algorithm using deep reinforcement learning named DRLCC to make the data arrive before the deadline. Recently, a large amount of applications such as video conference and online game is emergency. This application have deadline requirements for data delivery. This is multimedia data must arrive at the receiving end. If data is transmitted to the receiver out of scope of the deadline, it will be useless. And you can see the figure 1 is the framework of DRLCC, and it consists of 3 components, including application layer, network, and deep queue network is a deep reinforcement algorithm. And the state of our of DQN is the information about congestion and the information about about the deadline of the packet. And the state is the sending rate. DRLCC will make a judgment first. When the packet miss the deadline, we drop it to make our other packets to get more bandwidth in the flow. And then when the packet before the deadline, we collect the information about deadline and the deadline, creation time about packet, and the information about congestion to let our algorithm to learn a policy of congestion. And the figure 4 is our network topology. There are 3 senders in the simulation network. 2 of them are used as a sender with a congestion control algorithm for comparison, while the other is used to simulate background traffic. The 3 senders share a link corresponding with 3 senders. Receivers receive data from senders. The propagation delay is set, and the capacity is set to 15 for the bottleneck link. We use burst background traffic generated from real-world network data to simulate the real-world network environment. Random packet loss may occur on the link. The random packet loss rate is 0 and 1% and 0.1%
to simulate a wireless network. And the performance comparison, you can see our algorithm based on reinforcement learning performs well at each packet loss rate, and the ratio that packets arrived before the deadline to the number of packets sent was increased about 10% to 15% compared to BBR and PCCRL. We propose a DRL-CC to solve the problem of data transmission with deadline. That is for my presentation. If you have any question, please ask me or send an email. Thanks everyone for listening.
Hello, I have questions for you. DRL has been a network terms. My question is that why does a reinforcement learning framework work well in your paper, in your design?
I use the deep Q network to learn the information about congestion and the information about the deadline. The deadline information about packet, because I think in the past algorithm of congestion control, they don't consider the information about packet about deadline. And I use the DRL-CC to learn a policy of deadline information. And the reinforcement learning can learn the complex network state independently according to the goal. It is difficult to emulate all the situation in the artificial design network. That's all.
Okay, thank you.
Okay, thanks, Ronchi, for the poster. And now let's go to the fourth poster from Chen Jing.
Hello, can you hear me?
Yes, we can hear you.
Not sure whether the screen is showing correctly. Okay. Hello, I am Chen Jing from Tsinghua University, and it is an honor for me to present our poster named Physical Layer Informed Multipath Redundancy Optimization for Mobile Real-Time Communication, which is co-authored with Li and Professor Ming Wei and from Tsinghua. Real-time communication applications are getting more and more popular. For example, cloud video gaming, video conferencing, and remote surgery. These RTC applications pose strict, often millisecond level requirements on end-to-end latency. However, in mobile scenarios, cellular last mile could frequently experience high variations due to user mobility and handovers and so on. These mobile variations could greatly impact the path condition. And when the condition of one path worsens, merely relying on transport layer adaptation, for example, congestion control and AQM, cannot achieve satisfactory users' quality of experience. Under this circumstance, a common solution is to send data redundantly on multiple paths. In practice, many modern smartphones have two SIM slots and chipsets to support dual LTE connections. When the condition of one path worsens and the other path is in good condition, then duplicating data could effectively mask the tail latency. But there is a question: how much data to be transmitted on each path? How should we adapt the multipath redundancy rate to the path condition? To solve this problem, existing solutions fall into two categories: aggressively duplicating traffic on multipaths, oblivious to the path conditions. For example, REMP TCP, which send the data redundantly to all the available paths. These methods could compellingly reduce the tail latency, but would introduce unnecessary redundant transmission and consume more bandwidth. On the other hand, saving the bandwidth and selecting paths based on RTT measurement on multiple paths. For example, low RTT always sends data on the path with lower measured RTT. These methods could have high goodput, but may have little improvement in latency. So we aim to strike a good balance between low tail latency and high goodput. To this end, we need to timely and accurately observe path degradation. However, transport layer observation of the path degradation is often delayed, as illustrated in this figure. When the channel quality of the cellular last mile worsens, the transport layer cannot observe the degradation until receiving a successfully delivered packet from the cell tower and update the RTT information. Considering the last mile is becoming the major bottleneck of RTC services, this delay could be as high as approximately half an RTT. Therefore, we propose FIRO. We suggest to use physical layer indicators to decide multipath redundancy rates, because physical layer indicators can more timely reflect path degradation. The user equipment almost immediately observe a drop in the signal strength when the path condition degrades. This is our main idea. And during our design, we still confront three challenges. The first is which physical layer indicator shall we use? And we choose the SINR, the signal to interference noise ratio, as the indicator, because it is directly related to the path condition and is accessible through multiple tools. And the second challenge is how to use the SINR. And in response, we design a profiler that predict the distribution of latency given each SINR value. And the mapping from SINR to the latency distribution is fitted from our collected data. And the third challenge is how to seek a balance between low tail latency and high goodput. In response, we design a scheduler to optimize multipath redundancy rates. The scheduler is based on a finite state machine and probability modeling. And for more design details, please refer to our paper. And we also carry out a trace-based preliminary simulation, and our evaluation shows that Firo could effectively reduce the stuttering rate with negligible throughput degradation. We have some ongoing work. We plan to further verify profilers' accuracy and also measure the algorithm overhead, and also carry out the experiment in the NS3 emulation and also testbed. And finally, we will try to work through the implementation into the product stack. That's all my presentation, and welcome all questions and advice and comments. Thank you.
Hello, Jingchen. I have a question. As we all know, timely and accuracy is your key factor or metrics. I wonder how to evaluate the accuracy in testbed or NSN simulator.
To verify the accuracy, maybe we could to grab the packet and see maybe in NS3 emulation we can have traces, and we could set up when is the pass degrees, and we could see that when does our redundancy optimizer knows the pass degrees and compare the time slots, compare the time interval. And if the pass actually degrees and we say find out the degradation of pass in maybe a few milliseconds, then we could say it is timely and also accurately.
Oh, okay, thank you.
Hello, I have a question. Where is your proposed algorithm run? On the user equipment or on the base station?
It is on the user equipment.
Okay. Your proposed algorithm is run on the user equipment.
Yes, our algorithm is intended for the client side, and the client side, as this overview shows, it collects SINR value and go through the profiler and scheduler and outputs the decided redundancy rates and send the rates to the server. And the server will send data according to the redundancy rates.
Okay, thank you.
Thank you. And now let's go to the fifth poster from Guo Yaling.
Thank you.
Okay, can you hear me?
Yes, we can hear you.
Oh, okay. Thank you. Okay. Hello, everyone. I'm Yaning from Tsinghua University. Our work is towards optimization for large-scale Earth observation missions from a global perspective. And Earth observation is a mission of using satellites to take local images of specific area that needs to be monitored and send images back to the ground station for more analysis. It makes crucial contributions to many fields such as military, emergency rescue, and environmental protection. In the last few decades, the application scenarios have become more extensive, and by 2020, more than 30% of all launched satellites have been used for Earth observation. The scale of future missions will be further increased. And the emergence of large-scale low-orbit nanosatellite systems has further promoted the development of Earth observation missions. Because high resolution, which are beneficial for visual analysis, can be taken in low orbits, and large scale of constellation increase the frequency of visits to the same observation spot. But the scale of missions is large, and bandwidth resources are very limited. So scheduling based on distribution of satellites and observation spots is very critical. So a reasonable decision will effectively improve the mission completion rate. And some work has realized Earth observation. The band pipe system accepts ground commands and transmits all of the data. Due to a huge amount of data, it will cause great downlink load and severe packet loss rate, and cannot apply to large-scale Earth observation missions. Therefore, some researchers use in-orbit edge computing to pre-process data to reduce the transmission bandwidth. In fact, there are also ideas for in-orbit computing to deploy more tasks, such as using satellites as data centers to provide low latency and fire service to the whole world. However, with the increasing need for Earth observation, naively matching the local nearby satellites to the missions, that is, local observation, could lead to suboptimal resource utilization and mission incompletion. The main reason is the imbalance of geographical matching relationship between satellites and the observation spots. Most existing constellations are deployed in a grid pattern as marked by black lines for orbits and yellow dots for satellites in the figure. But observation spots are usually set up unevenly according to the population density, as the darkness of red shades in this figure. Therefore, in populated regions, limited satellites and numerous missions lead to mission completion, whereas in some rural regions, bandwidth resources are wasted. Moreover, new missions from different spots are continuously submitted, which might also follow a similar distribution of existing missions, making bandwidth resources even scarcer. The circumstances prevent us from fully leveraging satellite resources to complete more missions. So our observation is that we need to optimize Earth observation from a global perspective. In global optimization, resources are allocated to the most needed missions. Moreover, global optimization also enables the collaboration among multiple satellites to coordinate the resources and complete more missions. That's our motivation. And we model the transmission process from a global perspective. Can you see this part?
Yes.
Oh, yes, okay. Sorry. We model the transmission process from a global perspective, assign transmission according to the existing resources, and observation mission requirements. We use linear programming to find the optimal solution, and we use weather to transmit the images and what quantity to encode as decision variables. Establish the bandwidth constraints are met, the mission from this spot is completed. Our ultimate optimization goal is to maximize the number of missions completed. Through such a model solution, we can get optimal transmission decisions. However, the optimization meets several challenges. First, it is challenging to coordinate the optimization with the existing mechanism with visual tasks. For example, DDS proposed to send low-resolution images first for localization and high resolution in those regions of interest for further analysis. Therefore, we modeled the bandwidth consumption and latency expression for different types of image quality like following patients. And second, because visual tasks are usually completed with heavyweight neural networks, it is hard to ensure the inference accuracy. In response, we approximate accuracy with linear regression of bandwidth based on DDS. Finally, with the increasing scale of observation missions, reducing the complexity with the model is very necessary. Hence, we would always check the correspondence between satellites and missions to prune unnecessary variables. There are still other design points. To cope with real-time requests from different spots, bandwidth resources will be updated after each round of optimization, and all parameters are continuously updated to adjust the model. It should also be noted that we use the DDS framework here, but our model could comply with other visual methods. And as for the evaluation, we use Starlink parameters to simulate Earth observation and compare global and local optimization on the mission completion rate. Our preliminary simulation demonstrated a performance improvement of up to 61.5% over the local optimization. And global optimization also has stronger scalability, and that's my presentation. Thank you.
Thank you very much, Yani. And now let's welcome our final poster from Wang Jiayu.
Okay, thank you very much.
Can you hear me?
Yes, we can hear you.
Thank you. It's my pleasure to be here to introduce our poster. I'm Wang Jiayu from Beijing Institute of Technology. Our poster is exploring the impact of attacks on RNN-reduce. We know that distributed machine learning is widely used in the field of training a deep learning model. And for the field of distributed machine learning, there are basically two architectures, named the parameter server and the ring or reduce. For the parameter server architectures, there will be worker nodes and server nodes. In each training, the worker nodes will send the gradients to the server, and the server will aggregate the gradients from the workers to calculate the global gradients. Finally, it will send back the global gradients to each worker. However, it suffers from the problems that there will be a very high burden for the communication bandwidth. So there is the ring or reduce architecture. For the ring or reduce architecture, each worker only receives parameters from one worker and sends parameters to another worker. It can greatly reduce the burden of the bandwidth. For training a distributed machine learning model, it isn't always very safe. Sometimes it can suffer from the attack. On the right of it, in this picture, it shows the basic theory of the attacks of the malicious workers. When they are all correct workers, the gradients of each correct worker will be similar, and the global gradients will also be similar. However, when there is an attacker, the malicious gradients will be far away from the normal gradients, and the global gradients will be greatly affected by the malicious gradients, and it will result in a bad effect of the training. Some studies has been proposed for solving the problems in the malicious workers. However, this studies often assumes that there is a central server. This assumption isn't right in the ring or reduce architecture. In the ring or reduce architecture, it always contains the scatter reduce process and the all gather process. For these processes, the worker will send parts of the gradients to a fixed adjacent worker and receives the gradients from another fixed adjacent worker. There isn't a central server in this architecture. Based on the ring or reduce architecture, we give some attacking methods as follows. For the first attacking method is the gradient flipping attack. We assume that in this attack, the malicious worker will multiply the local gradients with -1. And for the gradient ascent attack, the malicious worker will multiply the gradients with -4. For the same value attack, each malicious worker will replace its gradients with a random value. For the same value attack, the malicious workers will replace its gradients with 100, and for the label flipping attack, the malicious workers will replace its training label with a wrong label. And after calculating the gradients on the malicious workers, the malicious worker will transmit its gradients between the ring or reduce architecture, and after many steps, the malicious gradients will be transmitted between all the workers and result in a bad effect of the training of the ring or reduce. Here we show some experiments. In our experiments, we assume that there are 8 workers and 16 workers respectively, and we train our model on a CIFAR10 dataset. We assume that there is only one attacker, and we show the effectiveness of the training on AlexNet and the CNN model. The results show that the attack on ring or reduce will result in a decrease of divergence of the training model, and for the same attack, the effect on different training models are distinct. And when there are 16 workers with only one attacker, the effect of the attack can be decreased compared with 8 workers. Here is our experiments, and that's all. Thank you.
Hello. This topic is timely and interesting. We all know PS and real reduce are most well-known architecture. My question is that what is the difference between PS and real reduce architecture?
Thank you for your question. And we know that for the parameter server, there is a central server and there will be many workers. Each worker will communicate with the server. And for this architecture, it suffers from the problems that the server side can have a very high communication bandwidth. And the difference between the parameter server and the ring or reduce is that for the ring or reduce, it can greatly reduce the communication bandwidth for the workers because in ring or reduce, each worker only communicate with 2 other workers. And furthermore, for the topology we see from a global size, the parameter server will be central. The parameter server architecture will be a central server, and the ring or reduce, the workers will be set as a ring architecture. And I think it's the difference between parameter server and the ring or reduce. Thank you for your question.
Does the same attract has a different effect on PS and the real reduce architectures?
Yes, because we have said that in parameter server, there is a central server which can see the gradients from the workers from a global size. And for ring or reduce, each worker can only get the gradients from only 2 workers and can only get the gradients from the adjacent worker. And it is very different. For the last, before studies, for defending the attacks, they always assume that there is a global server that can get the gradients from each worker. However, it can be greatly different in the ring or reduce architecture.
Oh, okay, thank you.
Hello, good morning.
Hi, Adrian. Thank you very much for joining. We'll start in a moment. Xiling, are we ready?
Yes. So, Professor KK, you can start now.
Okay, thank you very much. Adrian, thank you for agreeing to give this first keynote at our APNet workshop. You can share your screen and I will introduce you in the meantime. Folks, it is our great honor and pleasure to welcome Adrian Perig. He is a professor at the Department of Computer Science at ETH in Zurich, Switzerland, where he leads the network security group. From 2002 to 2012, he was a professor of electrical and computer engineering, engineering and public policy, and computer science at Carnegie Mellon in Pittsburgh. From 2007 to 2012, he served as the technical director for CMU's Cyber Security Lab, SciLab. He continues to still be associated with that, and as an adjunct professor at the EC department in CMU. He also got his MS and PhD in computer science from CMU. He is a recipient of the ACM SIGSAC Outstanding Innovation Award in 2013 and became an ACM Fellow in 2017. Adrian's research revolves around building secure systems, and in particular, his group is working on the Scion secure internet architecture. They've been working on it for a while, and he's going to talk about that today and give us some history and how it's a really new way of looking at networking. Adrian, please take it away. Thank you. Welcome.
Many thanks for your kind introduction, KK. It's a pleasure to give this presentation. So let's get started. So I'd like to start with a quite incredible story about the internet in the 80s when the internet started to grow and actually had quite a few growth issues. And also the routing protocol at the time was, which was a tree-based routing system, came to its boundaries. And so at the IETF in 1989, Kirk Lougheed and Yakov Rector met over lunch and said, well, let's try to fix this, and started designing essentially what became the BGP protocol. This is the famous three-napkin protocol that they wrote over lunch. And what's quite incredible is that this protocol still today is the interdomain routing protocol used in the internet. And what's even more incredible, so since the last major update in 1995 of BGP version 4, quite little has changed, and BGP up to today has managed to maintain connectivity in today's internet. So it's really, if you reflect on this, look at the importance of the internet and how one of the most fundamental systems that enables global connectivity was designed over lunch for a network of about 1,000 ASs and has scaled now to roughly 80,000 ASs. It's quite incredible when you reflect upon this. So I'd like to also take you on a journey that we've had over the last 12 years. We've started the journey trying to come up with a secure interdomain routing protocol. And initially, we had no ambitions, of course, to try to deploy this. But through this research, then and through this journey, I'd like to take you now. You'll see that there are actually interesting opportunities that have led to real-world deployment. And so I'll tell you this story now. So many people have noticed the limitations of the internet already that started in the 90s. When people say, well, the internet is important, obviously, and they say, well, what would be the best infrastructure and architecture to run the internet? And so over time, people have also mentioned many different applications that should be supported, like cloud computing, or also mobility was looked at, or video streaming recently, or IoT. And so people have thought about how we build an internet to support these applications. Or also people have looked at specific properties and said, well, security is an issue. We should have an internet that caters better to security requirements. Or people said, and especially recently, have noticed that the internet is being used increasingly for applications that require very low latency. And with BGP optimizing for cost, you typically don't get low latency paths. And so with applications like holographic video conferencing and so on, and tactile feedback and so on, you really want very low latency communication. Privacy, anonymity, high performance, high availability, rapid failover, all these are different types of properties you'd like to achieve from an internet architecture. The question is, well, which one should we do? And of course, the answer is all of them. We have all these applications in use. We should not build an internet for one specific application, but rather one that can cover all these different properties and satisfy all these different applications. And so an approach I'm going to promote in this talk is essentially, if we have a system that provides a very large number of multiple paths, so not just 2 or 3, but really on the order of dozens of different paths, you then get quite an interesting environment where you can then, the application, given all these different paths and path choices, the application can then optimize if it wants paths and optimize them for security or latency or privacy or performance and so on, or even a carbon footprint, CO2. This then enables all these different applications. And so the idea is to have a flexible routing fabric that enables you to create lots of different paths and then essentially disseminate as many paths as applications desire. So now, of course, a word of caution when you try to do this. Number one is also connectivity. You need to ensure that in the end you have connectivity between any node, that path, you do have a guarantee that the path does exist. You also need scalability as you're creating lots of paths. It may be that your network reaches scalability boundaries and you cannot, and your routing system takes up too much bandwidth or too much processing. Another point is security has to be built in from the beginning. As we've noticed, it's very hard to build in later if it wasn't a consideration from the beginning. And you also need compatibility with business models. Otherwise, ISPs may not deploy these systems. So to come back, so how could we create a system that offers strong properties? And so one thing that people have proposed is, well, let's simply disseminate the entire internet topology and with all the links, and then locally nodes can then select paths and essentially perform source routing. And obviously, if you think a bit longer about this, you'll see that, well, the internet is very large, and so the scalability of such approaches is a real issue. And there's also a lack of compatibility with ISP's business models and also privacy of AS topologies and AS routing policies and so on and so forth. So lots of issues with trying to perform source routing. Another approach is has also been proposed recently, and people say, well, with a lot of connections going into the cloud, we don't really need the internet anymore. So let's just simply have the hyperscaler or the cloud providers provide global connectivity, and we don't need an internet anymore, and they will provide connectivity. So although this may work perhaps in the short term, in the long term, this is perhaps not such a great idea. Also, as the applications and the environment keeps changing, and we know how hard it is to predict the future. So it's in long term not a great idea. But also one aspect is that we've seen even today's internet cannot provide good connectivity even to ubiquitous cloud providers. And there have been papers demonstrating around 10% of the connections into cloud providers, which are highly replicated. Despite that, about 10% of the applications or connections are experiencing quite poor connectivity and are quite suboptimal latency. There's also misalignment of incentives. So hyperscaler would have little incentive to provide high quality connectivity to competitors or to global locations. And also such an environment will likely result in a lack of innovation and competition, as a healthy internet ecosystem of large and small companies would enable to fuel innovation in a competitive environment. So that's to this straw man 2. And so people have been looking at a lot of different directions for a new internet. And this started last century, actually already in the 90s. The first projects on this list got started and had with lots of proposals being proposed. And in Scion, we drew our main inspiration from these projects here, shown with the red box, but mainly from the NERA system that has provided most of the inspirations that we built up and build upon. So here's a new suggested architecture that we follow. And in the control plane, the goal is to create lots of path segments. So then create a system for scalable on-demand dissemination of these path segments. So what's important here is it's on-demand. So only if a given path segment is requested, it's actually disseminated. This can also be cached. So imagine an infrastructure similar to DNS. And then, but keep the architecture open and flexible. So other entities can add additional paths that should be created with properties that you couldn't initially anticipate. And so the system essentially provides connectivity and lots of different path choices. Really, we want this massive multipath. And then if this is not enough, people can still add additional paths that can be disseminated in an on-demand fashion. And then in the data plane, we'll need a mechanism for combining these path segments in a policy-compliant way, such that ISP policies are being respected. And there's cryptographic protections that enable only allowed choices of path segment combinations. So then the routers themselves in the network, they actually don't need an interdomain forwarding tables anymore. They can simply look at the information in the path header and forward the packet accordingly. So this is a very high level direction. So diving into a bit more detail, first we'd like to achieve also scalability. So also the HLP system published in 2005 has suggested two-level hierarchical routing. So imagine also now in the context of Scion where we have path segments, you can think of this as a two-dimensional routing system. In the first dimension, it creates highways that connect with the path segments reaching to far places. And then there's also path segments that reach local destinations. So as you can think of local roads. So then in the end, an end-to-end connection can be composed of using a local road until one reaches a highway, going on the highway to close to the destination, and then again using a local road to get to the actual destination. So we'll also see that this path combination results in a very large number of potential combinations. And this is very desirable because that allows then different optimizations for different criteria. And again, the data plane itself is going to be very simple without any interdomain forwarding tables. So let's dive into this. The first mechanism to achieve this two-level hierarchy we call this isolation domains. So the small circles here represent autonomous systems, like in today's internet, but these are now grouped into different isolation domains, and they can also be overlapping. This is a virtual construct, if you wish, and an autonomous system can be part of multiple isolation domains. Then each isolation domain has what we call a core, and these ASs that are running this ISD core, they then also participate in the routing to create path segments between different isolation domains. So these are the highways, and then they also initiate the path segments within the isolation domains. These are the referred to as local roads. So here's a one-slide overview putting these concepts all together. So first, it's going to be a path-based architecture. So we'll have these path segments that are created in the control plane, and they're also disseminated by the control plane, and again, importantly, on demand disseminated. So they're not just globally pushed around, but only pulled and cached when required. And so in this example, we have a number of autonomous systems, and here we're going to look at communication from F to S. And here F requested and path segments to S. And for this example, here there's two sets of path segments that were given to F. They can only be combined in these two ways. So we have the local path segments inside the ISD. These are the local roads shown in blue. Then the inter-ISD path segments shown in orange. And then the destination, again, the local road path segment leading to S. And there are these two combinations, and these combinations now can be added to the packet header. They form the end-to-end path. And then the routers on the way simply look at this information, also perform cryptographic verification of this information, and then forward on the packet to the destination. So what's important also is the efficiency. And in terms of overhead, SIGN has a 12 bytes overhead per AS. So that's 12 bytes, including all the cryptographic information, which is a lot, but overall there's not that many AS hops. So we have an overhead of roughly 80 bytes per packet, which is a lot, but on the other hand, you're getting a lot of benefits as well. Then in terms of processing overhead, this cryptographic information can be validated extremely efficiently. So that's essentially an AES operation on a single block, which only requires on the order of a few nanoseconds. Even on standard CPUs, this only takes about 10 nanoseconds to compute. So it's really very, very efficient and very fast to forward these types of packets. So that was the high-level overview of SIGN. I'll like to highlight a few points. The first one is scalability. And here, this slide shows how the overhead of the construction of local path segments. So this shows intra-ISD beaconing overhead. So beaconing is the process in SIGN to create these path segments. And the x-axis shows different autonomous systems that were simulated and compared to also BGP. And then the y-axis shows the relative effort of that particular autonomous system compared to BGP, the effort that it has in BGP. And so it's a simulation of SIGN compared to the real-world BGP information. And for intra-ISD beaconing, the overhead is roughly 70 times less on average. That's the last bar shown. And then the overhead ranges between 100 times less overhead to roughly 50 times less overhead, depending on the AS. So dramatically lower overhead, despite that the SIGN system finds multiple path segments to the core ASs. So that's intra-ISD beaconing to find the local roads. Now for the global roads, the overhead is quite a bit higher. This now finds, because the core ASs, the largest ISPs that run these isolation domains, they have many more paths and they're very highly connected to each other. So here again, on the diagram on the left, you see the different autonomous systems, again, compared to the real-world BGP observations of the effort. SIGN has between a few percent to roughly 15% of the overhead of BGP, but of course finding in this example up to about 50 paths to every other ISD core AS. So in these simulations we had 2,000 core ASs with the real internet topology, and we only limited finding up to 50 paths between each pair of entities, and still compared to BGP, the overhead on average was roughly 10 times lower. Now, if you also compare this to BGP SEC, so this is now the diagram on the left, on the right, this is normalized to the overhead of BGP. So BGP is always 1, and SIGN is the tiny bar in blue at the bottom, and again showing the total overhead of finding all these different path segments, whereas BGP only finds 1 path segment. And then we also see BGP SEC, and here the overhead is on average roughly 5 times higher than the overhead of BGP. But of course, SIGN is also a secure protocol, so it also has actually even better security than BGP SEC, but at a much, much lower overhead. So putting these things together, it's a rule of thumb is that SIGN spends about 200 times less effort than BGP and about 1,000 times less effort than BGP SEC for a given to find 1 path, right, on a per path basis. But even for finding a massive number of paths, SIGN is of course much, much lower still than BGP. So the scalability is dramatically improved of these path-based systems. The reason is mainly twofold. So one reason is that SIGN announces per autonomous system and not per prefix. And a second reason is that in SIGN there is no convergence for the routing itself. So these paths are simply being announced and can be sent on by the respective autonomous systems, but there's no convergence process, so to speak. There's no back and forth to optimize these paths. There's simply more and more paths that are being announced, but there's no convergence process that is required for the system to work or to converge, so to speak. And that's where these big scalability gains are from. So next, I'd like to point out the importance of path awareness and multipath communication. And for this, I'd like to start out with a case of communication from Zurich to Singapore. And there are typically 2 paths that we can observe on the network. So one goes via the US and Japan and then to Singapore. That's typically a high latency, but also high bandwidth path of roughly 450 milliseconds round trip time. Second path through the Suez Canal, roughly half the latency, but also lower bandwidths because they're older cables and older infrastructure that way. And that's a path that sometimes we also see and is available. So you could say, well, which one is better? Well, both paths are good, and BGP is a money routing protocol that picks one or the other, typically takes whichever path is cheaper for the ISP. But depending on the application, you'd like either path to be used. So ideally, say for a teleconference, like I'm giving now this presentation, ideally the video signal could be sent over the high bandwidth path, whereas the voice signal would be sent over the low latency path. And even more paths may be available, and so all these paths can be used simultaneously, as I'm going to show in a demo in a minute. So to demonstrate that SIGN is really massively multipath, let me show you here an example. So the reason a very large number of paths can be found is not only because they're found in the control plane, but then in the data plane, they can also be combined with different, for different end-to-end paths. So here's an example of source AS and the destination AS. The source has these 4 path segments to its local core, ISD core ASs, and then there's a number of, the core ASs are typically very highly connected. Actually, I've only shown a few connections here. In reality, these large ISPs are very, very highly connected. And so you see a lot of paths. Like I mentioned, we typically try to limit the path finding only to 50 paths between any pair of ASs. And so there actually are a lot more paths. And so you already need to optimize which 50 paths you'd like to find the most high quality paths there. But so even in this small example, you see there are already 54 different end-to-end paths that are possible through the different path segment combinations. And this then leads to a very large number of possible end-to-end paths in reality. And so this type of flexibility then gives you a lot of opportunities for performing optimization. So you can optimize your paths and select the paths based on latency or jitter. And this is also something that we propose to paths have information in them what the lower bound of the latency is expected to be without the queuing latency. So as you're combining these path segments, you already learn what latency you can expect before you even send the packet. Also, some amount of bandwidth information is in, bottleneck bandwidth information, MTU, and so on. And also you can optimize your path combinations based on privacy or anonymity, or you could also want to lower your carbon footprint and select paths that reduces the CO2 footprint. That's also information that we're envisioning adding to the path segments. So then the application can also make use of multiple paths simultaneously and dynamically optimize them over time to improve performance. And what's really exciting, once you see this in operation, it's really a new world for networking. When you see the system has a dozen different paths available and it's starting to optimize over them, starts using one path and starts communicating, but selects additional paths that it keeps measuring. And over time, as the parameters change of given paths, they may break or they may encounter congestion. The system automatically fails over and use another path which is so fast that as a human you cannot even see this. So this happens within milliseconds. And with SION, there's no need for any network signaling or setup or state, or simply all the paths can simply be used right away. This is really, really quite exciting. Let me try to convey this excitement through 2 demos that we've recently built. So the first one is by Tony John, who is a PhD student at the David Hausherr's group in Magdeburg. And so let me just play this. This is an IoT demo for a remote driving case, where on the left-hand side you see the entity driving the vehicle, but the actual driving simulator is remotely. And then on the right you see the actual simulator output, and you'll see if you have a network problem, essentially your car will crash. But with a multipath system can fill over so quickly that your car will be safe. So let me just play this demo and go from there.
Link is a low-cost inter-domain connectivity solution for industrial systems. It is based on the SION Internet architecture. Our solution provides high availability, similar to a leased line connection, but served over a public network. To illustrate the capability of our solution, this demo presents a remote driving use case for Link. The car simulator is remotely controlled over a Link connection. The remote control sends control signals to the simulator, while the simulator sends back the video feed from a front-facing camera of the car. In this demo, there are 3 Scion paths for Link to choose from. With the controls, we can disconnect any path and change its quality in terms of latency, jitter, and bandwidth. In the first scenario, we are simulating a BGP-based internet. The end hosts have no control over the paths chosen. If the path fails in the network, it can take several minutes to find a new path. Now the current path has failed, resulting in the remote control losing connection and leading to the car's crash. In the second scenario, Link is running in normal mode. If the chosen path fails, it chooses another path. The user sets the path selection preference. In this case, paths with low latency and jitter are preferred. The chosen path is disconnected, and the connection fails over to the next best path. In normal mode, the failover can take up to a second. In the third scenario, Link is running in multi-path mode. Traffic is duplicated over multiple paths to provide very high availability and reliability. Here, the settings specify duplication over 2 paths. From the throughput graph, we can see the traffic is duplicated over paths 1 and 2. The remote control is unaffected when the first path is disconnected. Now the traffic is duplicated over the remaining 2 available paths. The remote control is still unaffected when the second path is also disconnected. In the final scenario, Link is running in adaptive multipath mode. In this mode, traffic is duplicated only when a change in path metrics is observed, so as to make a new connection before the current connection breaks. This mode provides high availability without the high network utilization of duplicating traffic all the time. The increase in latency resulted in duplication of traffic on path 2, so the remote control runs unaffected even when path 1 is disconnected. Path 1 is disconnected again to show the faster failover in adaptive multipath mode.
Great. So that was this first demo. And it's when you again see this in real time, how the system operates as you're changing parameters and keeps optimizing for the paths. It's really quite amazing how well it works. So the second example is a video conferencing, teleconferencing demo by Jonas Gessner, who's a master student here at ETH. And he built application for iOS leveraging Scion multipath. And in essence, so this is an very early demo of the system, but it already works quite well. And he's using 2 different paths for the voice, and then 1 path for the video. And then he cuts a link that is used by one of the paths for the voice, and the video path as well is being cut. But the voice keeps working because the third path is unaffected, and the video conference can continue. And then the system finds out that 1 path broke and fails over to another path that's working. So, but at no time do you actually lose the voice connectivity, and the video connectivity is only very briefly lost, but this can also be optimized even faster. So these types of demos, when you see these systems in operation, it's can be quite addictive to have such multipath. So, and in the Scion architecture, we've also built a lot of extensions to provide additional security features. For instance, one is the Colibri Global Quality of Service system, which is a system that we're taking into operation this month, still in June. We're setting this up in Scion Lab, which I'll introduce in a minute. But there are many other systems like DRKey to provide cryptographic keys for any host in the internet. It's a high-speed key derivation system that allows a router to derive a key for any host on the internet within roughly 20 nanoseconds. So it can create error messages that are fully authenticated. The EPIC system is another example where we allow routers to perform authentication for every packet going through using this DRKey system. And then deriving a key for the host, which is different actually for every AS and every host, and then validating the source address in a packet. And it also provides path validation at very low overhead, roughly almost providing no slowdown for packet forwarding. So these are all different types of systems that have been created for SION. There's many online resources you can look at to learn more about it, including open source code on GitHub. There's a company called Anapaya that commercializes SION, and I'll talk a bit more about SION Lab, which is the global infrastructure you can use. And the book is also available for free on the website. We're writing another book which will come out in the coming months. This first one is now 4 years old, and there was a lot of progress in the last 4 years. So a new book will come out soon that documents all the new features. We're also in the process of launching a foundation. The foundation is going to handle governance and also standardization documentation of SION, pushes further the open source development and community building, and also performs certification for people, hardware, software, and autonomous systems, or ISPs, I should say. The most important point in the short term will be the standardization, that SION will offer or will have a set of standards that people can look at and build upon. And this is, of course, also an open process with companies and research teams who can participate, similar to IETF or ITU. You may wonder, well, why didn't we go to the IETF or ITU or other organizations? And of course, we did go. But it turned out that for architecture with as many components as SION, it would take quite a long time. And so with the foundation, we'll be able to issue a first set of standards already this year, and then build on top of that. And meanwhile, we'll also interact with IETF, ITU, and other standards organizations as well to see how to best drive this forward. So you may wonder about deployment. How hard is it to deploy SION? And the answer is it's quite simple, actually. Even though it's a new internet architecture, an ISP only needs to deploy a few border routers, and which are implemented today based on standard hardware that essentially performs software-based routing and forwarding. And this is quite low effort to set up. We've onboarded an ISP within a week actually already. After a week, the ISP was fully operational and was able to offer the first connections to customers. Of course, the training is the longest part of this, training the personnel how to use the new architecture. But it's really not much effort. The largest part of the cost is employee training. Also for end domains, using SION is quite simple. There's a SION IP gateway, we call this the SIG, which translates from standard IP traffic to SION traffic. And this SION IP gateway is then fully configurable, allowing also forwarding via regular IP, IPv4, IPv6, or enabling rules such as path-based rules, which for given destinations, which paths should be chosen, and then be sent over the SION network. So lots of flexibility offered here. And so the end hosts don't have to be updated. What's nice is also the commercial system of the SION IP gateway can be deployed fully redundant. And so if one fails, it can be seamless failover to another SIG, and it's quite robust. And the customers using it can see immediate benefits thanks to all the different features I mentioned. Then you'll want to offer the SIG native SION connectivity to ISPs, and there's today are the 8 ISPs that are offering native SIGN connectivity. And so this, then the SIG has a choice ideally between different ISPs, but also is of course capable of speaking IP and sending, forwarding IP packets also directly to IP-based ISPs. There's a global infrastructure called SIGN Lab you can use today. This is mainly led by David Hausherr's team at University of Magdeburg, and it's open to anyone. You can set up and connect your own AS within minutes. And there's also some ISPs participating. SIGN Lab, though, is an overlay network, overlaid on today's internet. For the most of these connections are relying on BGP for forwarding, but it's okay in this case because this is a global testbed used for research, and so it's okay to rely on BGP. Lots of research opportunities. I'm happy to share the slides so you can go through them. It's exciting things you can do with SIGN Lab. What's also really exciting is the SIGN production network. This is mainly led by Anapaya Systems, the startup commercializing SIGN. And this global network is fully BGP free. So there's no dependence on the BGP protocol. So it's not an overlay network. And it's completely fault independent from BGP. And so there are several international ISPs also joining this network, and it's like a global internet, fully federated. It's not a private network, it's a global public network, but it has all the security mechanisms built in. And so the goal is to have the first global public secure communication network. The deployment for the ISPs are mostly in Switzerland for now, but also it's spreading globally, and including LG in South Korea is offering SIGN connectivity. There are also several IXPs. SwissX already offers SIGN peering, but many others also provide it. And it was quite easy to set up with these entities. Fundamentally, there's no big difference between SIGN peering or BGP peering. I'll talk about the deployment in banks in a minute. And so there's this global network available today, which is native SIGN, really BGP free, in over 100 data centers in over 10 countries globally, where you can get this native SIGN connectivity. So what's also exciting is that at the end host, we can offer native SIGN connectivity in a completely seamless fashion. And so this is an approach we're currently looking at, that the server, of course, one can set up a SIGN server, and that can be announced also via DNS. So you can offer the same service via IPv4, IPv6, and SIGN, and announce that presence via the regular DNS system. On the end host, we have a client bootstrapping package which can bootstrap all the SIGN parameters automatically, leveraging DHCP and DNS. So this works, really well. And then we're looking at extending the happy eyeballs system that switches between IPv4 and IPv6 to add SIGN as a third choice. So the application, if it uses if the application uses this happy eyeballs approach, it will try to see, can I reach the service via IPv4, IPv6, and also can I reach it via SIGN? And if it can, there is of course an incentive to make use of SIGN, because the path optimization will, with high probability, offer lower latency for the connection, and possibly also higher bandwidth through multipathing, and also dynamically optimize the connections or dynamically optimize the paths, I should say, as the connection is being established. And this will offer benefits and will offer higher communication quality. And so this is quite an exciting system we're now looking at, because it can use Cyan natively without the user even noticing. Some real-world deployments that are in use today. So the Swiss banks have built a network called the Secure Swiss Financial Network, and they are have been testing this for now almost 4 years, and it's now in production, where they're making use of Cyan for communication between Swiss banks. And the tests they've done were extremely positive. Compared to the existing infrastructure, Cyan had dramatically lower failover, and as almost the entire infrastructure was simulated to fail, the system was still up, and as long as one path works, the whole system was fully functional and provided connectivity, which was which the banks lay a lot of emphasis on. Also, the Swiss government has been using Cyan, and one example is for communication with embassies. And there's right now the embassy in Seoul, which is connected with Cyan to Switzerland in a BGP-free manner. Also in the ETH domain, which is composed also of EPFL and ETH Zurich, the Paul Scherrer Institute, which is a mainly physics-based institution, and the National Center for Supercomputing, CSCS, and many other institutes that are part of the ETH domain all have native Cyan connectivity now. And we've shown a lot of real-world use cases that without changing the end application, we're able to actually speed up communication and data transmissions, even though Switzerland is quite a small country. But even within this small environment, we're able to speed up data transfers by 2 to 3 times of traditional applications. And we achieved point-to-host data transmissions of over 90 gigabits per second for extended time periods for almost up to 10 minutes. So really very high speed, very high security, very high availability that we're able to demonstrate in real-world environments. And so next, I'd like to share with you a couple of insights we've had on this journey. And the first insight is that incremental deployment is really possible. So it's, people, when they talk about a future internet, they say, well, you can never deploy it. But actually, it's not as hard as it sounds. And a new internet can operate side by side with BGP, make use of the internal communication infrastructure without relying on BGP. And we've demonstrated that this is possible and actually used for production traffic already today. So, and also even for endpoints with the Cyan IP gateway and with this Happy Eyeballs system, Cyan can be used without the user even noticing. Another insight we've had is that secure routing is really insufficient. And I don't have time to go into details in this talk, but I wanted to briefly point out that there have been several large-scale failures where a secure routing protocol would have not been sufficient. So essentially, where a bottleneck link is being announced, which is a legitimate link, but it has insufficient amount of bandwidth, causing tremendous congestion and downtime for large areas of the internet, is one case. Another case is where a link fails, but the withdrawal message is not going out. And so packets are dropped for extended time periods, causing large-scale outages. And so you really need a multipath protocol. So of course you want the secure routing protocol, but BGP-SEC is really not sufficient. You really need a multipath protocol to handle these kinds of cases. So the insight here also is multipath is really a necessity and not a luxury. It also solves problems with rapid failover that have become possible in a multipath environment, or also while BGP type protocol needs to converge and update forwarding tables, a multipath protocol has alternative paths that are functioning already established. And so you get massively better availability thanks to a multipath system. Another insight was that cryptographic processing at line rate is possible. So using the AES block cipher, for instance, in hardware, you can perform AES within a few nanoseconds. And so this, even in software, it's on the order of 10 nanoseconds on commodity CPUs. So this really demonstrates that very high-speed cryptographic processing is feasible. And so the systems called DRKey and EPIC that I briefly mentioned on an earlier slide enable per packet source authentication below even 100 nanoseconds purely in software, and this can be much sped up also on the hardware deployment. And so these types of mechanisms now enable completely new approaches for network security, which has been quite exciting to build all these add-on systems that are now becoming available in Scion. Also, another insight was that formal verification is really necessary. As we design large-scale systems, as humans, we cannot think through all the millions or billions of different interleavings of the protocol or different types of actions. And so one really has to use formal verification. We've been very lucky to collaborate with David Basin's and Peter Muller's teams here at ETH over the past many years on this verified Scion project, where they also found vulnerabilities that did exist in the design and were able to eradicate very early on thanks to formal verification. But the insight really is, if you want to build a complex distributed system and you want to achieve high security, you must have formal verification. Otherwise, it's very hard to achieve strong assurance. So in summary, Scion is a next generation internet you can use today. You can get a native Scion connectivity in many data centers around the world. The system is very high performance. You can get increased efficiency. And of course, also, you can achieve very high security, high assurance, high availability. You're immune against many attacks. And so that gives you really a lot of nice properties today. And so finally, when you go on a long expedition, and this has been a 12-year journey that we've been on the Scion project, there's lots of discoveries you can have, and you have the opportunity to question ingrained assumptions and so on. So it's been really a lot of fun and very rewarding journey to rethink the architecture. And so I invite you to also join us, and you can join us via Scion Lab and start and connect to it and have your own node at your university. We'll be happy to connect you, or simply use an overlay connection through a VPN to one of our attachment points. So almost no setup required for that. And be happy to collaborate and work with you. So here's a picture of the team. And hopefully, despite COVID, we can take up our annual retreats again. Here, mainly showing the teams of Peter Muller and David Basin and my group at ETH. But hopefully we can again meet with everyone somewhere in the Swiss mountains on our annual retreats. Many thanks, and be happy to take your questions.
Thank you very much, Adrian. Folks, if you have questions, you can speak up or type it in chat, whichever.
Hi. Yeah.
Go ahead.
Yeah. Hi, Andrew. This is Yongqiang from Microsoft Research Asia. Thank you very much for such an insightful talk. I learned a lot, and I like the idea presented in Scion, which, well, I'm just curious whether, so you present some of the incentives for servers or clients that then they can bring some of the benefit for high bandwidth or low latency by multipath. So I'm just curious whether the ISPs or more generally the cloud service provider, CSPs, have the similar incentive to adopt such new architecture. So without some critical weakness such as IPv4 address shortage, they may hesitate to switch to the brand new architecture, even for IPv4. So we see a quite long path to replace it with IPv6. So yeah, so that is my first question. And the second question is, so I'm surprised to see that per packet speed for 100 nanoseconds. It is quite amazing number. But I'm also wondering how it would scale. For example, this performance might be sufficient for the end host with 10 gigabit per second link speed. But some gateways may need higher capacity as large as, for example, 100 million or even billion packets per second, for example, given 400 gigabit per second and 22 ports per switch. So that security or encryption speed requirements is very, very high. So I'm just wondering how you can scale that the speed to that scale. So yeah, thank you.
Great. Yeah, thank you for these excellent questions. The first one is about incentives. And so clearly, I hope you agree that customers do have incentives to pick multiple paths and improve latency, bandwidth, and so on. Yeah. And so if customers have the incentive, ISPs have an incentive to provide a product, right? They can offer new services. They can quite easily integrate, for instance, LEO satellite paths and sell those connections. They have a lot of opportunities for selling new services to customers, offering high security. And actually, because Cyan is a security architecture, it has fewer outages and is robust also to errors. So ISPs already noticed that the management is simpler. And even if a path breaks or fails at some point, likely another path is available and the customer is happy because they don't even notice the outage because the system can switch over very rapidly to another working path. So definitely lots of incentives for customers. And so ISPs also have new business models they can offer. They have new opportunities for providing services. So the ISPs now see many ways in order to offer new services. So for instance, CO2 is a big deal here in Europe, lower carbon footprint. So Cyan can offer insight and transparency about which path has which carbon footprint and enables carbon footprint optimization across different paths. So that's yet another product ISPs are currently looking at offering to customers, because there's also a way to offer and use the Cyan backbone as for traditional IP traffic to optimize CO2 for even regular internet traffic for regular hosts that communicate with regular servers that neither knows about Cyan, but the Cyan backbone is used as a way to optimize for CO2. And so that's yet another exciting offering that ISPs are looking at today. So to your second question about speed, what's surprising is despite the security, Cyan actually has lower overhead and effort for routers than today's internet, right? If you need to do interdomain route table lookup, that's actually tremendous effort, and it's only so fast because of dedicated hardware of TCAMs that are burning a lot of electricity. So if you look at the Cyan forwarding, it's even simpler, and so the speeds can be even higher than for today's internet. So router manufacturers, of course, in hardware, there will be less effort to forward a Cyan packet than an IP packet. And so in addition, then of course, we add security, then that's of course requires some additional effort. But as I mentioned, AES is extremely fast, can be computed in nanoseconds. And so, we're very careful of not requiring per flow state on routers. Even our QoS system has no per flow state on the router. And still the enforcement still works and finds entities that are sending too much. So putting it all together, without considering the security, Cyan is hands down requires less effort for forwarding. Of course, you need to build the hardware accordingly. We've shown that in software we can achieve very high forwarding rates, but in hardware this will be obviously even faster. So, but we did compute that the actual energy requirement of SION will be lower than for today's IP internet. So that gives you an indication that the scalability actually not only for routing, but also of the data plane is likely going to improve over today's internet, despite then having all these security features on top.
Thank you very much.
I wanted to follow up on the incentive question, Adrian.
I like your t-shirt, by the way.
I bought it just for you. The thing that you talked about in terms of incentives, if you have already the availability of multipath and you have the networking infrastructure move over to SION, what is the incentive then for end systems to actually change from their current framework to being native SION?
So if they continue using IPv4, then they have no optimization choices. So our early experiments show that if you have a choice of different paths, some with, and our experiments also show that for over 50% of the end-to-end connections, we have a lower latency path than today's internet. And these were quite careful optimization, quite careful simulations. So I think in reality, it's going to be even better than that. So this will yield about 20% faster download times, at least for web pages. Then obviously that's already a no-brainer, right? I mean, as a customer, you don't care, right? you want fast web pages. You want that your connection keeps running. And so also there, if you have a video conference and there's a link failure somewhere or a congestion, and the system can rapidly fill over to a different path that's working, you're going to have a better video conferencing experience. And so to you, I mean, fundamentally, as a user, you don't care if is it SION, is it IP. But if SION gives you lower latency, and in Europe, actually, many people really care about carbon footprint. So if they can say, I'd like to use a path that's carbon footprint optimized, we actually showed that in many cases also there's a path with a lower CO2 footprint, so people feel good. So whatever your fancy, if you play games, you also want low latency paths. And if you do a download, you want the high bandwidth path. So this simply gives you better quality of experience as a user. So what's not to like?
So one question is, you talked about policy being at the ISP level. Right. I was wondering if you look at, the ability for, whether it's end systems or enterprises expressing policy that can then be incorporated into all the route choices that you make. And is there a way to express that policy in a compact way?
Mm-hmm. Right, that's really, the whole policy discussion is a longer discussion, because in SION, if the end system does get some choice, and these choices then may result in, say, a more expensive path for the ISP, which of course ISPs will not like if the customers pick that. And so there do have to be some changes. So the way we envision this is that ISPs, if there is a path that is really more expensive, say a LEO satellite path, in SION this can be trivially offered to customers, right? It's a path that's probably 100 to 1,000 times more expensive for the ISP. And so a customer would likely have to pay more, and then it gets access to this LEO satellite path. But also, even other customers, they may be getting very small fractions of bandwidth on that path. So the ISP can say, I give you, say, 1 packet a second or something, right? So some very low rate. So you can try out the path, right? You can see the actual latency end to end. And or maybe if the path is not used very much, maybe the customers can get a bit more. But then if you then pay more as a customer, you then get full access to this path. Right? And so in Cyan, you can very easily, as an ISP, offer such services, but you do need to adapt a bit how you're doing your traffic engineering and how you're providing your paths to which customers and so on. But it's dramatically more flexible than what we have today and offers many new opportunities. Right, to do. Right. Mm-hmm.
I'll let somebody else ask last question. I know we are a little bit over time. Otherwise, let me make a request, Adrian. Will you share the slides so that we can post them?
Right, absolutely. Mm-hmm.
Thank you very much.
Great, yeah, many thanks.
On behalf of everybody, thank you for the talk. Thanks very much for the keynote. Thank you.
Thank you very much.
Thank you.
So now we will have a 4-minute break and come back at 3:10 for the next session. Welcome back. So let's start our first session in the afternoon, and I'll now give the microphone to Professor Huang.
Okay, hello everyone. Welcome to this session. And our first speaker is Liu Huang. He is now a PhD student from Xidian University, and today he will present his paper, Hyperparser. Now, Huang, you may start now.
Thank you for your introduction. Can you see the screen?
Yes, and you may start.
Okay, thank you. Hello, everyone. I'm Huan Liu from Xidian University. I'm happy to present my work, Hyperparser. Okay. Okay. Can you see the screen?
Yes.
Okay, thank you. Hyperparser, a high-performance parser architecture for the next generation programmable switch and smart NIC. Nowadays, ASIC-based programmable switches and FPGA-based smart NIC are becoming more and more popular. The programmable parser is a key element in programmable switches and smart NICs, which can identify the headers and extract the concerned fields. For the header identification, a parser can parse a series of bits and obtain several headers. And for the field extraction, parser can extract the concerned fields and scatter them to the proper positions in the packet header vector, PHV. According to the Ethernet roadmap, 1800 Gbps and 1.6 Tbps are expected to be the future switch interface space after 2022, which leads to higher throughput of the parser. Intel has announced that it has successfully integrated its 1.6 Tbps silicon photonics engine with its programmable Ethernet switch. So it's clear that future parsers should achieve higher performance. At the same time, it should keep efficient in terms of power, area, and latency. The end of standard scaling leads to the dark silicon problem, which results in a limited power budget. Moore's law is slowing down, and advanced process technology has become increasingly expensive. A lower chip area can efficiently reduce cost. As for latency, the need for low latency and low jitter operations at the data center scale continues to grow. Okay, the following is our observation. Firstly, high performance means a higher clock frequency or a wider bus in the chip. However, the performance wall indicates that the clock frequency of switch silicon is in the order of 1 GHz. So the only choice is the adoption of a wider inner bus, for example, 4,000 bits. Data bus in 4,000 bits is wide enough to accommodate the longest packet header. In this situation, for the header identification, the bit selection strategy outperforms FFM-based and pipeline-based schemes in performance and latency. For example, 2 bits instead of 16 can be used to identify 4 protocols.
As for the field extraction, a naive adoption of crossbar seems a good idea. The behavior of header identification can be referred to as bit gather operation, and the behavior of field extraction can be referred to as bit scatter operation. Both operations can be realized by the crossbar circuit. Unfortunately, crossbar is not the best choice. Crossbar can achieve high performance when the timing violation isn't taken account. Crossbar consumes more power for its larger area. The key problem of crossbar is area. Its area complexity is big O n squared, which is unacceptable. A crossbar performs well in latency. In summary, crossbar consumes too much area, and we need better bit permutation network. We would like to introduce butterfly and inverse butterfly network into parser design. The two networks can realize the two operations as mentioned before, with high performance and modest power area and latency. As for performance, the two networks can achieve the same high performance as crossbar when they have the same clock frequency. In addition, the two networks can achieve a higher frequency for their simple structure. The two networks are more power efficient for its small area. The two networks have much smaller area than crossbar. The area complexity is big O n log n. They are achievable in modern chips. Their latency is higher than crossbar, but still modest. The complexity is big O log n. In our optimized ASIC implementation, the total latency is 17 clocks. In summary, the butterfly network and inverse butterfly network can achieve better area consumption with guaranteed performance, power, and latency. This is inverse butterfly network, and this is butterfly network. We would like to show the workflow of the two networks. For the bit gather operation, inverse butterfly network can realize it in 3 stages: first, second, and third. For the bit scatter operation, butterfly network also need 3 stages: first, second, and third. Okay, the architecture of hyperparser is concise. As shown in the figure, hyperparser is composed of the inverse butterfly network, the SRAM emulated TCAM, the butterfly network, and the configuration circuit. The inverse butterfly network extracts and gathers the protocol bits and transfers them to the SRAM emulated TCAM. Okay. The SRAM emulated TCAM identifies the protocol type and notifies the butterfly network. The butterfly network extracts the concerned fields and scatters them to the proper positions in the PHV. Okay, a wider bus can lead to higher throughput at the cost of lower bus efficiency. Segmentation can increase the bus efficiency at the cost of a more complex control logic. To achieve the balance point between the throughput and area, the bus format shown in the figure is adopted. The relation between the throughput and the inner bus can be found in the equation. We focus on the bus packet forwarding rate, which is measured in packets per second. The number 20 stands for the 20-byte Ethernet frame gap. Okay. Hyperparser is a programmable packet parser. It can support classic and new parse graphs. 4 classic parse graphs are used as a test case in the paper. As for ASIC implementation, industry standard 14 nanometer and 28 nanometer process are used to evaluate the PPAL. Sanofi's design compiler is used for a 1.45 gigahertz clock cycle target. This work is necessary to prove feasibility in meeting goals, such as timing and chip area, but we have not produced a complete design or actual silicon. As for FPGA implementation, 7 nanometer ACAP and 16 nanometer FPGA is used here. Xilinx Vivado is used for a 600 megahertz clock cycle target. We have deployed Hyperparser to the real-world FPGA evaluation board. Okay, Hyperparser is LUT-oriented. It can achieve a much better deployment time. It has fixed LUT locations, and parse graphs can change without synthesis tools involved. Okay. As shown in the figure, previous works leverage P4 codes as inputs to generate RTL codes, which is very fast, but the synthesis are needed to convert the RTL codes to the partial bit streams. This procedure may take tens of minutes. As for Hyperparser, the P4 codes can be converted to the LUT content in tens of seconds, thanks to the fixed positions and connections of the LUTs. LUT content can be converted to the partial bit stream in several seconds without synthesis tools involved. Okay. For ASIC implementation, Hyperparser can achieve 4 times better in performance, 6 times in power, and 30% better in area than the state-of-the-art. Hyperparser can achieve 12 nanosecond latency. Okay, for the FPGA implementation, Hyperparser can achieve better performance, area, and latency, but we can consider that it's more power consuming for its high frequency. Okay, now for the conclusion. Hyperparser is a high-performance programmable parser architecture. It supports 3.2 Tbps line rate with modest power, area, and latency. It supports ASIC and FPGA implementation. The FPGA implementation supports rapid deployment. We sincerely look forward to sharing our idea with the community, and the source code of Hyperparser has been released on GitHub. Thanks for your attention. I'd like to take any questions. Thank you.
Okay, thank you for the nice talk. And is there any question from the audience? Okay, if no, I have a question. My first question is that does parser support user-defined packet format?
Yes, it supports user-defined packet formats.
Okay, and my second question is about the scalability of hyperparser. And you mentioned that you have some parser graph. So how large a graph can be in hyperparser?
It's a good question. Okay. Okay, hyperparser can support for classic parse graph, but if the parse graph is much bigger, the hyperparser will consume more area, and the performance will be worse. But for classic parse graph is enough for the most situations.
Okay, and I think there is a question from the audience. Hi, and Lin, can you type in your question, or you can unmute and say your question.
Hello, Dr. Liu. May I ask you a question?
Hello. Okay.
Hello. I have a question about the butterfly network. In traditional packet switch, an input data frame are sent to the flow classification module, and the packet header is extracted. I just have a question about why a butterfly network is needed in front of the SRAM and TCAM classification module.
It's a good question. Because we adopt a bit selection strategy, and a lot of bits can be reduced to a small portion of them. For example, there are 16 bits in total, but we only need 2 of them to identify the 4 protocols. If we don't use bit selection strategy, we must use the total 16 bits.
Oh, okay, I understand.
Okay.
Is the function of the butterfly network similar as the crossbar?
Yes, but it's more area efficient.
Oh, okay. Thanks for your answer.
Okay, thank you.
And I have another question. And since the latency of the butterfly network is log n compared to O1 in XBAR, so does it mean that the latency will significantly increase as the scale of complexity of the protocol?
It's a good question. The latency of butterfly and inverse butterfly is O log n, but the n is buswise, and the n is up to 4,000 bits, and log n is up to 12. And we can optimize them, and we can use lice DFF register, and the latency can be better. So it will not result in significant problem.
Okay, thank you. Okay, if there's no question, let's move on to the second speaker. And the second speaker is Abhishek. He is now a PhD student at Indian Institute of Technology, Bombay. And he got his master's degree from Indian Institute of Technology, Delhi, and bachelor's degree from University of Calcutta. And he is currently working on programmable network and software-defined network. And now, hi, Abhishek, you may start now.
Yeah, hello.
Yes, I can hear you.
Okay. Okay. Can you see my screen?
Yeah.
Okay, thank you. Welcome everyone. My name is Abhijit Bose. I am a PhD student at Indian Institute of Technology, Bombay. Today, I will be happy to present our work titled Leveraging Programmable Data Plane for a High-Performance 5G User Plane Function. So, telecommunication network consists of three major components. First is the radio network, then core network, and the data network. The radio network consists of its user equipment, its base station, and the data network is essentially the external network like internet, and it is the responsibility of the telecommunication core network to relay user data between the radio network and the data network. So core network consists of two components, its control plane and the data plane. The control plane is responsible for handling user attachment, user management, authentication, etc. management jobs, and the data plane or user plane is responsible of actually forwarding user data between base station and the data network. So in traditional telecommunication network, this core network components were built as a dedicated hardware box, and those hardware boxes used to hold both control and data plane components together. So this approaches was not scalable, and also it was tough to upgrade due to the use of dedicated hardware components. So in modern 5G core network splits the control plane components from its data plane components to increase scalability. Also, it uses virtual network functions instead of dedicated hardware network devices to increase the flexibility. These virtual network functions are basically software-based network functions running over commodity server or cloud, and so they can scale easily. Such example of such network functions are AMF, which in control plane, which handles mobility, in 5G, which handles mobility, SMF, which handles station management, etc. And in 5G user plane, the only network function is the user plane function. This user plane function handles a lots of user data, and it also communicates with control plane to get the rules regarding how to handle those data. So we have already said that using virtual network functions increases the scalability and remove the necessity of specialized hardware. But when it comes to user-based function, which requires to handle a lot of data, traditional virtual network functions running over Linux kernel like slow network stack becomes bottleneck. So in this work, we primarily focused on this user plane function. So here are the use cases, the diverse category of use cases 5G is supposed to cover, like high throughput application like video streaming, very low latency requiring application like self-driving autonomous cars, and on top of that, low cost like providing internet service at villages. So we need to think how to provide these strict user spaces in the diverse category of strict user spaces using virtual network functions at 5G data plane or user plane. Means we are interchangingly using the data plane and user plane. So nowadays, most of the industry level user plane functions are built using high performance network stack like kernel bypass stack, like GPDK stack. And researchers have also offloaded some of the user plane components to programmable networks. For example, Kalum and Mavenir has offloaded the data forwarding part to programmable NIC. Kalum has also offloaded incoming RAID verification of data packets to programmable NIC. However, the existing research lacks an approach to find what all the UPF functionalities should be offloaded and what is their pros and cons, and also they lack a comparison between all the offload designs. So in this work, we we started with the software-based, pure software GPDK-based UPF, and we successively offloaded UPF feature to programmable NIC. First, we offloaded the feature of tiering particular user packet to particular core to programmable NIC. Then we offloaded the data forwarding, and finally we offloaded the control plane communication to programmable NIC. And altogether we came up with 4 prototypes, and we compare their performance in terms of throughput, latency, cost, and power efficiency. And we also shown what are the challenges arises from offloading. We have shown that offloading some components has reduced the efficiency of other components. And finally, our last design is a preliminary design of comprehensive offloaded UPF, which is supposed to answer the challenges that are arising from offloading. So before going to our designs, I will quickly give an overview on the 5G UPF functionalities and programmable data plane. So when a user comes to the 5G network, before sending any data, user attaches itself to the 5G network and establish session. During the attachment and session establishment, control plane verifies control plane network function verifies the user authenticated and installs session rules to the user plane function. Then when the user sends data, the incoming data comes to user plane function, and user plane function matches those data against the session rule. If a session rule found, then the packet is handled according to the session rule, like forward, buffer, or drop. If a session matching not found, the packet is completely dropped. Also, 5G uses GTP tunneling between the base station and UPF for increased mobility. So for uplink packets, the GTP encapsulated packets are decapsulated at UPF, and for downlink packets, it is GTP, the UPF to the GTP encapsulation. So during GTP encapsulation, the entire user packet is encapsulated using inside a GTP header followed by an outer IP and outer UDP header. UPF also do quality of service enforcement, like it checks the incoming packets against the maximum allowed bit rate for the session. It also do some policy control and charging. So overall, UPF needs to do a lot of function, and they need to handle data at a very high rate. So performance of the UPF is very critical for the 5G success. So here is a quick overview of programmable data plane. Modern programmable data plane network devices allow programming their data plane using high-level languages like P4. Using P4, we can define custom packet header format, custom packet parser, and custom match action pipeline. And the match action rules in the match action table can be dynamically uploaded using P4 runtime or other APIs by offloading some of the. This allows the researchers to offload some of the programming logic to programmable data plane, and researchers have shown that such offloading has improved performance of several applications. However, offloading has its own limitation, like a limited expressiveness of P4 programming language, limited memory, or limited resources in the programmable network devices. So often intelligent offloading techniques required to get the most benefit. So this is our test-based setup. We used three server with Intel Xenon CPU and programmable NIC. Server 1 hosted the load generator and control plane on all other control plane in it, and server 2 hosted the user plane function, and some of which is offloaded to the NIC based on our design, and server 3 holds a sink and a download link traffic generator. So our load generator was a DPDK based load generator which emulates the user and the base station. So here is our first pure software based UPF design. In this design, a set of dedicated codes called master code continuously poll the NIC. So when packet receives this master code, forward this packet to worker code using lockless DPDK structure. So we used separate worker codes for control plane and data plane processing. So the master code used some hash-based simple algorithm to steer particular UE packet to particular code. In this, the worker codes matches those packets against the established session, do the GTP encapsulation, decapsulation, QA forwarding, buffering, etc., and send back the reply for control plane packet or whatever the action it is. So this design is scalable. The only cons is that this all the functionalities here is done by the CPU code, so cost is high. So in our next design, we offloaded the packet steering, means steering particular UE packets to particular code to programmable NIC. So first one point here has to mention that normal NIC, that non-programmable NIC also have RSS support, but an ordinary RSS cannot forward individual user packet to individual code, because ordinary RSS is done on TCP IP headers, the outer TCP IP headers, but here the user packets and all user information are encapsulated inside the GTP header. So, ordinary RSS cannot do it. We use programmable NIC to parse user identifier and redirect traffic to user specific code. So here is the throughput and latency. Here is the throughput and latency for comparison for software UPF versus steering offloaded packet steering offloaded UPF. We have shown for three different packet size. This iMix is a typically mix we found in internet traffic. So we found that 45% higher throughput and up to 45% higher throughput and 37% lower latency in the steer offloaded design compared to the software pure software design. So now the question is software offloading packet steering always good, or it has some cons? So to study that, we studied how to design scaling on increasing loads. So when loads start increasing at this point, so software UPF, the master code detects the load and starts spawning new worker codes, and slowly the throughput has increased in the software UPF without any downtime. However, the steer offload design cannot increase the number of codes without a NIC restart. So we can see that due to the NIC restart, there is a downtime. So the steer offloaded design is tough to scale. We have seen almost 500 millisecond time has spent for this dynamic scaling. Next experiment we have done is with a single heavy hitter UE. Bursty traffic is very common in telecommunication network. So we have taken one bursty UE along with some non-bursty uniform traffic UE. So the bursty traffic UE suddenly started sending bursty traffic at this point. So we have seen in both software UPF and steer offloaded UPF a sudden increase in the latency. But the software UPF quickly redistributed the UE among all other user codes. But the steer offloaded UPF do not have such a design. So the latency of the heavy hitter UE remains high for the steer offloaded UPF. So our conclusion is tier offload is not suitable under dynamic and queued workload. So in the next design, we offloaded the entire session rule matching, GCP encapsulation, decapsulation, and RAID verification to programmable NIC. So in this design, the control plane packets are again processed by the user space. After processing the control plane packet, the user space communicates the session rules with programmable NIC using a controller and a API. So once the rule is installed, incoming data packets are directly matched at the NIC against the session. And if a matching is found, NIC, the NIC directly do the GCP decapsulation encapsulation. The NIC also do a RAID verification of the incoming packet. So if the incoming packets rates are under the allowed rate by the session, the packets are directly forwarded. But if the rate is higher than the allowed rate, then those packets are forwarded to user space for queuing and other operations due to lack of resources in the data plane and for other reasons. So here is the performance we got for software UPF and data plane offloaded UPF. So we have measured the end-to-end latency for both the design, and we found up to 24% lower latency in the data plane offloaded UPF. Now, data plane, we found that only data plane offloaded UPF also has its side effects. Like we already said that in data plane offloaded UPF, the control plane packets are processed by the user space. So after processing the control plane packet, user space communicates with the programmable NIC to install the session rules. And we found that the communication between the user space application, user space UPF part and the NIC become the bottleneck when there is a high control plane traffic. So we measured the control plane traffic throughput, means control plane communication traffic throughput for software UPF and data plane offloaded UPF. We found a huge reduction in throughput and increase in latency in the data plane offloaded UPF compared to the software UPF. So we found 86% lower control plane throughput and 15x higher control plane latency. So to solve this problem, we offloaded the entire control plane signaling message processing and rule installation directly to the hardware. So now the packets are directly processed to the rules and in our solution, and the rules are installed at the hardware itself. But there are challenges to do so. The primary challenges is the nature of the control plane traffic. Traffics are very complex, and they include arbitrary size of length header and recursive header structure. So in this implementation, we took a strict assumption of fixed packet format, and with those strict assumption of fixed packet format, we install the session rules into the data plane register and directly process the control plane traffic from the control plane communication traffic from programmable NIC. So here is the performance of the three models for control plane signaling messages. So we have seen that a control plane offloaded design has very high throughput compared to both of the designs. Very high control plane signaling messaging throughput compared to both of the design, and have a lower control plane processing latency compared to both of the designs. So here is a summary of UPF. So we established the point that UPF optimization is critical for 5G success. Offloading UPF functionalities to programmable hardware improve performance but decreases flexibility. So we came up with 4 different models, and we have shown their pros and cons. Offloading data plane forwarding alone, we have established that offloading data plane forwarding alone has the capacity of processing signaling messages that configure forwarding rules. So as a future work, we will try to develop a comprehensive UPF design, which prototype we have already built and shown here, but we've taken many assumptions. So without assumption, we want to build the full control plane offloaded and comprehensive UPF design. So thank you, and that's it for today. Asking for questions.
Okay, thank you for the nice talk. Is there any question from the audience? Okay, I have a question. What about the resource overhead of offloading? In particular, you may know that programmable devices are also used for other general functionalities. So if your offloading consumes too much resources, it may degrade the performance of other functionalities. So what about the resource usage?
Yeah, if we this is a good question. If we offload too much, all the functionalities to programmable networks, programmable devices, they may overflow the capacity. And we also observe this effect. If we offload all the user data 5G network, 5G UPF may support to programmable data plane, the single device may overwhelm and exhaust its capacity. So we in the future work, we are trying to address this issue. There are two approaches. One approach is to splitting the states between multiple network switches. So that is one approach, and second approach is using some techniques to detect which users need critical performance and offload only those users to network data plane, and that can also be done dynamically. So this part is not yet done. This is our future work.
Okay, thank you. And another question is that I find that in this paper, you mainly consider programmable NICs or smart NICs. And if we consider programmable switches, does your conclusion still hold, or is there anything different?
We believe the conclusion will be still hold, but the design will, the experimental setup will be little bit changed. Let me come to the setup. Yeah, the setup will be little bit changed. In that case, this box will go outside this server, and it will be somewhere outside. So maybe there may be additional latency for communication between this server and that switch, but that communication will be there even if we not use programmable switch and we use a normal switch there. So that will be neutralized. So I believe the conclusion done here will still hold.
Okay. Does the performance of control plane offloading will be affected?
Sorry, can you this?
Is the performance of control plane offloading affected if we use programmable switches?
Okay, if we use programmable switches, again the mechanism will be same. Like the programmable NIC, this user space UPF has to, if we only use the data plane offload design, then this user space UPF again has to communicate with the switch which is then situated outside this server. Maybe in that case there may be additional more latency in control plane communication for the data plane offloaded design. But once the control plane is also offloaded, then that issue will not be there.
Okay, thank you. Okay, if there's no other question, and let's thank our speaker again, and we will move to the final talk in this session. And the final speaker.
Yeah, thank you.
Okay, thank you. And the final speaker, Fangping Lan, she received her bachelor degree in Changshu Institute of Technology in China, and she also received her master degree from Monmouth University in United States this year. And start from this September, she will be a PhD student at Temple University. Now let's move on to Fanping, and Fanping, you may start now.
Okay. Oh, sorry. Can you see my slide?
Yeah, I can see your slide.
Yes, thank you. And hello, everyone. My name is Fanping Lan, and I'm very happy to be here to have a talk. And I'm going to beginning my PhD student at Temple University in 2 months. And this is my first serious talk, so I am very excited. And our topic is flexible routing with policy exchange. And the paper authors are my partner Bing Gui, and I, and my advisor, Professor Andrew Wang, and I am the presenter. Okay, first, what is the flexible routing? The goal of the flexible routing is making participants happy. On the global internet, every participating network has their own concern, and the flexible routing schema is capable of accommodating the diverse needs of individual participants. That's flexibility. And there are 3 roles in the policy control: sender, receiver, and transit. Ideally, the final policy control is that the sender, receiver, and transit both can control traffic transmission in the network. If we want to make more flexible routing on the internet, these 3 roles should be able to control the traffic transmission. And our goal is making routing more flexible. And on the internet, there are many networks play different roles. And they also contain different components that exist in a competing relationship. This is because on the one hand, every component wants to be as independent as possible. And on the other hand, these components must be cooperated with each other to do something, such as path selection. However, the independence may be more expensive in the traffic transmission due to the no concerns with cost information from others. And if no coordination, the selected path might be worse for most components. Therefore, how to balance the independence and the coordination on the internet is critical. And our problem state is how we can achieve flexible routing on the internet with these 2 competing goals. And in the next 2 slides, I will introduce several current existing solutions. And first is the well-known protocol, BGP. It prioritizes individual independence and tolerates routing inflexibility and refrains from remote coordination. But coordination is needed so that there are many BGP alternatives appear, such as source routing, multiple path routing, and overlay routing. And these 3 alternatives, they are trying to relax some aspects of BGP as the means to achieve better flexibility and the means of to satisfy more policy requests and make more participants happy. Although every BGP alternatives improve the flexibility of BGP, and there are extra costs and they are not ideal, that they didn't really achieve maximal flexibility. So we are going to introduce a principle to categorize in the next few slides. No matter BGP or BGP alternatives, we think they are not flexible enough. We want to find a sweet spot between independence and coordination. But we are not thinking a predefined single solution that works for everyone best. Instead, we want to find a dynamic point based on the information change. So what is the best fitting adjustment? So far, we are talking about the flexibility, but we didn't really characterize and we didn't precisely define what we mean the flexibility. In fact, to our best knowledge, there is no formal definition of flexibility. So here is our characterization of flexibility. It is permit a policy as long as it's possible. The possible means as long as the realization of policy doesn't harm other policies, then this policy can be achieved. And this is our definition, and this is also our principle. Now we have this formal definition and this principle, but the principle itself is still pretty abstract. How to use this principle in practice? And I will show you the two examples. And these two, there are two counterexamples show that if you don't want to follow this principle, what will happen? And this is the first counterexample. And this figure is the graph of topology. Each node is the network or autonomous system, AS. And there are 4 ACs. And here, our concern is how to allow AS0 and AS3 to satisfy their policies. AS3's policies is that they want to deliver traffic to D1 to go through the most preferred provider, AS2. And the AS0's policy, they want to balance the traffic to D1 and D2. And policy 0 and policy 3 can be satisfiable because there is the path 3 to 0 exists. These paths can meet the requirements of these two policies. However, if the policy 0 make a wrong implementation that instructs D2, D1 use the link 1-0, and then the D2 must be used the link 2-0. That will cause the policy 3 cannot be matched. And how can we fix this issue? And we can use the policy exchange. The P3 need to expose its information to the node 1 and node 2, and the node 1 and node 2 need to further propagate the P3's information to the node 0. Then the node 0 can make a right decision. The second counterexample, it is also a topology. Here, node 1 and node 2, their policy is fixed, and they order some delivery services. And node 5, 6, 7, they request some delivery services. And the tricky part here is how a transit node 3 best match the request and the services offered. And all policies are jointly satisfiable only if the P3 make a proper decision. And the critical thing is how P3 can make a good match, can make a good decision. Only if P3 have the way to learn its neighbors' concerns, its neighbors, including node 5, 6, 7, also including the node 1 and 2. Then our goal is to allow any legitimate policy. And we also observed that the most of failure cases that cannot meet the policy requirements are blindly making a decision. Therefore, our approach is exchanging necessary policies. We only make informed decision and only expose minimal policy information. And this slide shows our policy exchange protocol. And this algorithm is similar with this distance vector protocol. And the main difference between these two protocols is that our protocol is exchanging policy information, and the distance vector protocol is exchanging the routing information. And now let me show you the example to represent how our protocol works without jumping into the details of the protocol algorithm. And this protocol is same with counter example 2, and we will focus on 3 nodes, nodes 3, 5, and 6. Because nodes 5 and 6 request something, and the node 3 should make a right decision. They are the key points of this policy exchange example, and we are not going to the rest nodes of the policy due to the time concern. But if you are interested in, you can find detail in our paper. And these 3 policies, P3, P5, P6, has initial state. At first, the P3 is unconditional delivery state. P5 is secure delivery state. P6 is fast delivery state. And then the node 5 will send a request to the node 3 that they want to use the secure delivery for D, and the node 3 receives this request, and this will cause the P3 change their state from the unconditional state to the secure delivery state. Then also the node 6 also will send their request, its request to the node 3 that they want to fast delivery service. And now at this point, node 3 receives 2 complete requests. Then in order to fix this complete situation, node 3 introduced a cost tag that charging 1 unit for fast delivery, denoted by fast1, and charging 2 units for secure delivery, denoted by security 2. And the node 3 will send this information to the node 5, 6, and then the node 5 receives this offer from the node 3, and they only accept this offer because there is no other available providers. So the policy 5 will change their state to the secure 2, and However, the Node 6 will reject this offer from the Node 3 because they have a free offer from the Node 4. So they will send the information, send the rejection information to the Node 3 and send the acceptance information to the Node 4. And finally, the policy 6 will keep the fast state, and the policy 3 will finally converge to the secure 2. And this is our progress of policy exchange protocol. So far, I have shown you the concept of our policy exchange protocol and how to operate. Actually, how do we implement it? We need to address two challenges here. One is policy representation, and another one is policy exchange computational. And we have preliminary implementation in these two challenges. For the policy representation, we cannot find a policy entity in policy where routing scammers such as BGP or BGP alternatives. They embed policies in the decision process. So we create a novel way that use conditional table to represent policies. Conditional table is a regular database table with variables and additional conditions over those variables. And table TP here is an example policy conditional table that represents the shortest path policy with two neighbors. This table has two abstracts, flag and path, and the attribute flag shows whether a path is flagged or not. And R is a constant value. That means the candidate routes. And the B is also the constant value. That means the best routes. And the attribute path specifies the path itself, and the X, Y are the variables that they are unknown paths at this moment. The third tuple means path X will be selected as the best route, as the best path, as long as it's shorter than other alternative, which is represented by variable Y. And these variables, X and Y, depending on the instantiation of these variables, they can correspond to different state of the network routes. And as the example, I am going to show you two possible instances, and the presented as I1 and I2. And you can see the I1 and I2 are the regular tables, and they are concrete instances of all possible states produced by table TP. And an advantage of conditional table is that we can implement our protocol by SIGCOMM operation. We also evaluated our protocol in two aspects. One is performance, evaluated by computation table on the realistic topology. And another one is effectiveness, evaluated by synthetic policy. And the result of our protocol is reasonable and expected. Here this slide shows the policy exchange performance, and we implemented the merging function. And we also generated two realistic network topologies. One is rocket field topology, and another one is the topology inferred from BGP route field traces. And we can see in this figure is the CDF figure, plots the processing time of merging function on these two realistic topologies. As expected, the merging function runs fast in two topologies, both less than 8 microseconds. And this slide shows the effectiveness policy realization. And in this table, PS is the percentage of the node labeled as the secure router, like the node 1 here. And it also can a secure router also can be considered as the firewalls in the network. So the percentage, the PS, our intuition is that the more firewall in the network, which is implicated by the PS here, and the more likely we want to, the more likely we are able to jointly satisfy 3 requests. And the PS increases from 0.01 to 0.5. And the probability of satisfying all 3 policies increases from 0.35% to the 51%. And there are 3 related works, and also the special cases. And in fact, we are like to see how we can use policy exchange framework to implement these special cases. And for declarative networking, we share database usages in networking and introduce a novel use of conditional tables. And to our best knowledge, we are the first to use the conditional tables to do such implementation. And in this paper, we only represent the shortest path policy with conditional tables. So our future work wants to represent more realistic policies, such as existing BGP policies for IXPs, and SDN policies, and so on. And we also want to build a native implementation in the relational databases with support for large tables and extremely efficient indexing maintenance that can make more possible to represent realistic policies. And that's all. Thank you. Now I'm happy to take questions.
Okay, thank you. And is there any question from the audience? Okay, I may have a question. My question is about the convergence of your algorithm, and in particular, when the network scale increases. So, can your algorithm achieve very fast convergence, or is there any theoretical results about the convergence?
You mean this one?
Yeah, I mean, how long does your algorithm reach stable? If, for example, if we want to add a new policy.
It depends on the policy compatibility. If the simple policy, such as the shortest path policy, they will be very fast. But the specific experiment data, I'm not very familiar with it, because the experiment is I didn't do the experiments. But in our ongoing work, we use the conditional table to build up a real BGP route view real file, and they want to they execute SQL operation to how to sorry if the in our going work for the conditional table, we represent the one policy. But the specific, I have I cannot remind my memory, but the running time is very fast. Under the 100,000 tuples in the databases, less than 1 second. So it is also the fast execution time. I don't know.
Okay, thank you very much. Okay, and if there are no other questions, I think we may end this session. And let's thank all 3 speakers again. And okay, let's we can terminate now.
Okay, thank you very much. It's a little bit over time, so let's have a short break of 3 minutes and come back at 4:25 for the next session. Welcome back. So today's last session is on industrial spotlight. I will now give the microphone to Professor Xu.
Sure. Welcome back again. My name is Chenren Xu from Peking University, and I'm super excited to chair this industrial spotlight talk session. And in this session, we will have 3 very exciting talks from Alibaba, Microsoft Research, and Tencent. And first, let me introduce our first presenter, Yunfei Ma. So Yunfei is currently a researcher at XG Lab in the Alibaba Damo Academy. Before joining Alibaba, he was a postdoc researcher at MIT Media Lab. His research explores and develops wireless technology that extends human and computer abilities in sensing, communication, and actuation. He got his PhD from Cornell University and bachelor degree from USTC. In recent years, he has published more than 10 papers on top CS conference, including SIGCOMM, MobiCom, and NSDI. His research has been covered by media outlets, including BBC, The Verge, MIT Technology Review, and IEEE Spectrum. Now, Yunfei, could you share your screen?
Okay. Hi, Chenren. Can you hear me?
Yep.
Okay. I will try to share my screen. Yeah, I think I may have a problem in sharing. Let me see. I will try again. Now I think this time it works.
Chuling, have you opened all your? Okay. Oh, great.
So you can see my screen, right?
Right.
I will try. Am I in the main mode or in the presenter mode?
In the presenter mode. Now we can see the full screen of your slides.
You can see the full screen of the slides, right?
Right, not the script.
Oh, not the script. Okay, sounds good. Hello everyone. My name is Yunfei. I'm from the XG Lab in the Alibaba Damo Academy. It's my great pleasure to give this talk at APNet 21. And today, my topic is X-Link, the Alibaba's multipass quick protocol. So now let's start. So first of all, for those of you who may not be familiar with XG Lab, XG Lab is one of the 14 labs in Damo Academy. It is founded for the purpose of collaborative innovation of the next generation network communication technology and application. And at XG Lab, we focus on developing core technologies and products such as 5G private network, mobile network transport protocols, video codecs, and innovative 5G application. And we are very closely related to Ali Cloud. And by applying 5G technology to the cloud ecosystem, XG aims to deliver innovative and immersive experiences and services to enterprise and consumers in scenarios such as industrial IoT, smart transportation, smart healthcare, the new media and entertainment. And so if any of you are interested to learn more about XG Lab, and feel free to shoot me an email. And we are also hiring this year, so any applicant will be welcome. Now let's go back to our today's topic, X-Link. X-Link is the Alibaba's multipass transport solution developed by XG Lab and Taobao Technology. And the word X-Link is equal to X plus link, which is and X here is an unknown variable. The word X-Link represents a variable number of links running in parallel. So it could be 2 links, 3 links, 4 links, or more. So in theory, our protocol can support arbitrary number of links. And the X-Link implements our Alibaba's multipass quick IETF draft. Here is a link, and welcome to check it out.
And now we have updated our draft to version number 3, and any feedback of the draft will be appreciated. And on the implementation side, Xlink builds on top of the Xquick library, where Xquick is an internal IETF Quick library at Alibaba. And Xquick is also going to be open sourced by the end of this year. So the reason we built Xlink is that when we look at the Alibaba ecosystem, at the bottom, there are 2 pillars, AliCloud and Damo Academy, where AliCloud provides the infrastructure to the ecosystem, and Damo Academy provides the technology support. And at the center are the sellers and the buyers. And in order to support the sellers and buyers and to make it easy to do business everywhere, we build apps such as Taobao, Tmall, Youku, and DingTalk to facilitate the interaction between sellers and buyers. And these apps are also the interfaces of how our users interact mostly with us. And now we can see one big trend in all these apps. That is, when you open this app, you can see video is everywhere. Now let's take a Taobao as an example. So in the past, when you want to purchase something online, you went to Taobao.com, and what you got was just a web page. Now, things have changed. When people use mobile Taobao on their cell phones, and when you open the app in your cell phone, and almost every product is displayed by a short video. And according to the statistics, 96% of our consumers say that videos are incredibly helpful in helping them making their purchasing decisions. And the pandemic is further changing people's habits in viewing and buying. And in recent years, we have seen tremendous growth in Taobao Live video broadcasting. And many of the sellers on Taobao Live video broadcasting have even become internet celebrities like Li Jiaqi and Wei Ya. And in the past, June 18, last week, the GMV of Taobao Live video broadcasting passed the 2 billion yuan in just 1.5 hours. So as video becomes so important, and when we want to deliver a superior experience to our users, and we are forced to deal with the last mile connectivity problem. And I believe many of you have got the following experiences. So when you want to watch a video, it takes a while to load. So you feel that it's very uncomfortable. It's a slow start problem. Or when you see that your Wi-Fi signal at the top in your cell phone is all good, but the connection is mysteriously lost. Or when you are watching a video, and at the most exciting part, it suddenly stops due to very strong rebuffering events. So in fact, if a video freezes for more than 2 seconds, 25% of the audience is liable to leave. And this is also called the 2-second rule by Akamai. And what's our solution today to solve the last mile connectivity problem? The first type of solution is through FEC coding, such as Reed-Solomon, LT code, LDPC. And the second type is to try some optimization in the congestion control algorithm. For example, we have many congestion control, such as Cubic, BBR, GCC, or PCC. And the third type is to do some adaptive bitrate, for example, the MPC. And in recent years, we have also seen a lot of interest in machine learning-based approach, such as the Pensive. But those techniques can only optimize the network performance. What they cannot do is they cannot overcome the physical limitation. So if the connection is broken physically, and all this solution won't work. And on the network path, we just have so many components that may cause a failure, and the reasons are very, very diverse. It could be an ISP failure, or signal coverage issue, or just because of insufficient bandwidth. So the question is, how can we solve all these problems in one shot? And the opportunity is multipath transport. As today, most of our smart devices is equipped with many radio interfaces, like Wi-Fi and cellular. Therefore, if we can have a lightweight multipath transport protocol that can be easily used by our apps, then we can aggregate independent links for more bandwidth and also enhance our network robustness for our apps. And here, what I want to do is I want to reflect a little bit history of the multipath transport protocol. In fact, the first IETF draft was proposed by Christian Huitema, who also collaborates with us in our Alibaba multipath quick draft. This is done in as early as 1995. But at that time, the demand was not there either from the device side or from the application side. And in the year 2007, Mark Henley and his colleagues started working on the so-called MPTCP protocol. And MPTCP protocol became RFC in 2013. And in 2017, Apple Series started using MPTCP. And Honor smartphones introduced Link Turbo that utilized MPTCP in 2019. But overall, the adoption of multipath over the public internet is still quite slow. Apple perhaps has the largest deployment, but it is still limited to audio apps. And later we will see why this happens. And for video, large-scale and multipath deployment is not there yet, and we haven't seen rapid progress in recent years. To understand the reasons, there are really several issues with MPTCP. The first one is deployment difficulties. MPTCP requires a kernel support from both client and server side. It means that for app providers like Alibaba, it's really a big challenge to enable these features on smartphones that they have no control. On the other hand, for phone manufacturers, even though they have more control of the smartphone OS, they have no control of the application server end. As a result, enabling MPTCP from one end to the other end is not easy. So even if you have this feature, it does not mean that you can enjoy this feature at any time. The second problem is the middle box problems. MPTCP relies on this MP-capable option in TCP header, and middle boxes may remove these unknown TCP options from the TCP header. So when MPTCP tried to use this option to signal the support of multipath to its peer, it may be affected by such middle boxes. And when middle boxes come to interfere, MPTCP fall back to regular TCP. And the communication still works, but not with multipath anymore. And to prevent, this prevents users from enjoying this feature. And remember that in the world full of middle boxes, the negotiation between two parties becomes the negotiation of n parties. And to solve these problems, QUIC used end-to-end encryption, which can help a lot in this case. And later, I will also discuss why, how QUIC can help. And the third problem is that, in fact, different applications require different queues support. For example, for long video or high-resolution video like Youku, rebuffer is more critical. And in short video, in addition to the rebuffer rate, we also need to think about the startup speed. And in video conferencing, latency and reliability should be top prioritized. But MPTCP is in the kernel. So how to design a scheduling algorithm that can fit all of the different needs from different applications is also very challenging for multipath TCP. And all these issues can be addressed by extending QUIC to multipath. Again, a little bit history of QUIC for those who may not be very familiar. QUIC started as an internal project at Google in 2013, and the IETF working group of QUIC was formed in 2016. And at Alibaba, we start building our IETF QUIC library, XQuic, at 2018. And in the 2019, we begin the project of XLink. And this year, the 6 basic drafts of QUIC have become RFC. So what are the benefits of QUIC? First, QUIC is a user space protocol, meaning it can be integrated with application, so upgrade cycle can be easily controlled. Second, QUIC is fast. It reduces the 3 RTT handshake of TCP and TLS to just 1. QUIC also offers better performance via stream multiplexing. And as I just mentioned, QUIC is integrated with application. So it enables customized QoS support for application. For example, in QUIC, we can use different congestion control algorithm for each of our apps. And more importantly, Quick offer better security. In Quick, even the header is protected. And later we will see this will have a huge benefit when it comes to multipass. And the figure on the left shows how Xlink fit into the picture. At the top, we have application protocols such as H3, RTMP, RPC, and they utilize Quick as a transport layer. And one layer below, we implement Xlink as a multipass extension of Quick. And Xlink uses UDP to send and receive packets. In Xlink, we offer 3 modes of operation: aggregation, switching, and steering. Xlink is integrated and released with the apps, so it can cater for the different needs of different applications. No kernel changes are needed. So end-to-end deployment is much easier than MPTCP. This also creates the opportunity of accelerated innovations. For example, we can quickly experiment with Xlink. On the client side, the upgrade frequency is daily. On the server side, we can update the configuration hourly. And now I will give you a quick overview of Xlink multipass Quick protocol. So you can easily find our draft by typing Alibaba multipass Quick IETF in Google to check out the draft. So our protocol is designed with one simple goal. That is, we want to provide people who want to experiment with multipass with something simple to start. And we try to avoid making new concepts. So when you are having a functioning Quick, you should be easily to add this multipass extension to your code base. And to achieve this goal, we have made several key design points. First, we reuse as much as possible the mechanism of IETF Quick V1, the current Quick RFC. And in other words, Alibaba's multipass Quick is designed as a minimally scoped extension of Quick. Second, we are fully compliant with Quick invariants, and we use the same header formats as Quick V1. This makes sure that the middle boxes should not find any difference between a single pass Quick header and a multipass Quick header. And number 3, because we're dealing with multipasses, we need a path identifier. So in Quick, every packet includes a destination ID, and therefore it is natural to use the connection ID and the sequence number of the connection ID as a path identifier. And number 4, we separate the packet number space in each pass. Each pass is responsible for their own loss detection, and the loss detection algorithm is the same as a single pass Quick. Another good thing about the separate packet number space is that it prevents a lot of range holes in the acknowledgement. And number 5, we use the same one RTT key on different passes, so key exchange protocol does not need to change. And number 6, the congestion control, RTT measurement, PMTU discovery is done in per pass manner because they all belong to the properties of a specific pass. The first question is, how can we enable multipass in Quick? The multipass start as a single pass Quick, and the Quick handshake and the key exchange are all the same. The only thing you need to do is to add the transport parameter called enable multipass in client hello. And once the server sees this enable multipass in the client transport parameter in the client hello is 1, and the server will reply with enable multipass parameter in the extended encryption. And this parameter will also be set to 1. The middle boxes is unaware of the multipass negotiation because the transport parameter is completely encrypted. So this helps multipass Quick packet to traverse through the internet. So just recall that what I have mentioned in the MPTCP, because the MP capable option is exposed to middle boxes, so middle boxes can come to interfere. But in Quick, this enable multipass is completely encrypted. so middle boxes won't know multipass negotiation is happening. And the second question is, how can we initialize multipass? As I have just mentioned, multipass quick started as a single pass quick, but for different paths, we need to use different connection IDs to communicate. Therefore, the first step is to obtain new connection ID. And this is done with the help of the new connection ID frame defined in Quick V1. So the client, in this example, the client may choose to offer the server a new connection ID C1 to use. And the server, in return, offers the client two new CIDs, S1 and S2 to use. Then the client can start sending new packets on the new pass with the new CID S2 at the second pass. The reachability of the pass in different directions, however, also needs to be tested. And to test the reachability, we reuse the mechanism of Quick V1's connection migration. And this can be achieved using the pass challenge and pass response frame defined in Quick V1. And also notice that when multipass communication started, the ACK frame is replaced with the ACK MP frame. And for the ACK MP frame, the multipass ACK frame, there is only one small change to the ACK frame. We add the pass identifier to indicate the packets on which pass it acknowledges, since each pass now has its own packet number space. Also, the ACK MP doesn't need to return from the original pass. In MPTCP, ACK is always returned on the same pass, but in Quick, we have more flexibility. For example, you can choose to always send ACK MP on the shortest path, which also help boost the performance. And the next question is about packet protection. So for packet protection, in our draft, the general principles of packet protection are not changed for multipass Quick. No changes are needed for setting packet protection keys, the initial secret, header protection, the use of 0 RTT keys, receiving out of order protected packets, receiving protected packets, or the retry packet integrity. The use of multiple packet number space for 1 RTT packets, however, requires the changes in the AEAD nonce. As I have mentioned earlier, different passes they share the same 1 RTT key, so no change in the key negotiation process. But when using the same key, we must ensure that the nonce used in AEAD is unique for every packet. In Quick V1, the nonce is computed as an exclusive OR of the packet number and the initial vector. However, since the packet number space are now separated, that means there is a possible overlap between different passes on their packet number space. Therefore, the way we compute the nonce also needs to be modified. And in our proposal, here is how we construct the nonce. We take the 32 bits of the CID sequence number, 2 bits padding, and the 62 bits packet number to reconstruct a packet number. And then we compute the nonce by exclusive OR between the IV and this new packet number to obtain the nonce. And in this way, the uniqueness of the nonce is reassured. And the next question is, how can we manage multi-passes? It is also necessary to think about this because in multi-pass communication, different paths can have different status. Therefore, we introduced the path status frame. And this frame, the path status field, right now, we define 3 values: abandoned, 0, standby 1, and available 2. And later, I will explain how we use the path status frame when I want to close a path. And in order to close a path, what should we do? Remember the path status frame in the previous slides. So basically, the process of closing a path consists of 2 steps. The first step is to send out a path status frame with the status sent to abandon. And then the endpoint who receive the abandoned status frame will also reply, indicating that they both agree to abandon the path. Then the next step is to retire the CID with the retire connection ID frame. And the retire connection ID frame tells the receiving endpoint to release the corresponding resources for this particular connection ID. And now we are very close to having a working version of multipath quick protocol. I hope this process is not too complicated. And at this stage, however, we are not done. We still need to solve the biggest challenge in multipath, that is performance. And one may expect that multipath should achieve no worse performance than single path. Otherwise, we defeat our purpose. However, in reality, unfortunately, it is really not easy to get a good multipath performance. So the first thing we're trying to do is to build a vanilla multipath quick. And we test the vanilla, and in this vanilla multipath quick, we use the default Linux kernel min RTT scheduler. And we compare this vanilla multipath quick with single path quick by running a large-scale A/B test in Taobao. And this figure shows the video request completion time for video chunks where we capture the multipath quick and compare the performance with single path quick. And the vanilla multipath quick was only effective at times on the median and 90 percentile request completion time. The RTC was worse on days 1, day 3, day 4, and day 5, as can be seen in this figure. And the largest median RCT degradation was about 16%. And vanilla MP also always lead to degraded tail performance at 99 percentile RCT, which could be even 28% worse than single pass quick. And we found that the major problem was the multipath head offline blocking problem. As shown in this figure, in multipath transport, the path RTT difference could be very large in the wireless environment. So when the scheduler wants to send packets, it splits the packet across 2 passes. And what can happen is the packet sent earlier could end up arriving later. And this causes blocking at the receiving end. And this phenomenon also drags down the overall performance. And wireless scheduler that based on prediction won't work well because wireless environment is highly fluctuated. And one simple solution to solve this problem is to send duplicate packets as shown in this figure. However, the problem is that the redundant packets also means that the bandwidth or traffic cost is much higher. And especially in video application, the amount of traffic is very high. So we cannot afford to send redundant packets a lot. And indeed, in the past decades, there has been lots of research work on multipath scheduling. And so what I show here is some recent work on multipath scheduling, and I will put them in this coordinate. So what they do is they generally fall into 2 categories. The first category is along the x-axis where the performance is high, but the traffic overhead or the redundant packets, number of redundant packets is also high, which makes it difficult to deploy this solution at large-scale video services. The second category is along the y-axis, where the traffic overhead is low, which is good for large-scale deployment, but the performance is also low. So what we really need is a solution at the top right corner, which can achieve good performance with low cost simultaneously. And this is X-Link. In X-Link, we try to achieve the performance and optimize performance and cost at the same time. And in X-Link, we introduced the QE-driven multipath scheduling, which is the first multipath scheduler based on remote client-server feedback control. it consists of two parts. In the first part, we use reinjection to overcome multipass head of line blocking. And in the second part, we use a remote QE feedback to control the aggressiveness of this reinjection. The QE feedback contains information related to client's video buffer. The high-level idea is when the video buffer level is high, our reinjection can act conservatively, saving traffic costs. But when the buffer level is low, that means the network condition is poor, and our reinjection scheduler should become more aggressive to boost the performance. And to support this QE feedback, we also include our third extension frame, the QE control signal frame. And this frame is used to carry any desired QE signals to control the scheduler. And with such a design, the client and server can now work closely together to achieve the two design goals. The first one is the optimized QE performance. The second one is minimized overhead cost. And here, I show the dynamics of the video buffer level when one of the passes is fading. In the first figure, we show the pass trajectory of two passes. The second figure has no reinjection. So for the second figure, what happens is that the data is blocked with the sudden failure of a pass as shown in the first figure, the pass number 1. And this fading of a pass will cause the video buffer to run out of data, and hence the video stalls. And the figure on the lower left is reinjection without QE control. We can see that the reinjection is helpful, but it also incurs many unnecessary reinjection, which keeps increasing the traffic overhead. And the figure on the lower right is a reinjection with QE, and it uses reinjection only when it is necessary. So reinjection is turned on when pass 1 fades, but there is no reinjection after the pass 1 recovers, which allows us to balance the performance and cost. And in our experiment, with QE control, the redundancy rate is reduced from 15% to 2%. And here is a demo of how Xlink works. Xlink, so on the left is Xlink that uses Wi-Fi and LTE at the same time. And on the right side is a single pass QUIC with Wi-Fi. So as you can see, Xlink starts much quicker than the single pass QUIC. And also because of the unstable Wi-Fi environment, the single pass QUIC suffers from rebuffering. While in contrast, the Xlink with LTE and Wi-Fi running in parallel will be overcome this Wi-Fi failure. And in comparison, Xlink's playback is much smoother throughout the whole process. And we also run a large-scale A/B test in Taobao with 100K participants who upgraded to our test versions. Those participants were in the same geographical region where we formed two contrast groups and they ran in parallel. So on the client side is the Taobao mobile Android app, and on the server side is the Nginx Edge server. The application scenario is a user viewing short form video with or without multipass from Edge server. And this figure is the A/B test result of video chunk request time. And in contrast to the Min RTT scheduler, the vanilla multipass, which we saw previously, when we can see that the Xlink achieves a steady performance improvements of both median 95th% and 99th percentile. And the improvement of the 95th percentile ranges from 9.4% to 34%. And the improvement of the 99th percentile ranges from 19% to 50%. And we have also, we also shows the rebuffer rate improvement of X-Link over single pass quick. And in this figure, the rebuffer rate, which measures the video playback smoothness, is defined as the total amount of video rebuffer time normalized by the total amount of video play time. And in other words, the video rebuffer rate is calculated at the sum of rebuffer time divided by the sum of play time. So compared to single pass quick, we can see that X-Link consistently outperformed single pass in video rebuffer rate. And they observed the rebuffer rate reduction was significant, which ranges from 23% to 67%. And such a result was in accordance with the video request completion time shown in the previous slides. And this evaluation result shows that the X-Link was effective in improving the quality of user perceived experience in terms of video playback smoothness. And so in conclusion, in this talk, what I present is the X-Link, the Alibaba's multipass quick protocol. X-Link is designed as a simple extension. So we hope that people can use our extension and our draft to do more experiment with multipass. And in the X-Link draft, we only 3 extension frame is added. So we hope that we have made things as simple as possible. And also in X-Link, we add the support of QE feedback, which help us to overcome not only the multipass head-over blocking issue, but also to reduce the redundancy traffic cost. And remember that in order to deploy multipass for large-scale video services, cost and performance are the 2 key things. And with this QE support, we're able to balance the cost and performance at the same time. And thank you so much. And now I'm happy to take questions.
Okay, thank you, Yunfei, for giving us such a great protocol work talk. Must be a long journey behind it. Now, do we have any questions from the audience? Yeah, sure, please, Professor Xiaoming Fu. Go ahead.
Happy to hear this excellent talk. And I wonder the quick would be feasible for doing more than 3 or let's say 2, at least 2 paths. So did you check how when there are more than 2 paths, how the performance will getting worse or how this is going to happen? Yeah, in your experiments.
Okay, thanks, Professor Fu. Fu, right, Professor Fu. Thanks so much for this great question. And yeah, indeed, it's very important to think about extending quick to more than 2 passes. And currently, in the evaluation result, what we have done is we run Taobao mobile on cell phones. So we use 2 passes. But in theory, you can extend this to more than 2 passes. And actually, we have done some experiments in our test bed. And however, what I want to mention is that extending the number of multipass to 4 passes, you need a more careful design in the scheduling algorithm.
I just wonder because usually the protocol is optimized for 2, and when there's 3 or more, then your really system support and detecting the multiple presence of the path will take you additional energy. Yeah. Okay, thank you.
Do we have any other questions? Actually, I have one more question. So you mentioned MPTCP will encounter some middle box issue. Sometimes it will block your traffic, right? But for quick, have you ever encountered some mobile carrier will also limit the rate of your UDP traffic because quick is built on top of UDP, and then sometimes in some countries, some carrier will, when they observe a bursty traffic of UDP between a fixed pair of endpoints, and then they will detect and recognize it's belong to a malicious flow, and then do that. Have you ever seen that phenomenon?
So in our Taobao experiment, we haven't observed such phenomenon, but I think it is definitely possible that in some country there is such a limitation of the UDP traffic. But I think what is good now, and if you look at the trend, right, because Facebook has now a very wide deployment of Quick, and almost 75% of Facebook's internet traffic is now on Quick. So I think the situation will become much better because as Quick become the next generation transport protocol or the underlying protocol for HTTP3, right? So I think the carrier will also add more support for Quick. And also in addition, if you look at the Quick draft, there is something called a Quick invariant draft, which means that if you are compliant with Quick invariant draft, the middle boxes should not do anything or should not try to block your traffic, right? Because this is the part of the agreement of the internet. And also what I want to mention is that in this our Alibaba Multipass Quick extension, we're also fully compliant with the Quick version 1 invariant. So from the middle box perspective, you should not observe any difference between the multi-pass Quick and the single pass Quick.
Yeah, sure. I also agree the policy makers should adapt to the trend. Oh, we have one more question from Tong Li. Dr. Tong Li, yeah, please go ahead.
Okay, I want to ask a quick question about when we talk about multi-pass Quick, it seems we have two roadmaps of the multi-pass Quick. Another one is from the early 2018. Olivia, they proposed the multi-pass Quick. And I wonder what is the difference between the Alibaba's multi-pass Quick and the Olivia's one? And do you have any performance comparison between these two roadmaps? Thank you.
Yeah, thanks for this question. That's a really good question. And first of all, so the design philosophy of these two drafts are quite different if you look at the details of this draft. And we designed the multi-pass Quick more from the industry perspective, but not from the academia perspective, which means that, so what does industry people want, right? We want something that can reliably work and something that is very simple and something that won't break. So with that said, what you need to do is you need to simplify as much as possible. So in this draft, we design the Quick as a minimally scoped extension, which is agreed by most of the IETF member in the working group. And so this is I think the number one thing. And also, if you look at the Luwen's draft, what they do is they have the new concept called Uniflow, right? But whether or not you should have Uniflow is under heavily debate at the working group right now. And also on the performance part, right? So what I've mentioned is in order to achieve good performance, you really need the QE feedback to support the scheduler. And this is the new thing. I think this is the big change we have added to the past knowledge, because in the past knowledge, what you have is you have the client and the server, right? And the scheduler and the client, you don't talk to each other. So that causes many problems. For example, you cannot balance the performance and the cost at the same time. But with the QE support now, they can work hand in hand and they closely collaborate with each other to achieve superior performance. So that's the second major change of this draft.
Okay, thank you.
Okay, due to the time limits, let's thank the speaker again. Yongchang, are you here?
Yeah, I'm online.
Oh, cool. Can you share screen?
Okay, start to share. Where's it?
So while Yongchang is sharing his screen, let me introduce our second speaker. Dr. Yongchang Xiong is now with Networking Research Group at Microsoft Research Asia as a senior principal researcher and research manager. Dr. Xiong received his bachelor, master, and PhD degrees all from Tsinghua University, all in computer science. His research interests include system and networking, as well as network security, especially on the architecture design, optimal scheduling problem, switch construction to improve resilience, performance, and diagnosis, as well as its security problems, such as handling the DDoS attacks. He has published more than 80 papers in these areas. Today, he's going to talk about OpenNet Lab, an open networking platform for machine learning-based real-time communication. Let's welcome.
Yeah, thank you. Thank you, Professor Xu. And can you see my screen now?
Yep, perfectly.
Okay, hi everyone. I'm Yongchang from Networking Research Group, Microsoft Research Asia. Now I'm going to talk about the OpenNet Lab, the open platform for data-driven networking research. Actually, this is a community effort, including many professors and researchers in Asia-Pacific area. So today, I do the presentation on behalf of the whole ONL community. So in the past 20 years, we witnessed the rapid growth of networking applications in different scenarios, especially for real-time networking communications and conferencing. For example, the Zoom service that I'm currently using to do the presentation, Microsoft Teams, Google Hangouts, and of course, some popular domestic meeting tools such as Tencent Meeting or Alibaba Dingding. Also, the video on demand attracts a lot of attention, such as Netflix, Hulu, YouTube in the US, and China-based iQIYI, Bilibili, or Tencent Video. So recently, the live streaming traffic increases very fast. In addition to today's live streaming service, for example, Bilibili and YouTube, we are now using to broadcast today's presentation. There are quite a lot, many others, such as Twitch, Douyu, Huya, and YY. And it is said that the live streaming traffic will reach 17% of the total internet video traffic by 2022, according to Cisco's white paper. So, and we can see many of those popular networking applications require the property of real-time communications. And this becomes even more important during the COVID-19 pandemic. Since people need to keep social distance, as we are doing now for the remote online APNet 21 conference. In addition to the online conferences, we also see very rapid growth for online education and even online tomb sweeping. That's particularly helpful for many Chinese people. And this is the, we got some picture snapped from internet. However, the quality of service of real-time communications is still a big challenge, even after around 20 years of development. Here we show some of the statistics data from the real production. We classify the one-on-one core problems to different categories as illustrated in this table. We can see that the problems in dark blue color are highly related to a networking module. For example, the distorted audio accounts for 14.7% of the total problems, and its root cause are networking loss, jitter, and limited bandwidth, or bad bandwidth control. Similarly, the audio delay, video low quality, and video freezing problems are all highly related to the networking module. And this in total accounts for a near 30% of the total problems identified for the one-on-one calls. And moreover, there are around 41% of the poor calls are related to a networking module. And we illustrated them in the light blue in this table, such as no sound problem, or background noise, or acoustic echo. So in total, we have around 70% of the problems related to one course are highly or related to networking module. So that said, the networking module is one of the keys to the quality of service for real-time communications. However, the cost for the real-time communications is still a big challenge. So now let's take a deep dive of those modules in real-time communication software in industry. We illustrate it with two main popular RTC software. One is Google Web RTC, and the other one is Microsoft Teams. We can see that the RTC software has a very complicated modules from the camera at the sender side to the display at the receiver side, because it needs to decide many attributes related to networking properties, such as video audio sending rate, video audio framing rate, frame resolution, padding, and forward area correction, and so on, so forth. And obviously, such networking module interact a lot of other components with many other tools inside. The encoder, the pacer, the padder, the decoder, and the filter. So in the software architecture, we see the quite complex module diagram in both software. So besides the industry efforts, there are lots of literature work, research in this area in academia, in the area of video streaming. For example, the perceived work from MIT. And this morning, Professor Junchen Jiang presented his insightful perception-driven optimization research work, such as Sensei, a work that'll be published in this year's NSDI. Both adopted so-called data-driven approach to do the optimization. And this actually already happened in networking congestion control area that takes advantage of the machine learning to automatically tune the networking protocol. Many of them use the supervised learning, while in the recent years, we also see attention paid to the reinforcement learning to solve the congestion control, since they share lots of similarities on states, action, and reward nature. So, but from the research to the practical networking systems, there are a number of challenges to be addressed. First, we see different behavior from newly emerging devices and platforms. For example, the mobile devices are the dominating video consumers nowadays, and the different mobile operating systems and different smartphones have quite different consumption, computation resource, scheduling, and power management policy, which will affect the final quality of experience a lot in the real scenarios. Secondly, the application behavior become more and more complicated. For example, the RDC applications now includes more and more features such as slides presentation, file uploading, screen sharing, whiteboard collaboration, and different applications compete each other. The video traffic competes with audio as well. And the networking environment is also becoming more and more complicated. For delay and loss variance, the Wi-Fi network, the Wi-Fi network is quite different from 5G and 4G mobile network, and the 6G is already on the way. And different ISPs may have quite different policy, which result in different behavior for the networking services. For example, the ISPs may shape the traffic and even do the policing in some segments where the user traffic triggers some predefined rules. This situation becomes more sophisticated when we consider the consider different congestion control or different application interfering traffics, or even some non-deterministic gateway behavior, such as random packet loss from some well-known firewalls. To address these networking challenges, we need heterogeneous devices, such as personal computer, mobile phone, and pad, etc. And we also need some of the real applications to be deployed so as to capture and identify the real application behavior. And of course, we need the distributed nodes located in heterogeneous networks. All of these are not easily to be solved by any individuals. So a public infrastructure by commodity is necessary. So this leads to the joint efforts of OpenNet Lab, the next generation platform for open and practical networking research by the whole OpenNet Lab community. So the OpenNet Lab community is not owned or controlled by any single participating org. The current rotating chair is Professor Chen Tian from Nanjing University, while Professor Kai Guibian is the co-author from Peking University. We also have many other professors from around the world. And we also have Professor Feng Yuan from Tsinghua University and Lanzhou University, and Professor Bing Sheng, and many other professors, and Henry Xu from domestic China area, and Henry Xu from CUHK China. In addition, the ONL community has a number of researchers, architects, designers, and most importantly, the developers who are now actively contributing to the society. For ONL, the OpenNet Lab would be the three keywords. So the major goal of the ONL is to build the next generation platform for open and practical networking research. It needs to be open to the whole networking research society, and it consists of different types of networking in the wild, including a wide network, campus network, cloud network, and wireless network, Wi-Fi 5 or Wi-Fi 6, and mobile network, including a 3, 4, 5, and even the potential 6G. For lab keywords, we need to be real, including the real applications, such as the real full-stack RTC applications, such as Google's WebRTC or Microsoft Teams, real browser-based applications, for example, the Chrome or Edge-based browser-based video streaming, and different internet connection control, such as well as some of the customized applications. Also, it has it need to have heterogeneous nodes, such as virtual machine, physical machine, desktop, laptop, smartphone, and so on and so forth. The highlight of the in addition to the heterogeneous nodes and networking environment, the highlight or the uniqueness of the ONL is to enable data-centric research for machine learning-based networking, as illustrated in this figure on the right. For the ONL job, the ONL platform can automatically generate the data, collect the data, store the data in the cloud, and do the data aggregation, filter, and do the analytics for the data, and finally share the data out as the common data set, so that we can contribute to the research community. We also provide a set of open source toolkits, in particular, the simulation, the gym, the environment that are very essential for the reinforcement learning based training for real applications. Of course, the platform itself is free to networking research community, and the data set itself will be published on GitHub for researchers to reproduce and the experiments and train the models accordingly. Here's the brief diagram for the ONL system architecture. Basically, it is a microservice based with many management services running on the cloud, including user management, development, deployment agent, health agent, job agent, as well as the database. The microservices are quite flexible. Currently, we use the Azure Kubernetes service with RESTful API interface, while it is quite easy to port to other Kubernetes platforms such as AWS or Google. We also provide the front door service to automatically authenticate the ONL user and provide storage and database using Azure SQL database. Currently, ONL nodes support different networking interfaces, including Ethernet, Wi-Fi, 4G, 5G, and support different operating systems such as Windows or Linux. And the mobile operating systems such as Android support is ongoing. By far, with all members' great help and contribution, we have already finished the first stage platform building in 7 cities, mainly in East Asia. We have already finished 6 nodes in Beijing, 8 nodes in Nanjing, 5 nodes in Lanzhou, 1 node in Singapore, and 6 nodes in Korea. And we are building more and doing more research based on such OL platform. So the first low-hanging fruit research we like to conduct on OpenNet Lab is to compare and verify different congestion control algorithms in the real networking platforms, just like what Pantheon did previously by our team member Francis Yan. As we know that in a networking research area, almost every emerging TCP congestion control algorithm claims to be the state of art when they publish the paper or release the results. However, it is hard to compare and verify them in the common ground. For example, for those papers or solutions, they may just compare with another algorithm that they picked, or they evaluate on their own testbeds, or with some simulators or emulators with their own settings. Based on the specific results that they collected, they claim that they're the sort of work. Actually, Pantheon from Francis Yan can provide the training ground by regularly run all the congestion control schemes with the same common testbed. Here's the illustration that we'd like to reproduce and compare those different congestion control algorithms in the different real networks and with real applications and different devices. Therefore, the OpenNet Lab can provide the congestion control benchmarks between nodes across the world, even after the end of the support of Pantheon running in Stanford. Next, I'd like to use some slides to introduce our work on the R3Net, a reinforcement learning based real-time communication solution on OpenNet Lab. First, as I just mentioned at the beginning of this talk, there are quite a lot of challenges for current RTC real-time communication systems, and I will show you how hard it is to improve in the real, according to our real experience from real RTC products. First, for RTC system, one of the most crucial components is the bandwidth estimation. But this technology currently used in production is over 10 years old. And it is very hard job to optimize the, for example, the common filter used in the system, since it includes almost hundreds of heuristics and thousands of different parameters that are some correlated and dependent between themselves and other components. Therefore, it requires both networking experts and video audio codec experts working together to manually fine-tune those parameters. Naturally to say, there are so many, thousands of parameters to be tuned. Moreover, the code base is extremely hard to maintain. For example, as illustrated in this figure, the green blocks consist of over 150,000 lines of code. You can imagine how hard it is to maintain. Needless to say that we also need to be future-proof. That means we need to make the system adaptive to the emerging and future device and networking environment. For example, some parameters in unsent common filter algorithms are tuned based on the old networking conditions, where we still, at that time, we still use ADSL or 3G mobile networks. Obviously, we need to tune them again for the new networks accordingly. So actually, we once tried to refactor and improve the old code base, but failed. That try actually took us several months for revising the code. And the new version worked quite well in the simulator environment, but sometimes behaved quite badly in the real network. And this is totally unacceptable for the real production. So therefore, we propose a data-driven approach, which we also call it Software 2.0, which we leverage the deep reinforcement learning technique for real-time communications. The idea is very simple. We can see from this figure, reinforcement learning module will replace all bandwidth control components to achieve simpler architecture by removing the hard-coded rules and automatically and automatically tune parameters even for new networking devices. The advantage of the new approach is huge. The architecture is much simpler because there's no hard-coded rules any longer, and everything is automatically tuned based on the data and trace. And it needs much less domain expertise and knowledge to tune the algorithms. And it is easier to support newly networking and device because we only need just to retrain the system using the new data and trace in the new environment. However, there are so many lines of code to be replaced. So we have to replace it step by step. And it would be better to start with a small step and build a reinforcement learning-based bandwidth. Currently, we build the reinforcement learning-based bandwidth estimator first. And later on, we will replace all other components with data-driven modules. So here's the diagram of our solution called APNet. That is a reinforcement learning-based recurrent network. So it consists of the 3 parts: the states, including the RTT, delay or delay jitter, loss rate, and throughput, and many other networking properties. And to estimate the bandwidth, and we run the system in the G environment or in the real networking. And based on the client-side network and video measurement, it will get the reward. So we already deployed the APNet in the real production and got continuous improvement for different scenarios. This figure shows a frustrated bandwidth scenario. APNet has much faster response when the available bandwidth drops, and then reduce 5% of the loss ratio. So overall, the APNet can reduce 1% to 13% loss ratio in different scenarios. And this figure shows the bus loss scenario. And because we set the inherent network loss ratio to 23%. And the left figure is the normal UKF, and the right figure is our newly proposed APNet. We can see the obvious gain. So actually, the APNet can tolerate the inherent network loss and achieve at most 2.25 times more throughput. So in addition to the conjunct control and real-time communications, so we also conduct some of the university networking education project on OpenNet Lab. And this is driven by current ONL chair, Professor Chen Tian in Nanjing University. To facilitate the university networking courses, so Professor Chen Tian worked with the ONL developers and his teaching assistant to design and implement a networking education platform based on the ONL. So it has many desired features which are quite useful for the networking education. For example, it is an automated platform for real end-to-end networking experiments, and the experimental scheduling, results, and log collections for students and TAs are all automated. So now the networking education service on ONL is already online in Nanjing Universities. So by far, we have already 154 students in CDI experiments in total. So among them, 152 students have already submitted their experiments results with 385 successful submissions. And TI has already got 2,600 logs queries. So moreover, there are many other projects on ONL led by many ONL members. So for example, those from Korean researchers and Singapore researchers, as well as some Peking universities. So last but not least, OpenNet Lab is also used to host the ground challenges for multimedia communication system research. So ONL collaborated with the Microsoft product group to host such ground challenges on bandwidth estimation for real-time communications on MMC21. The basic idea is that we provide the Google conjunct control in a WebRTC with real trace, and we provide the GIM environment called Alpha RTC. So the simulator and the sample trace, and ask the participants to train their model based on those materials. So everyone submits their bandwidth control, bandwidth estimation model, and compete which one is the best. So now the GIM and the Alpha DC and all the traces are open source at this GitHub page. So here are some more details about the such details. So participants can submit their training model to OpenNetLab, and we run the experiments and calculate the results based on the metrics to rank each participant, and then rewards the top participants. So the champion will be rewarded 32,000 RMB, that is $5,000 US, and the run-up would be awarded 16,000. That is equivalent to 2,500 US. So now that the abstract registration due is tomorrow, and the final deadline is around 4 weeks later, July the 19th. So welcome to submit your own model on MMS 21. So in summary, so OpenNetLab actually is a new data-centric training and evaluation platform for networking applications research. So we're going to build a large-scale heterogeneous testbed with heterogeneous networking connections among 10 universities or lab. So currently we support different use cases. For example, the conjoint control, bandwidth estimation, and the ground challenge on MMS 21. So yeah, so that is the end of my talk. So we welcome all the participants and interested researchers to join this OpenNetLab. And please visit us at this page, the opennetlab.org/join. Thank you very much.
Oh, thank you, Yunqiang, for the great talk. And also the competition looks very attractive. Now we have Chen Hu had a question. Please go ahead.
Okay, thank you, Chair. So Xiong, very impressive talk. I can see it's a very good initiative. So I have several questions. So the first one, how can you compare with your ONL with like Planet Lab? So you all have some, different nodes and collect the data. Yeah. So what's the difference? This is my question. Okay.
Yeah. So the highlight and uniqueness, or we want to differentiate with the Planet Lab is that first we admit that that is sort of the reinvent the wheel. So we are going to reproduce reinvent some of the networking platform wheel. And the second, that we like to provide some of the unique features, such as, for example, heterogeneous or mobile networking environment, mobile nodes, or even mobile nodes. And the third, that is, we like to have a data-driven diagram in the platform, so we can automatically distribute the job, automatically collect data and store the data and do the data analysis, and finally publish the data to form the common ground for the data set, so that others can compete and evaluate again against each other with the same common data set. So yeah, so the first one, I admit, actually that is some sort of the reversion, and the third one and the second and the third one, we'd like to make some more differentiation and contribution over that.
Okay. Regarding the data collected by the heterogeneous, and devices, so are these data generated manually, or someone is really using this device?
Currently, that is it is not generated by some probing tool. So it is generated by the real application. But currently, those real applications is not other testing user. So we use the testing user using the real application, for example, the WebRTC or some of the other networking tools to generate those networking traffic. So the user are the testing one, and the applications are the real one.
Okay, thank you. And also, you mentioned that you have some proprietary primary, experiment to do the bandwidth estimate and to train, a model for RL. So how do you know the ground truth of the bandwidth?
Yeah, for that one, actually, so that's why we need some of the dream environment. And even for the challenge, we will also provide RFRTC, which actually they can train the model with some of the predefined and pre-configured network emulators. So by that, we first train the model in the emulator or simulator or the NetTM. That is basically a TC traffic control in Linux. And then we compare. Currently, for the real networking environment, we don't have the ground truth for the comparison. So we only have the comparison against the previous version, for example, the UKF or some other congestion control algorithms. So that is the baseline, because we cannot reproduce the model in the real environment with the same networking condition.
Okay, thank you very much. So in fact, I have more questions, but we can discuss offline. Just give the chance to others. Okay, thank you very much.
All right, do we have any other questions? If not, maybe let's thank the speaker again.
Thank you.
Thank you. Right, is Dr. Feng Yang here? Can you turn on your mic?
Can you hear me? Sorry, I just muted my mic. Can you hear me now? Hello?
Yes, we can hear you.
Okay, but I don't see that. I see the video is static. Okay.
It's moving now. Can you share your screen?
Okay, thanks.
Oh, now we can hear you. Okay, great. All right, so let's welcome our last speaker in this session, Dr. Feng Yang. So Feng Yang received his PhD degree in electrical engineering from Tsinghua University. He's the chief architect of Tencent Cloud, leading the development of the innovative edge computing and cloud networking technology driven by 5G and beyond. Before joining Tencent, Feng worked in Orange Labs and later in Intel Lab as a senior research scientist on mobile networks, especially in 4G, 5G, SDN, and NVF. Today, he's going to tell us about Tencent Cloud Cellular Network Accelerator, a new paradigm for connecting to the cloud anywhere. Let's welcome.
Thanks, Chairman, and thanks for the introduction. Just to check, can you see my screen? The slides I'm sharing?
Yep, perfectly.
Okay, thanks. And so my name is Feng Yang from Tencent. I'm the chief architect of Tencent Cloud. And today I'm going to introduce the latest progress in Tencent Cloud networking, which is called Tencent Cloud Cellular Network Accelerator. And this is outline of my presentation. First, I would like to introduce some background and motivation of our work. And second, I will dive into the technical details of the TCNA, Tencent Cloud Cellular Network Accelerator. And third, I will present some trial results that we did with operators. And this slide is an overview of Tencent Cloud networking. Okay, Tencent Cloud networking basically can be divided into several layers. From top to the bottom are respectively the in-cloud networking, cross-region interconnect, and the hybrid cloud networking. For the top layer, the in-cloud networking, we have a couple of products for our tenants. Maybe one of the most important product we present is virtual private cloud, so which creates an independent network space for our tenants in Tencent Cloud. And other products including the night gateway, elastic IP, EIP, and Anycast acceleration, which provide high-performance internet access for
tenants on in the Tencent Cloud. And others also have, include the cloud load balancer, which provides the function to, for service scalability and to avoid a single point of failure. Here are some numbers for the, in that cloud networking. We have more than 20 data centers worldwide, and we have more than 40 BGP lines with both domestic and foreign, overseas internet service providers. And regarding the VPC, which is one of the most important products we have, the milestone is that the VPC 3.0 can support up to 3 million virtual machine instances in a single cloud. So that's pretty much, and as we estimated, it can satisfy the increase of our customers, the largest customers on Tencent Cloud in the coming 3 years. Regarding the middle layer, the cross-region interconnects, the product is called Cloud Connect Network, so which provide full mesh interconnections for VPCs across multiple regions. So as a customer, if you have a VPC on Beijing region and also on Shanghai region, and you can use Cloud Connect Network to collect them together. And the bottom layer is the hybrid cloud networking, which interconnects the customer's infrastructure on the premises, for example, their headquarters or the IDCs with the resources on the Tencent Cloud. So that's one of the, that's the area that has been developing so fast today. And also one of the topic areas that I'm going to discuss today. This is the current status of the hybrid cloud networking. And in Tencent Cloud, we have 3 products, so which are respectively the Direct Connect, VPN, and SD-WAN. So among the products, and the most popular hybrid cloud networking product is still the Direct Connect, and it's also the choice of our tier 1 and tier 2 customers, because the Direct Connect can bring a very large bandwidth. For a single line, the Direct Connect can bring at least up to 10 gigabits per second. And if we aggregate multiple lines, this number can increase multiply. And the Direct Connect can bring very low latency and best quality of service. The only problem is that it cannot support mobility. But for VPN and SD-WAN, the bandwidth is smaller and the latency is higher and the quality of service is worse. But SD-WAN for 4G and 5G SD-WAN, the features that it can support some part of mobility with mobile networks. So with that, and we have 3 kind of hybrid cloud networking technologies in our product portfolio. So the question is, why do we need to introduce the 4th one? I mean, the Tencent Cloud Network Cellular Network Accelerator. So the short answer to that question is that none of the 3 products I presented in the previous slide can satisfy some customer pain points rising from part of our customers. So here I give some example. So the customer, we selected 2 customers and to show what the pain points are. So for customer A is running esports games, and for example, like KPL or KGL. And so they have the list line connected their esports arena with Tencent Cloud. The problem is the days that they have esports game are less than 1 month within 1 year. But the price they have to pay for the list line is that they need to pay the subscription for at least 1 year. So they want to have a solution that can be charged based on usage rather than annual subscription.
but also they also care about quality of service because there's important for them to have a stable bandwidth connected with their arena and the Tencent Cloud when the esports games happen. And another customer is driving is running a broadcasting car for broadcasting, and they connected to the cellular network and finally connected to Tencent Cloud with internet. So their problem is they subject to performance degradation and during traffic peaks or network congestion. And so their demand is they want some kind of mobility, but also they want very high quality, the very strict quality of service. So with that, in summary, so our customer want to have a technology that can be charged based on usage and can have quality of service and also can bring a kind of mobility. So that's the features what TCNA, Tencent Cloud Cellular Network Accelerator, can bring to our customer. And the second part is about the technical details of the TCNA. So what's TCNA? Sorry. A quick answer to that question is that TCNA is a synergy of 5G network and the direct connect we have. And when we designed TCNA, the key features we had to address include first how to connect the 5G network to the existing DC system of Tencent Cloud. So that's not a very easy question very easy question to answer because the existing DC gateway, I mean a gateway of the DC cloud only accepts data compatible with 802.1q, the WLAN. So obviously, the 5G network cannot, the output of the 5G network cannot satisfy such condition. So to solve the problem, we introduced a new network element, which is called the Tencent Smart Access Connector, TSAC, on this figure. And the second question is, the second problem we need to solve is how to provide end-to-end quality of service. To that end, we closely work with operators to design a set of APIs, to create 5G network slice and to configure and 5G QoS parameters for our TCNA tenants, so that we can provide end-to-end quality of service for our customer. So in summary, as a synergy of 5G network and direct connect, TCNA can have the feature with DC grid performance, support of mobility, and beam plug and play. So that's something that we cannot find in the traditional hybrid cloud networking technology. Here's the control plane design of the TCNA, some technical details. So the TCNA control plane can be divided into 3 parts. And so the first part is about the control of the CPE. And so the second part is about control of the 5G core network as well as the TSAC gateway. And the third part is the existing DC system, meaning that the DC gateway and the DC gateway controller. So as a customer, as a user of TCNA, what the user have to do is just to invoke the cloud APIs through the console of Tencent Cloud, and first to create a DC gateway, and then bind the CPE to the DC gateway, and then the console will automatically configure both the CPE and the 5G network, the TSAC gateway, as well as the DC gateway within several minutes. So through the control plane I show on this slide. And so this is the user plane of the TCNA. And so which is comprised by CPE 5G network, TSAC gateway, and DC gateway. Suppose, we have two tenants that happen to have two identical subnetworks, both in cloud and outside cloud. And suppose the host with the IP address of 192.168.1.2 want to send data to a host on the cloud with IP address of 2.2. And first, the CPU will receive an IP packet, and then the CPU will add the IPsec header on top of that. The IPsec header is a kind of identity of the tenant which can be recognized by the TSAC gateway. After IPsec encryption, then the CPU will send the IPsec tunnel data to the 5G network. In the 5G network, the UPF will add the GRE tunnel header on top of the IPsec data. And the GRE header are identical to all tenants of Tencent Cloud. And when the TSAC gateway receives the GRE tunnel data, and first it decrypts the GRE header, and then decrypts the IPsec header. So by decrypting the IPsec header, the TSAC gateway can find the tenant-related information, and then it will transform the tenant information to the 802.1q VLAN tag, and then send the data to this DC gateway, and which will finally encapsulate the tenant's data within the TGRE tunnel and send to the host on the cloud. So you see that IPsec header plays an important part and to include the tenant-related information. This is a routing plane of, this is a routing plane of the TCNA. Okay, and the routing plane, a function of routing plane is to distribute, sub-network information onto the CPE, TSAC gateway, as well as the DC gateways. So the figure on the left-hand side shows how the sub-network information of the VPC on the cloud are propagated to the CPE as well as TSAC gateway. So the first, the DC gateway will announce a prefix where the BGP session established between TSAC gateway and DC gateway. And then the TSAC gateway will report the prefix to the controllers, and the TSAC controller, and then configure this prefix to the SD-WAN global controller, and finally, the prefix will be installed on the CPE. The figure on the right-hand side is an example to show how the prefix sub-network information outside the VPC can be propagated to the network element on the cloud. So first, the user need to manually, configure the prefix and through the console of the Tencent Cloud. And this prefix will be installed on the CPE through the SD-WAN global controller as well as the CPE controller. And on the other hand, this prefix will be installed through the TSAC global and TSAC regional controller, and finally installed on the TSAC gateway. With the BGP session established, then the TSAC gateway will announce this prefix to DC gateway so that the prefix can be synchronized among CPE, TSAC gateway, and the DC gateway. And the forwarding plane can forward data from the IDCs of the customer to the VPCs on the Tencent Cloud. So, and the slides and that followed show some, show the key features of our TCNA. And so the first feature is that fast delivery. We compared with the delivery time of TCNA with that of the Direct Connect. So as a subscriber of Direct Connect, if you subscribe the list line on day 1, and it's likely that you won't get your list line ready, until day 30 or day 45, meaning that it would take at least 1 or even 2 months for your vendors, for your suppliers to get the list line ready. But for TCNA, if you subscribe TCNA service on Tencent Cloud on day 1, and on day 3 or day 4, even on the second day, you will receive a CPE like this. You power on the CPE, and then you'll be connected to the Tencent Cloud with a TCNA service within just 1 minute. And the second feature is end-to-end QoS provisioning. And so as a vendor, as a user of TCNA, and you can use the cloud API provided by Tencent, by the Council of Tencent Cloud, and to configure 5G QoS parameters and configure the 5G QoS service. And then the Council of Tencent Cloud will invoke the loss-bound APIs provided by operators. And the operators' backend server will configure both the 5G base station as well as the transport network of 5G transport network. So for the 5G base station, the parameters, I mean the quality of service is provided by a technology called guaranteed bitrate. So guaranteed bitrate is a kind of air interface technology that can guarantee that your speed, the data rate of your both uplink and downlink transmission will be no less than the target date you set using GBR. But for the non-GBR users, during the network congestion, and their transmission data rate will decrease if the network is heavy loaded. And so in the experimental result part, I will show you the comparison between GBR user and that of the non-GBR user. And regarding the transport network, and for some operator, they also assign high priority transport parameters for the TCNA users. And regarding the interconnect between the 5G network and the Tencent Cloud, and because we have the DC in place, and so it's unlikely that the TCNA user will, you will undergo traffic jam, even in the traffic is, even in traffic peak. But for the other users, they access the Tencent Cloud with the internet. So in case of traffic congestion, when during traffic peak, they were subject to performance degradation. So which lack of kind of end-to-end QoS compared with TCNA users. And the third feature of TCNA's design is high availability. And the purpose of high availability is to avoid a single point of failure. To that end, we set up 2 lines with operators and with the core network, 5G core network of the operators. And we also configured 2 IPsec tunnels for a single CPE user. So in that case, in case of DC fail, and as I showed on the left bottom figure, and the uplink, the CPU will still see 2 next hops to reach to the VPC. The two next hops are respectively TSAC gateway 2 and TSAC gateway 1. And the UPF, the user plane function of the core network will see 1 next hop to reach each TSAC gateway. And for the downlink, and the TSAC gateway will see one next hop to reach to UPF in case of a single DC fails. And the figure on the right shows the case when TSAC gateway, one of the TSAC gateway fails. And for the uplink, the CPU will see only one next hop to reach to the VPC, and the UPF will see two next hops to reach to the TSAC, the second TSAC gateway. For downlink, the second TSAC gateway will see two next hops to reach the UPF because we have redundancy design in terms of both gateway and also the the direct connect with operators. And this part, this is the high availability design on the Tencent Cloud side, quite similar with the with the part on the operator side, and we have dual direct connected design and also dual gateway design. So I will not go through the technical details. And the conclusion is quite similar, that the connectivity can be kept in case of DC or gateway failures in both cases. And this is the fourth feature of TCNA, and users can, which is that users can flexibly switch between the SD-WAN and TCNA. So this is a feature that's very important for our SD-WAN users. And this kind of feature at least can bring two advantages. So the first advantage is that as a SD-WAN user, if you want to transfer to the TCNA, you don't need to buy a new CPE. What you have to do is just to switch the the service mode and from SD-WAN to TCNA and bound your CPE to a specific DC gateway, and the controller will automatically configure the rest for you. And another benefit is that as a TCNA user, so when you need some kind of roaming, I mean roaming means that you want to use it in another city or in another place where TCNA is not deployed, and so you can simply change the mode to SD-WAN mode, and by bound your CPU to one of the Cloud Connect network, so that you can still be connected to Tencent Cloud with internet, not with the 5G network slice or the DC, but you can still be connected with internet. So the CPU can still work, and you don't need to transfer or change to buy a new one. And the fifth feature is the end-to-end operation management, and it's a kind of design has not been implemented yet because the interface between the Tencent and the operator is still under discussion. And our purpose is to provide end-to-end operation and management for customers. And for the Tencent side, I mean, the equipment or devices that are owned by Tencent, we would perform packet capture on the CPE, the TSAC gateway, and the DC gateway. And for the operator side, it has been confirmed that it's impossible to do packet capture. So instead, we ask the operators to do traffic statistics for us and provide the traffic statistics data to Tencent via the interface negotiation. And good news is that the operator is committed to help us with the packet statistics on the N3 and N6 interface of the UPF, so that by doing so, it will be possible for us to figure out where the failure or packet loss happen and what the cause of failure or packet loss is. in case of failure of packet loss. The third part is the trial results we did with China Mobile and China Unicom in Beijing. With China Mobile Beijing branch, we deployed the TSAC gateway in the IDC of their, in China Mobile Beijing. And we also deployed CPE in the Beijing branch, the building of Beijing branch where there is 5G indoor coverage. So the purpose with China Mobile Beijing is to test the feasibility of, to test the function of TSAC gateway, as well as to validate the end-to-end QoS, the GBR features, the readiness of the GBR. And for China Unicom, and we deploy a CP in the headquarters of Tencent Beijing, and where we already have 5G indoor coverage. And so the purpose is just to validate the readiness of GBR, I mean the 5G QoS features provided by China Unicom. Here are the results of GBR testing. And so the left-hand side is the result with the China Mobile, and the right-hand side is the result with China Unicom. For both operators, you can we add non-GBR users as low priority users under the same base station. First, we start the non-GBR users, and you can see that the speed, the transmission speed is good. But after a while, we start the GBR user, and you'll find that the transmission data rate of the non-GBR user decreased very sharply. After we stop the GBR user, and their transmission speed recovered and back to the as the GBR user is not there. And for the China Unicom case, and the results quite similar. The difference that we introduced 2 non-GBR users, but the conclusion is that if we introduce the GBR user, and the transmission speed of the non-GBR user will decrease sharply, and after GBR user stops sending data, and the transmission data rate will recover for the non-GBR user. And here's the latency measurement testing with China Mobile, and we did a half day pin testing. I mean, using ICMP Echo, and we connect the RTT data and to plot the data with both histogram and the CDF. So the left hand side is the histogram, and you see that most of the RTT value lies somewhere between 17 milliseconds and 23 or 24 milliseconds. And if we plot the CDF of the RTT data, and so the conclusion is that 90% of the RTT is less than 25 milliseconds, which partly meet our design goal in terms of latency. But we have to see that there's still some room to improve for the 5G network in terms of latency, because compared with the DC system, the latency is still a little higher. Okay, this is the final slide I have today. And so what's next? And we will open the test of the TCNA for invited customers in the next quarter in Beijing. And the 5G network of 2 operators will be available during the test. And we plan to add more cities, the tier 1 cities, including Shanghai, Shenzhen, Guangzhou, later, and for TCN testing. And the commercial rollout is planned by the end of this year. And our long-term plan is to cover most of provincial provincial capitals, such as Chengdu or Nanjing in the long run. So for the audience, if you want to join the test of TCNA, and welcome to send the email to me. And so to Feng Yang, FENGFYNG@tencent.com. And that's pretty much I would like to share with you today. And with that, I'd like to take your questions. Thank you.
All right, thanks, Feng, for the great talk. Let's see, do we have any questions from the audience? If not, I have one quick question. So from this work, I can see that actually needs Tencent to establish extensive joint effort with the mobile carriers. Could you share some lessons you learned from this process or this whole procedure?
Okay, so it's a short question, but I may not come with a short answer. As you said, the collaboration with operators is not very not very easy. But I think the advantages we have is as a team from Tencent, and maybe one of the biggest customers of the operators, they would like to collaborate. So collaboration with operators, I think. First, we will have a holistic design of what our system is. That's our responsibility. So we need to explain to them and what our need from you in terms of net topology and in terms of for example, regarding the high availability design, we need two lines, and we also need to ECMP established between operators and Tencent side. So we need to make that very clearly, and maybe not within one email, but a round of emails we discussed, and to confirm that that's what we need and what you have to provide. And the second part is we need to give them some guidelines about our usage, how this kind of product can be used in the future, and that's also a motivation for the operators to collaborate. And some other tricks like you need to give them some expectations on the revenue or expectations on the profits they can have in the long run. It's also helpful for us to collaborate with them. So in a summary, so as a team from Tencent, I think it's more easy for us to collaborate with operators. But for other companies, I should say the collaboration may be even harder.
Mm-hmm. Thanks for sharing. Do we have more questions? If no, let's thank Dr. Feng Yang again. Thank you for a great talk.
Thanks, Chairman.
And we are running actually a little bit ahead of time, but maybe it's better for us to go to dinner first. Then I will hand it over to the host.
Okay, thank you very much. So hope everyone enjoyed the wonderful talks today. And tomorrow we will start at the same meeting room at 9 o'clock. See you all tomorrow. Bye.